Imagine a single research paper, one that didn't just, tweak something existing, but fundamentally reshaped an entire field. It became the bedrock for these incredibly powerful tools we use now, like ChatGPT, like Google Translate. It really transformed how we interact with AI. Today, we're taking a really deep dive into that very paper, a true landmark.
That's right. We're unpacking Attention is All You Need, the seminal 2017 paper by Vaswani and his colleagues. You've probably heard the name. You almost certainly use technologies powered by the transformer model it introduced probably every single day. But how much do you truly understand about what makes it tick, beneath the surface?
Yeah, that's our mission in this deep dive. We want to peel back every single layer of this groundbreaking work. We're going to explore its core innovations really rigorously to find its mathematical underpinnings and uncover its profound implications. Think of it like a guided tour, page by page, sentence by sentence. We want to make sure you gain a truly comprehensive and informed understanding, not just the what, but crucially the why behind every design choice these authors made.
Exactly. And our sole guide for this journey is the original Attention is All You Need paper itself. We'll be walking right through it section by section, making sure you get that informed understanding. So let's start right at the very beginning, with its incredibly bold abstract and introduction.
The abstract, it just immediately declares this revolutionary intent. It plunges us directly into the landscape before the transformer existed. So back then, the dominant models for what they call sequence transduction, basically, taking one sequence, turning it into another, like English to German translation, they were typically built on complex recurrent neural networks, RNNs, or sometimes convolutional neural networks, CNNs. These usually had an encoder-decoder structure.
Right. To kind of visualize this, the encoder would read the entire input sequence, let's say an English sentence word by word, basically, and it would build up this thought vector or a series of hidden states that sort of summarize the input. Then a separate decoder would take that compressed representation, that summary, and generate the output sequence, maybe in German, word by word.
Okay, so encoder reads, decoder writes.
Pretty much. And even back then, attention mechanisms were already being used. But, and this is key, they were largely an add-on. They help the decoder connect back to relevant parts of the encoder's output. So it could dynamically focus on which input words were most important when generating a specific output word. The crucial point here, though, is that these attention mechanisms were almost always used in conjunction with RNNs or CNNs. They just augmented the main architecture.
Got it. They weren't the main event.
Exactly. And this is where the transformer just bursts onto the scene with its radical proposition. The paper states, with remarkable clarity, we propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely.
Wow. Okay, that is a huge declaration. What exactly does it mean to be solely on attention? And what's the real significance of dispensing with recurrence and dispensing with convolutions?
Well, dispensing with recurrence is monumental. Recurrent networks, RNNs, by their very nature, process sequences sequentially, one element at a time. So imagine you're processing the sentence, the dog ate the apple, and RNN first processes the, then dog, then ate, then the, and only then apple. To understand apple, it needs to know what came before it.
Right. Context matters.
Exactly. So the paper explains it like this. HT, which is the hidden state for the word at time t, is inherently a function of the previous hidden state HT1 and the input for position t. You literally cannot compute HT until HT1 is fully processed. This sequential dependency creates an inherent bottleneck. It makes training slow, especially on modern hardware like UPUs, which are designed to do tons of computations simultaneously in parallel. You just can't parallelize a sequential process like that.
Okay, that makes sense. So that's recurrence gone. What about dispensing with convolutions? CNNs can be parallelized, right?
They can, yes. CNNs offer more parallelism than RNNs, but their ability to capture long-range dependencies, how words far apart in a sentence relate to each other, that requires stacking many, many layers. Each convolutional layer only has a limited receptive field. It only sees a small local window of words. So to get information from the beginning of a really long sentence to its end, you need a deep stack of these layers, and that increases the path length for information.
Ah, the path length problem again. And longer paths make learning harder.
Precisely. This extended path makes it much harder for the network to effectively learn those distinct connections. Gradients can vanish or explode over long paths. So by declaring solely on attention, the authors are basically saying this one mechanism, attention, can handle everything that recurrence and convolutions used to do, but crucially, it can do it without their inherent limitations in speed or path length.
That simplification sounds powerful. And it leads directly to their groundbreaking claims, which really shook the AI world. The first claim is about quality. The paper says it achieves superior performance, specifically 28.4 BLEU on the WMT 2014 English to German translation task, improving over the existing best results, including ensembles, by over 2 BLEU. Okay, for listeners who might not be deep in machine translation, what does a 2 BLE point improvement actually mean in practice? It sounds small.
Yeah, it might sound small, but in machine translation, a 2 BLEU point improvement is actually incredibly significant. It often means a really noticeable qualitative leap in how fluent and accurate the translations feel. It's not just a tiny edge, it's a clear signal the model is producing much better, much more human-like output. And the phrase, including ensembles, is key here too.
Right, what does that add?
Ensembles are usually the top performers. They're made by combining predictions from multiple models. It's computationally expensive, but it typically gives the best results. So the transformer achieving better results as a single model compared to these complex, costly ensembles, that was a really powerful testament to its raw power and efficiency.
Okay, quality is one thing. Then they highlight parallelization, more parallelizable. Why is that so critical for modern computing, especially large-scale AI training?
Oh, it's absolutely fundamental. Modern deep learning basically runs on parallel processing, primarily on GPUs, graphics processing units. GPUs are brilliant at doing massive numbers of calculations all at the same time. Recurrent networks, with that sequential nature we talked about, directly choked off this parallelism. They were a bottleneck. The transformer, by being solely on attention, allows almost all the computations for an entire input sequence to happen at once, in parallel.
Ah, so it fits the hardware perfectly.
Exactly. It aligns perfectly with how GPUs work. This enables dramatically faster training times, especially with the huge datasets we use now. And that unlocks the ability to train much, much larger and more capable models than were feasible before.
Which leads right to their third claim, requiring significantly less time to train. They give a really specific, punchy example. English to French translation task. Our model establishes a new single model state-of-the-art BLE score of 41.8 after training for 3.5 days on 8 GPUs, a small fraction of the training costs of the best models from the literature.
Yeah.
Okay, 3.5 days on 8 GPUs still sounds like a lot for maybe an individual, but in the context of big AI research labs.
It's mind-bogglingly fast, absolutely. While 3.5 days on 8 high-end P100 GPUs might seem substantial, you have to compare it to the weeks, sometimes even months, some previous state-of-the-art models took, often on even more hardware. It represented a massive reduction in training time. The practical impact was huge. It meant researchers could iterate faster, try more experiments, deploy powerful models much more quickly. It sort of democratized access to training truly state-of-the-art models for more research groups.
Faster research cycles, faster progress. Makes sense. And finally, the abstract mentions generalization. It says, the transformer generalizes well to other tasks by applying it successfully to English constituency parsing both with large and limited training data. Why is generalization such an important measure for an AI model?
Generalization is crucial. It tells you if a model has learned underlying abstract patterns that apply across different tasks or domains, rather than just, memorizing the specific training examples it saw. If a model only works well on the exact task it was trained for, its usefulness is pretty limited. The transformer's ability to take its core architecture, apply it to a totally different structurally complex task like parsing, and perform well even with limited data that signaled its robustness and adaptability. It's a key indicator of a truly powerful and versatile AI architecture.
That's a great point. Before we move on from the abstract, I just want to briefly acknowledge the authors here. The paper lists them as equal contribution, which is interesting, and then gives these fascinating insights into each person's specific role. Like Jacob Uskarate proposed replacing RNNs with self-attention. Ashish Vaswani and Ilya Polasukin designed and implemented the first models. Noam Shazir proposed scaled dot product attention, multi-head attention, positional representation, and Nikki Parmar, Lion Jones, Ugas Kaiser, and Aidan Gomez were also instrumental in developing, implementing, tuning, accelerating. It really shows the collaborative genius behind this breakthrough.
It really does. It was a remarkable combination of brilliant minds all tackling this fundamental problem together. Okay, now let's transition into the introduction section of the paper. This really lays out the problem with the status quo in sequence modeling at the time. The authors reiterate the dominance of recurrent networks, specifically LSTMs and GRUs, in tasks like language modeling and machine translation. These were the undisputed champions, and people were still making advancements with them.
But the introduction immediately flags the fundamental flaw of these dominant models. It says, recurrent models typically factor computation along the symbol positions of the input and output sequences. What does that mean exactly, to factor computation along the symbol positions?
It means that to compute the representation for the current word, say at position t, the model needs the hidden state that was just computed for the word at position t1, plus the input for the current position t. So back to the dog ate the apple example. To get the hidden state for apple, the RNN first needs the hidden state from the, which needed the state from ate, and so on, all the way back to the. This inherently sequential chain of dependencies leads directly to what the authors call the bottleneck. They state, this inherently sequential nature precludes parallelization within training examples.
And that goes straight back to the GPU problem we were just talking about. And presumably, longer sequences just make this problem worse.
Precisely. The longer the sequence, the longer the chain of dependencies, and the more severe the bottleneck becomes. Now, there had been previous attempts to sort of work around this, things like factorization tricks and conditional computation, and they did achieve, significant improvements in computational efficiency. But the paper really emphasizes the fundamental constraint of sequential computation, however, remains. That statement is critical. It sets the stage for the transformer's complete paradigm shift. It says incremental fixes weren't enough. The core issue persisted.
The introduction then shifts to the rise of attention mechanisms. It notes they have become an integral part of compelling sequence modeling and transduction models, allowing modeling of dependencies without regard to their distance in the input or output sequences. Okay, that's a critical point attention addresses. How exactly does attention overcome that distance problem that often plagued RNNs?
Yeah, in traditional RNNs, information about words at the very beginning of a long sentence could kind of degrade or get forgotten by the time the model processed words way at the end. This was due to things like the vanishing or exploding gradient problem over many sequential steps. Attention mechanisms, however, allow the model to directly look back at any position in the input sequence when it's processing a position in the output. It essentially creates these direct shortcuts or connections between distant parts of the sequence, no matter how far apart they are. So information doesn't have to slowly trickle step by step through a long chain. It can be accessed directly.
But, and this is where the transformer's uniqueness comes in again, the authors add a crucial caveat. In all but a few cases, such attention mechanisms are used in conjunction with a recurrent network. Quote, so most existing attention models were still hybrids, still relying on that RNN backbone.
Yes, exactly. And that's precisely where the transformer really sets itself apart. Its defining principle, as stated, is that it's a model architecture eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. This global dependencies part is key. Instead of just looking at the immediate previous step or maybe a small local window like a CNN might, the transformer can directly assess the relationship between any two words in the sequence. Doesn't matter how far apart they are, and it can do it in a single computational step via attention.
And the practical benefits they cite tie right back to the abstract. Significantly more parallelization and achieving that new state-of-the-art in translation quality after being trained for as little as 12 hours on 8 P100 GPUs. It really drives home the power of this completely new way of thinking.
It really does. Okay, let's move into the background section, page 2. This briefly surveys the landscape of other models that were also trying to tackle this sequential bottleneck problem. The paper acknowledges that the goal of reducing sequential computation also forms the foundation of the extended neural GPU ByteNet and ConvS2S. So these other models were also trying to escape the sequential trap, primarily by using convolutional neural networks, CNNs, as their basic building blocks.
Right, so these earlier attempts were also chasing parallelism, but using convolutions instead of attention. How do CNNs compute representations in parallel?
Well, CNNs apply filters, or you can think of them as small learned patterns, across different positions of the input simultaneously. Imagine a small window, often called a kernel, sliding across a sentence. Instead of processing one word at a time like an RNN, a CNN can apply its kernel to multiple parts of the sentence in parallel to extract local features. This method is definitely more parallelizable than an RNN because the calculations for different chunks of the sequence can happen at the same time.
But the paper immediately points out a limitation with CNNs in this context. It says, in these models, the number of operations required to relate signals from two arbitrary input or output positions grows in the distance between positions, linearly for ConvS2S and logarithmically for ByteNet. This sounds like that path length issue rearing its head again. Why is it still hard to learn dependencies when the path length increases, even with parallel convolutions?
It's a really critical point for understanding why the transformer was such a leap. Path length just means the number of steps or layers information has to travel through the network to get from point A to point B. Even in CNNs, if you want information from the very first word to influence the very last word in a long sentence, you usually need to stack multiple layers of convolutions. For standard CNNs with contiguous kernels, this path length grows linearly with the sequence length. For ByteNet, which used a clever trick called dilated convolutions, it grows logarithmically. Now, logarithmic growth is much better than linear, but it still means that learning truly long-range dependencies remains challenging, because the longer the path, the more chances there are for gradients to vanish or explode during training, making learning difficult. The paper explicitly cites reference 12 on this.
And the transformer's advantage here is just stark. In the transformer, this is reduced to a constant number of operations. Comparing ON, or O log n, path lengths to O1, that feels like a monumental difference, especially for really long sequences.
It's absolutely a game changer. O1 means it doesn't matter how long the sequence is, any position can directly interact with or attend to any other position in a single attention operation, one step. This fundamentally solves the long-range dependency problem that plagued previous architectures. However, the authors are also quite transparent about a potential trade-off here. They mention, albeit at the cost of reduced effective resolution due to averaging attention-weighted positions.
So averaging things out could blur some details.
Potentially, yes. If you just average all the attended information together, you might lose some fine-grained details. But they immediately introduce their solution, an effect we counteract with multi-head attention as described in section 3.2. This is a really crucial early hint about why multi-head attention exists. It's not just about enabling parallelism, but also about capturing diverse types of relationships that might otherwise get washed out by simple averaging.
Okay, that sets up multi-head nicely. The paper then formally defines self-attention, sometimes called intra-attention. It's defined as an attention mechanism relating different positions of a single sequence in order to compute a representation of the sequence. So this isn't the decoder looking at the encoder. This is a word looking at other words within its own sentence. How does that self-referential process help build a richer picture?
It's a really powerful concept. When a word attends to other words within the same sequence, it can dynamically pull in information about its context. Think about a sentence like, the animal didn't cross the street because it was too tired. To really understand what it refers to, a self-attention mechanism could learn to attend directly back to animal. This self-referential process lets each word build a context-rich representation that captures its relationship with every other word in that sentence, not just its immediate neighbors. This is how the model learns meaning from the entire context, not just a small local window.
And the paper lists several prior successes, where self-attention had already shown promise. Reading comprehension, abstractive summarization, textual entailment, learning task-independent sentence representations. Why were those specific tasks particularly well-suited for self-attention?
Well, all those tasks inherently require understanding complex internal relationships within a single piece of text. For reading comprehension, you need to link a question to relevant parts of a passage. For summarization, you need to identify key phrases and how they connect to form a coherent summary. Self-attention is perfect for this because it inherently allows these internal, potentially very long-range connections to be modeled directly. It doesn't have the constraints of sequential processing or limited receptive fields.
The paper also briefly mentions end-to-end memory networks. These were based on a recurrent attention mechanism instead of sequence-aligned recurrence. How are these different from the transformer's pure attention approach?
Yeah, the key distinction is in that phrase, sequence-aligned recurrence. While memory networks did use a form of recurrent attention, meaning attention operations were still part of a sequential step-by-step process, maybe to access an external memory, the transformer completely eliminates any form of sequence-aligned recurrence from its core computations. Its internal layers don't depend on the calculation from the previous time step in the sequence. That's the defining feature of recurrence. It's a subtle but really important difference. It underscores the transformer's complete reliance on parallel attention for its internal processing.
And this leads right to their powerful statement, reaffirming their unique selling proposition. To the best of our knowledge, however, the transformer is the first transduction model relying entirely on self-attention to compute representations of its input and output without using sequence-aligned RNNs or convolution.
Precisely. It clearly stakes their claim to novelty and sets the stage perfectly for the rest of the paper. They promise to describe the transformer, motivate self-attention, and discuss its advantages over those earlier models like extended neural GPU, ByteNet, and ConvS2S.
All right, let's get into the real blueprint then. Section 3, Model Architecture, starting on page 2. The paper confirms that most competitive neural sequence transduction models have an encoder-decoder structure. This seems like a standard, reliable paradigm. Can you just quickly recap the roles of the encoder and decoder in this setup for everyone?
Sure. The encoder's job is to map an input sequence of symbol representations by 1, xn, to a sequence of continuous representations, z equals z1, zdn. So you feed it an input sentence, maybe broken into words or subword tokens by 1 through xn. The encoder processes these and transforms them into z, is a sequence of these rich, contextualized feature vectors. You can think of z as capturing the meaning or the essence of the input sentence, but represented numerically.
Okay, encoder produces this meaningful representation z. What does the decoder do with it?
Given z, the decoder then generates an output sequence, y1, my yim, of symbols one element at a time. So the decoder takes that full contextualized representation z from the encoder and uses it as a guide to generate the output sentence, token by token. And critically, for generating sequences, at each step, the model is autoregressive, consuming the previously generated symbols as additional input when generating the next.
Autoregressive. So if I'm translating the dog barks to French, and the decoder has already output le chien to predict the next word, aboie, it needs to know it just said le chien. It uses its own past output.
That's a perfect example, exactly. This autoregressive property is standard in most sequence generation models. Now, the transformer follows this overall encoder-decoder architecture, but here's its core innovation in how it builds them. It uses stacked self-attention and point-wise, fully connected layers for both the encoder and decoder, shown in the left and right halves of Figure 1, respectively. So if you're looking at Figure 1 in the paper, you can see the encoder stack on the left, decoder stack on the right.
Okay, let's break down these stacks, starting with the encoder stack. It's composed of a stack of NFL 6 identical layers. What does identical layers mean here? Are they literally the same weights?
Good question. They are identical in terms of their structure and the components they contain. Each of these 6 layers has the exact same sublayers inside. However, and this is crucial, each of these identical layers has its own distinct set of learnable parameters, its own unique weights and biases. So while they look the same on the diagram, they learn different things. They learn progressively more abstract transformations of the data as it flows up through the stack. Each of these identical layers has 2 main sublayers. First, a multi-head self-attention mechanism, and second, a simple position-wise fully connected feed-forward network.
And then come 2 absolutely critical additions that really enable training deep networks like this: residual connection and layer normalization. The paper is very clear. We employ a residual connection around each of the 2 sublayers, followed by layer normalization. That is, the output of each sublayer is layer norm x plus sublayer x. This combo is fundamental in deep learning now. Can you explain what residual connections do and why they're so vital?
Absolutely. Residual connections, often called skip connections, are quite simple conceptually, but incredibly powerful. They allow the input x to a sublayer to be directly added to the output of that sublayer, sublayer x. So you compute x plus sublayer x. This creates a direct shortcut or path for information, and more importantly, for gradients during back propagation. In very deep networks, without these shortcuts, gradients can vanish, become too small to be useful, or explode, become too large and unstable as they propagate back through many layers. This makes training extremely difficult. By allowing the original information x to flow through directly via addition, residual connections ensure gradients can flow more freely. This stabilizes training, prevents information from degrading layer by layer, and allows us to successfully train much, much deeper networks.
Okay, so residuals help gradients flow. What about the layer normalization part? How does that fit in, and how is it different from something like batch normalization?
Right, so after the residual addition x plus sublayer x, they apply layer normalization. Layer normalization works per sample and normalizes across all the features within that single sample. It calculates the mean and variance across the feature dimension for each individual input vector and then normalizes it. Batch normalization, in contrast, normalizes across the batch dimension for each feature independently. In sequence models, especially where sequence lengths can vary, batch sizes might fluctuate, or different features might just have vastly different scales, layer normalization is often preferred. It helps stabilize the activations by ensuring they have a consistent mean and variance for each sample independent of the batch. This makes the training process smoother and often leads to faster convergence. It works really well with residual connections, preventing the summed values from growing too large or unstable.
And to make that residual addition x plus sublayer x actually work mathematically, the paper specifies a consistent dimensionality. To facilitate these residual connections, all sublayers in the model, as well as the embedding layers, produce outputs of dimension D model equals 512. Why is that consistent size so important?
It's purely a necessity for the vector addition. You're literally performing element-wise addition between the input vector x and the output vector sublayer x. For that addition to be defined, the vectors must have the exact same dimensions. If x has dimension 512, the output of the sublayer must also be 512 so you can add them together. This D model of 512 becomes a foundational constant defining the internal width or representational size throughout the transformer architecture.
Got it. Now let's look at the decoder stack. It's also composed of a stack of n equals 6 identical layers, just like the encoder. But it has one crucial architectural difference. In addition to the 2 sublayers in each encoder layer, the decoder inserts a third sublayer, which performs multi-head attention over the output of the encoder stack.
This sounds like the classic decoder attention, or what people sometimes call cross-attention.
Exactly. Right. That third sublayer is what's commonly called cross-attention. Its purpose is to allow every position in the decoder to attend over all positions in the input sequence. This is the critical bridge. It's how the decoder looks at the source sentence's rich, contextualized representation, Z, that the encoder worked so hard to produce. It's the mechanism linking the source information to the target language generation process. As the paper says, it mimics the typical encoder-decoder attention mechanisms seen in earlier models. And just like the encoder, the decoder also uses residual connections and layer normalization around each of its sublayers. But there's another critical modification unique to the decoder's self-attention sublayer. Quote, we also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. Why is this prevention step so critical for how the decoder operates?
This is absolutely fundamental for maintaining that autoregressive property we talked about, especially during training. When the decoder is actually generating a sentence, say translating, it can only see the words it has already generated up to that point. It can't peek into the future and see the words it hasn't produced yet. To enforce this constraint during training, where the entire correct target sequence is available, they implement a very clever masking mechanism within the self-attention layer.
Okay, how does this masking work at a technical level? How do they stop it from cheating?
The paper explains. This masking, combined with the fact that the output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at positions less than I. The masking itself is implemented inside of scaled dot product attention by masking out, setting to infinity, all values in the input of the softmax which correspond to illegal connections. So, before the softmax step calculates the attention weights, any connection where a position I tries to attend to a position J where Ji, i.e. a future position, has its attention score forcibly set to negative infinity. When you take the softmax of negative infinity, the result is effectively 0.
So the attention weight for future words just becomes 0.
Precisely. This means those future positions contribute absolutely nothing to the weighted sum for the current position's output. It elegantly enforces causality, ensuring the model learns to predict the next word based only on the past, just like it will have to do during actual generation.
That's a really neat and essential design choice. Okay, let's move to the absolute heart of the transformer. Section 3.3, attention. The core mechanism. The paper gives a general definition. An attention function can be described as mapping a query and a set of key value pairs to an output, where the query, keys, values, and output are all vectors. That might sound a bit abstract. Can you maybe give us a more intuitive analogy?
Sure, let's try one. Imagine you're at a massive library looking for information on a specific topic. You are the query. Your information need is the query vector. The library's catalog contains entries for countless books. Each book entry have a key, maybe its title, author, keywords that describes what it's about. And each book also has a value, the actual content, the information inside its pages. The librarian's job, which is the attention mechanism, is to compare your query to all keys in the catalog to figure out how compatible or relevant each book is to your question. Books that are highly relevant get a high attention weight missed. Finally, the librarian synthesizes an output for you. This output isn't just one book. It's a weighted sum of information extracted from the values, the book contents. Books that were deemed more relevant, higher weight, contribute more significantly to the final synthesized answer. So the output is tailored specifically to your query based on a weighted combination of all available information.
That's a fantastic analogy. Query, keys, values, weighted sum output. It makes the concept much clearer. Now, the specific type of attention used in the transformer is called scaled dot product attention, shown on the left of figure 2. The inputs are queries and keys of dimension dk and values of dimension dv. Let's break down the process step by step, including the math and what each part actually does.
Okay, let's walk through it carefully. 1. Compute dot products. The paper says, we compute the dot products of the query with all keys. In the transformer, we're dealing with matrices of these things, not single vectors. So we have a query matrix, Q, a key matrix, K, and a value matrix, V. To get the dot product between every query vector, each row in Q, and every key vector, each row in K, we perform matrix multiplication. Q times KT. Using the transpose KT aligns the dimensions correctly for the dot products. This multiplication QKT results in a matrix of raw scores. Each element, ij, in this matrix represents the raw compatibility score of the dot product between the ith query and the jth key. It's basically how well each query matches each key initially.
Okay, so QKT gives us the raw compatibility scores. What's next?
2. Scaling. This is crucial. Next, they divide each score by score t dk. The operation becomes QKT score tk. This scaling step is absolutely critical for stable training. The paper explicitly explains why. For large values of dk, the dot products grow large in magnitude, pushing the softmax function into regions where it has extremely small gradients.
Can you elaborate on why large dot products lead to these extremely small gradients in the softmax? And how does dividing by score key dk actually fix that? This feels like a really key mathematical insight.
Absolutely. It's fundamental to why this works so well. Let's think about a single dot product between a query vector Q and a key vector K, both having dimension dk. The dot product is QK equals some key across all dk dimensions. Now, if the individual components key and key are, say, independent random variables with a mean of 0 and a variance of 1, which is often roughly true for initialized network weights, then their dot product to key k will also have a mean of 0, but its variance will be dk. This means as the dimension dk gets larger, the magnitude of these dot product values, how far they are from 0, positive or negative, tends to grow.
Okay, so bigger dk means bigger dot products on average. How does that affect softmax?
Right. Now, when you feed these potentially very large or very negative values into the softmax function, remember softmax is XISTA, the outputs get squashed towards the extremes, 0 or 1. If one score cell is much larger and more positive than others, EXI becomes huge, making softmax extremely close to 1, and all other softmax nearly 0. Conversely, if EXI is very large and negative, EXI is nearly 0, and softmax becomes almost 0. In these saturated regions where the output is practically 0 or 1, the gradient of the softmax function, which is what we need for backpropagation to learn, becomes incredibly small, almost 0.
The dreaded vanishing gradients problem.
Exactly. Vanishing gradients mean the network effectively stops learning because the error signals can't propagate back to adjust the weights properly. So by dividing the dot products by scores dk before the softmax, you're essentially normalizing the variance of those scores back towards 1. This keeps the inputs to the softmax in a more well-behaved, non-saturating range. It ensures the gradients remain large enough for effective learning throughout training. It's a really elegant piece of numerical stability engineering.
That's a fantastic explanation. That tiny square dk is doing some heavy lifting behind the scenes. Okay, so after scaling, step 3 is to apply a softmax function to obtain the weights on the values.
Yes, the math is softmax, Q, AT, A star, T, dk. The softmax takes those raw scaled compatibility scores and turns them into a proper probability distribution. Each row in the resulting matrix now represents the attention weights for a specific query. These weights sum to 1 for each query, telling us how much attention or importance that query should pay to each of the keys, and therefore to their corresponding values.
So these are the actual attention weights now. And finally, step 4. The weighted sum of the values.
This is the last multiplication, softmax. You take the matrix of attention weights, the probabilities, and multiply it by the V value matrix. This computes a weighted average of the value vectors. Each value vector contributes to the final output for a query based on how much attention that query assigned to its corresponding key. The result is a new representation for each query that elegantly combines information from all the values in the set, weighted by their relevance.
Okay, putting it all together, the full equation for scaled dot product attention is attention QKV equals softmax QKT square T DK GeV. It seems remarkably concise for something so powerful. The paper also compares this to additive attention and the unscaled dot product attention. It highlights that scaled dot product is much faster and more space efficient in practice since it can be implemented using highly optimized matrix multiplication code. That seems like a huge practical win.
It really is. Additive attention involves using a whole feed-forward network just to compute the compatibility scores, which is much more computationally expensive. Unscaled dot product attention, as we just discussed, suffers from that numerical instability problem. The scaled version cleverly leverages the raw speed of dot products and matrix multiplications operations that are heavily optimized on modern hardware like GPUs, while simultaneously fixing the critical numerical stability issue with that score TK scaling. It's a very elegant and practical design choice.
Agreed. Now let's move on to multi-head attention, shown on the right side of Figure 2. The motivation given is key. Instead of performing a single attention function with demodeled dimensional keys, values, and queries, we found it beneficial to linearly project the queries, keys, and values h times with different learned linear projections to dk, dk, and dv dimensions, respectively. Why is this beneficial? The paper hints it lets the model jointly attend to information from different representation subspaces. What does that mean?
Okay, imagine you're trying to understand a really complex sentence. You might need to look at it through different lenses simultaneously. Maybe one attention head focuses purely on grammatical structure, like subject-verb agreement. Another head might specialize in semantic relationships, like figuring out which noun is the object of which verb. Maybe a third head becomes good at spotting very long-range dependencies across the sentence, while a fourth focuses intensely on the immediate local context. If you only had one attention head, it would have to try and average all these different kinds of relationships together into a single representation. That could potentially blur or dilute important signals.
So multi-head attention is like giving the model multiple different perspectives or lenses to look through simultaneously.
Exactly. That's a great way to put it. Each head learns its own set of linear projection matrices for the input queries, keys, and values. These projections map the original high-dimensional D model input vectors into different lower-dimensional DK and DV subspaces. By doing this, h times, with different learned projection matrices for each head, the model can indeed jointly attend to information from different representation subspaces at different positions. This allows for a much richer, more comprehensive, and multifaceted understanding of the input. Each head can specialize in capturing a different aspect of the relationships between words.
That makes a lot of sense conceptually. Let's walk through the exact process of multi-head attention step by step with the math.
Okay, here's how it works. 1. Linear projections. For each of the H attention heads, let's call a specific head I, where I goes from 1 to H, we apply a unique learned linear transformation to the original Q, K, and V matrices. These transformations use distinct weight matrices, WQI for queries, WQA for keys, and WVI for values. These W matrices are trainable parameters that the model learns, so for each head I, you calculate key, Q, WQI, key chi, KWQI, V, WI, WVI. Each of these projection matrices maps the input D model dimension down to the smaller DK or DV dimensions. This creates 8 different sets of projected queries, keys, and values, each potentially highlighting different aspects of the original information.
Okay, so we project the original Q, K, V down into 8 different subspaces. What happens next?
2. Parallel attention. Now, the paper says, on each of these projected versions of queries, keys, and values, we then perform the attention function in parallel, yielding DV-dimensional output values. This means we run H separate scaled dot product attention calculations simultaneously. Each calculation uses the specific projected key, vi for that head I. So at H, attention, QWQI, KWQI, VWVI, we get H separate output vectors, each of dimension DV.
So H attention calculations running at the same time. Then what?
Concatenation. These are concatenated. The H output vectors, each having DV dimensions from these parallel attention heads, are simply stacked side by side. Imagine putting them end to end. This forms a single larger vector with a total dimension of HDV.
Okay, concatenate all the head outputs. And the final step.
Final linear projection, and once again projected, resulting in the final values. This final step applies one more learned linear transformation. This uses a weight matrix WO. The WO matrix takes the big concatenated HDV dimensional vector and projects it back down to the original D model dimension that the rest of the model expects.
Right, back to 512 in the base model. So the full equation is multi-head QKV equals concast at 1 and head WO. And for the practical parameters, the paper states, in this work we employ HA equals 8 parallel attention layers, or heads. For each of these, we use DK EVV equals D model equals 64. So if D model is a 512, then DK and DV are 512, 8 equals 64. That seemed like a really clever design choice. Balances having multiple heads with a computational cost, right?
It's very clever, yes. The authors explicitly point out, due to the reduced dimension of each head, the total computational cost is similar to that of single-head attention with full dimensionality. Let's think about why. If you had just one single attention head operating on the full D model dimensions, the main computational cost from the matrix multiplies would be roughly proportional to D model 2. Now, with H heads, each operating on reduced dimensions dk EDV equals D model, the cost per head is proportional to D model 2. Since you have H heads running in parallel, the total cost is roughly H D model 2, which simplifies to H D model 2 H2 equals D model 2H. So the total computational cost is actually reduced compared to a single large head, or at worst, very similar. But you gain that huge benefit of capturing diverse information from those different representation subspaces or lenses we talked about.
That's a fantastic trade-off. Same or less cost, but much richer representation. Okay, now let's look at the 3 specific applications of attention in our model, described in section 3.3.3. First, the encoder-decoder attention layers. Here, the queries Q come from the previous decoder layer, and the keys, K and values V, come from the output of the encoder. What's the fundamental purpose of this specific setup, this cross-attention?
This is the primary way the decoder gets information about the source input sentence. Its purpose, as the paper says, is to allow every position in the decoder to attend over all positions in the input sequence. So as the decoder is generating each word of the translation, the output, it can dynamically query the entire contextualized representation Z of the source sentence that the encoder produced. It uses the encoder's output, K and V, to figure out which parts of the input sentence are most relevant for generating the current output word. It's the essential bridge linking source information to target generation.
Got it. That's the cross-attention. Second, the encoder self-attention layers. In this case, keys, values, and queries all come from the same place. The output of the previous layer in the encoder. What's the goal of this internal self-attention within the encoder?
Here, the goal is for the encoder to build up that rich contextualized representation Z in the first place. Each position in the encoder can attend to all positions in the previous layer of the encoder. This means that as the encoder processes the input sentence, say the English sentence, the representation of each word is continually refined by looking at its relationship to every other word in that same input sentence. This is how the encoder learns the context. It understands how dog relates to ate and apple within the sentence the dog ate the apple by letting these words directly attend to each other.
Makes sense. Build context within the input. And third, the decoder self-attention layers, masked. Again, keys, values, and queries come from the output of the previous layer in the decoder. But here we have that crucial constraint we discussed earlier. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. You already explained the masking within infinity. Why emphasize this mechanism again here?
It's emphasized because it's absolutely critical to how the decoder learns correctly. Remember, during generation, the decoder must operate sequentially, word by word, only seeing the past. During training, the entire target sequence is available. Without this masking, the decoder's self-attention would happily look ahead at future words in the target sentence to help predict the current word, which would be cheating. It wouldn't learn the true conditional probabilities needed for generation. By implementing the mask, setting attention scores for future positions ji to infinity before the softmax, they ensure that E infinity becomes 0. This guarantees that those future positions have 0 attention weight and contribute nothing to the current position's output. It forces the decoder to learn to predict U based only on the preceding outputs Y1 through I1, perfectly preserving the autoregressive property needed for generation.
So the attention mechanism itself is modified on the fly to enforce causality. Very elegant. Okay, let's move to section 3.4, position-wise feed-forward networks, or FFNs. The paper states, each of the layers in our encoder and decoder contains a fully connected feed-forward network, which is applied to each position separately and identically. Oh. What does separately and identically mean in practice?
It means 2 things. 1, identically. The exact same feed-forward network with the exact same learned weights, W1, D1, W2, B2, is used for every single position in the sequence within that layer. The parameters are shared across all positions. 2, separately. The computation for each position is done independently. The FFN transforms a vector representation of word 1, then it separately transforms a vector for word 2 using the same weights, and so on. There's no information shared between positions within this FFN step. This design is highly efficient. You get parameter sharing, which reduces the model size, and the computations for each position can be done completely in parallel.
Okay, and the structure of this FFN is clearly defined. It consists of two linear transformations with a ReLU activation in between. The formula given is FFNX equals max 0, XW1 plus B1 W2 plus B2. Let's break this down step by step. What's happening here?
Okay, let's trace the input X, which is the D-model dimensional output from the preceding attention sublayer for a single position. 1. First linear transformation, XW1 plus B1. This is a standard matrix multiplication of the input X by a weight matrix W1, followed by adding a bias vector B1. This typically projects the input into a higher dimensional space. In the base transformer, W1 maps from D-model equal 512 dimensions up to DFF 2048 dimensions. 2. ReLU activation max 0 to 10 applies the rectified linear unit activation function. This is crucial for introducing nonlinearity. Without nonlinear activation functions, stacking multiple linear layers would just be equivalent to a single linear layer, severely limiting the model's ability to learn complex patterns. ReLU simply outputs the input if it's positive, and 0 if it's negative or 0. 3. Second linear transformation, bot W2 plus B2. The output of the ReLU activation is then passed through a second linear transformation using weight matrix W2 and bias B2. This step maps the representation back down to the original D-model dimensionality, so W2 maps from DFF's 2048 back down to D-model 5212.
So it expands, applies nonlinearity, then contracts back. Why this expansion and contraction?
It's thought that this expansion to a higher dimensional space, DFF, gives the model more capacity within that layer to learn more complex features and interactions between the dimensions. It can sort of think in a higher dimensional space before projecting the result back down to the standard D model size needed for the next layer and the residual connection.
The paper also notes, while the linear transformations are the same across different positions, they use different parameters from layer to layer. That makes sense. Each layer learns something different. And interestingly, it says, another way of describing this is as two convolutions with kernel size 1. How can a convolution with a 1-by-1 kernel be the same as this position-wise FFN?
It's a neat equivalence. A convolution with a kernel size of 1 means the filter only looks at a single position's feature vector at a time. It doesn't mix information from neighboring positions like larger kernels do. Applying such a 1-by-1 convolutional filter across a sequence, where the filter's weights correspond to the FFN's W1 or W2 matrix, is mathematically identical to applying that same linear transformation independently to each position's vector. It's just a different perspective, often used by people coming from a CNN background, but it performs the exact same computation as the position-wise feed-forward network described.
Okay, that clarifies the FFN layer. Next up, section 3.5, embeddings and softmax, the input and output layers. The paper mentions using learned embeddings to convert the input tokens and output tokens to vectors of dimension D-model. These are our standard word embeddings, right? Mapping words to vectors.
Yes, exactly. These learned embeddings are fundamental. They take discrete tokens, words like cat, or subword units like ing, and map them into a continuous high-dimensional vector space, with D-model equal 512 dimensions here. The key idea is that the network learns these mappings during training. Words with similar meanings or that appear in similar contexts tend to end up with embedding vectors that are close to each other in this vector space. This allows the model to work with words numerically and capture semantic relationships.
And then at the very end of the decoder, we also use the usual learned linear transformation and softmax function to convert the decoder output to predicted next token probabilities.
Yeah.
This is how it actually predicts the next word.
That's right. After all the attention and FFN layers in the decoder have done their work, the decoder produces a final D-model dimensional vector representing the context for the next word. This vector is then passed through one final learned linear transformation. This transformation projects the D-model dimensional vector into a much larger vector, where the size is equal to the total number of tokens in the vocabulary, for example, 37,000. Finally, a softmax function is applied to this large vector. The softmax converts these raw scores, often called logits, into a probability distribution over the entire vocabulary. The token with the highest probability is then typically selected as the predicted next word in the output sequence.
The paper mentions an interesting optimization here, weight sharing. It says, in our model, we share the same weight matrix between the two embedding layers, input and output, and the pre-softmax linear transformation. Why would they choose to share weights between the input embedding lookup and the final output prediction layer?
That's a really clever technique, often attributed to reference 30 mentioned in the paper. Sharing weights here has a couple of nice benefits. First, it significantly reduces the total number of parameters in the model, especially if you have a large vocabulary. Fewer parameters can help reduce the risk of overfitting and make the model more memory efficient. Second, and perhaps more importantly, it ties the input and output representations of words together. It encourages the model to learn a consistent vector representation for a word, whether it's seeing that word as input or trying to predict it as output. This can lead to better generalization and more coherent representations, especially in tasks like translation where the same words might appear in both source and target.
That makes sense, forcing consistency. And they also apply specific scaling to the embedding layers themselves. In the embedding layers, we multiply those weights by squirt D model. Is there a particular reason for this specific scaling factor, similar to the attention scaling?
Yes, it's related to stabilizing the activations, especially at the very beginning of the network. Remember, the input to the first layer of the transformer isn't just the word embedding, it's the sum of the word embedding and the positional encoding, which we'll get to next. Scaling the embeddings by squirt D model helps to keep the magnitude of the word embeddings roughly on par with the magnitude of the positional encodings, and ensures that the combined input vector doesn't have excessively large values. This can help prevent the activations in the first few layers from becoming too large, which could destabilize training or hinder gradient flow early on. It's another small but important detail for numerical stability.
Okay, stability seems key. Now, speaking of positional encoding, section 3.6, this addresses how the transformer, which fundamentally lacks recurrence or convolution, recovers information about word order. The problem statement is crystal clear. Since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in the sequence. Why is this order information fundamentally lost in a purely attention-based model without this injection?
Because the core attention mechanism, mathematically, operates on a set of vectors. Think of it like putting all the word vectors into a bag. Attention calculates interactions between all pairs of items in the bag, but it doesn't inherently know or care about the original order they went into the bag. If you shuffled the input words of a sentence and fed them into a pure self-attention layer without any positional information, the output representations would likely be identical or just permuted. Attention itself is permutation invariant. It computes compatibility between pairs, Q and K, regardless of their original sequence position. It doesn't intrinsically understand this word came before that word or this is the first word. This is completely different from RNNs, which process sequentially and thus implicitly encode order, or CNNs, where the filter's position provides local order information.
So attention treats the input like an unordered bag of words. The solution. To this end, we add positional encodings to the input embeddings at the bottoms of the encoder and decoder stacks. Oh. And critically, the positional encodings have the same dimension D model as the embeddings so that the two can be summed. Direct element-wise addition. The authors mentioned various choices learned or fixed, but they landed on a fascinating one, using sine and cosine functions of different frequencies. Let's really dig into these formulas. They're a defining feature of the original transformer.
They are indeed iconic. The formulas they use are PE post, sin post, I plus 1 equals cos plus 1001. Let's break down each part carefully to see what's going on. Posts. This is simply the absolute position of the token in the sequence. The first token is post 0, the second is post 1, the third post 2, and so on. This is the dimension index within the D model dimensional positional encoding vector. It ranges from 0 up to D model 2, 1. For each value of I, we calculate two dimensions of the positional encoding vector, one using the sin function for the even dimension 2i, and one using the cos function for the odd dimension 2i plus 1. So the final D-model dimensional vector is composed of interleaved sine and cosine values. 10,000. This is just a large constant chosen by the authors. It acts as a scaling factor that determines the maximum wavelength of the sinusoids used. Two-ed model, this exponent term is really the key to the different frequencies. As the dimension index I increases from 0 towards D model to 1, this exponent 2-ed model increases. This makes the denominator 1008-poded model get progressively larger.
Okay, so the denominator changes with the dimension Ia. How does that create different frequencies?
Because when the denominator of 1002 model is larger, the argument inside the sin or cos function, post-denominator, becomes smaller for a given position pos. A smaller argument means the function oscillates more slowly, corresponding to a longer wavelength or lower frequency. Conversely, when I is small, the denominator is small, the argument is larger, and the function oscillates more quickly, corresponding to a shorter wavelength or higher frequency. So different dimensions of the positional encoding vector end up encoding positional information using sinusoids of different frequencies.
So as the paper says, each dimension of the positional encoding corresponds to a sinusoid, and the wavelengths form a geometric progression from 2po to 10,000 to OP after P2. Why use a geometric progression of wavelengths? Why not just say linearly spaced frequencies?
A geometric progression provides a really nice multi-scale representation of position. Dimensions with short wavelengths, high frequencies, small I, will change rapidly with position, allowing the model to easily distinguish between nearby positions. They capture fine-grained relative position info. Dimensions with long wavelengths, low frequencies, large I, will change very slowly across the sequence, allowing the model to get a sense of the absolute position or to compare positions that are very far apart. They capture coarse-grained position info. Having this mix, covering a wide range of frequencies geometrically, gives the model a powerful and flexible way to represent and reason about both relative and absolute positions at various scales. And the authors had a very specific hypothesis for why this particular sine-cosine function would be effective. They state, "We chose this function because we hypothesized it would allow the model to easily learn to attend by relative positions, since for any fixed offset k, PE post plus k can be represented as a linear function of PE post."
Okay, that sounds mathematically interesting, but a bit abstract. How does that linear function property actually help the model learn about relative positions?
It relates directly to basic trigonometric identities for sums of angles. Remember formulas like sin A plus B plus cos A sin get cos A plus B plus K plus A plus B A sin B. If you think of A as representing the positional term pos, TEED model, and B as representing the offset term K 1000R model, then the positional encoding for a shifted position, PE post plus K, can be expressed as a simple linear combination of the sine and cosine components of the original position's encoding, PE post. Specifically, PE post plus K is basically a rotation of PE post in the 2D space defined by the sin post and components for that dimension I. And rotations are linear transformations. This means that a fixed relative offset K corresponds to a consistent simple linear transformation in the positional encoding space. This property makes it potentially much easier for the attention mechanism to learn how to compute attention scores based on relative positions. It doesn't need to learn some complex nonlinear function of position, it just needs to learn these simpler linear relationships to understand how far apart two words are based on their positional encodings.
That's a really subtle but powerful geometric insight baked into the design. They also mentioned they experimented with learned positional embeddings, like other works had done, and found nearly identical results in their experiments. Table 3, row E. But they still chose the sinusoidal version. Their stated reason is quite forward-looking. We chose the sinusoidal version because it may allow the model to extrapolate to sequence lengths longer than the ones encountered during training. Why is that extrapolation property potentially so important?
It's a significant potential advantage. Learned embeddings are fundamentally discrete. If you train a model on sentences up to, say, 100 tokens long, it learns specific embedding vectors for position 0, position 1, 10 del up to position 99. If, during inference, it suddenly encounters a sentence that's 101 tokens long, it has no pre-learned embedding for position 100. It simply hasn't seen that position during training. The model might struggle or behave unpredictably. Sinusoidal functions, on the other hand, are defined mathematically for any real-valued input pose. They can generate a unique positional encoding vector for position 100, 1000, or even 10,000, even if the model never saw sequences that long during training. This gives the transformer, using sinusoidal encodings, a theoretical ability to generalize gracefully to arbitrarily long sequences at inference time, which is a massive advantage for handling real-world data that might exceed training limits.
That makes perfect sense. Planning for the unknown. Okay, now that we've meticulously walked through the architecture, the encoder-decoder attention mechanisms, FFNs, embeddings, and positional encodings, let's address the core question posed in Section 4. Why self-attention? The paper sets up a comparative analysis framework. They want to compare self-attention layers to the incumbent recurrent and convolutional layers based on 3 key desirable properties, or desiderata, for a sequence processing layer. What makes a good layer in this context, according to their analysis?
Right. When designing a layer to process sequences, especially with an eye towards efficiency in handling long dependencies, they focused on 3 crucial metrics. 1, total computational complexity per layer. Basically, how much number crunching does the layer need to do? Lower is better. Usually expressed in big O notation relative to sequence length n and representation dimension d2. Amount of parallelization, minimum sequential operations. This measures how much of the layer's computation can be done simultaneously. Ideally, you want the number of sequential steps required to be constant, O1, meaning everything can happen in parallel, fully leveraging hardware like GPUs. 3, maximum path length between long-range dependencies. This is crucial. It measures the number of steps or operations information needs to travel through the network architecture to connect any two arbitrary positions in the sequence. Shorter paths are much better for learning long-range dependencies, as shown by prior work 12. A shorter path means gradients flow more easily, and the model can more readily learn connections between distant elements.
Okay, complexity, parallelism, and path length. With that framework, let's dive into the detailed comparison based on Table 1 in the paper. It compares self-attention, recurrent, and convolutional layers on these three metrics. First, self-attention, complexity, ON2, Keats D. N is sequence length, D is representation dimension. Why an N2 again?
The N2 term comes directly from the core attention calculation. For each of the n-query positions, the mechanism computes a dot product, a compatibility score, with all n-key positions. That's NN equals N2 pairwise comparisons. Multiplying by D accounts for the operations involving the D-dimensional vectors.
Right, but despite that N2 term, its sequential operations are listed as O1, and its maximum path length is also O1. This really seems to be the transformer's magic trick. What's the profound implication of O1 for both of these?
The O1 for sequential operations is revolutionary for sequence processing. It means that all the dot products for the N2 pair, the softmax calculation across all keys for each query, and the final weighted sums to produce the output vectors within a single self-attention layer can, in principle, be computed simultaneously. There's no dependency of step T on step T1 within the layer's core computation. This enables massive parallelization on suitable hardware. And the O1 maximum path length is equally transformative. It means any two positions in the sequence, no matter how far apart, POSI and POSE, are directly connected through a single self-attention operation. Information doesn't have to hop through n steps like in an RNN. This fundamentally resolves the long-range dependency bottleneck that plagued recurrent models.
The paper also makes a nuanced point about complexity in practice. Self-attention layers are faster than recurrent layers when the sequence length n is smaller than the representation dimensionality d. And they add that this condition holds most often with sentence representations used by state-of-the-art models in machine translations, such as word piece and byte pair representations.
Yes, that's an important practical consideration, especially at the time the paper was written. While N2 complexity looks scary for very large N, in many real-world NLP tasks like translation, the sequence length N, after using subword tokenization like word piece or BPE, might be, say, in the low hundreds, while the model dimension D, like DModel 512 or DFF 2048, is often larger. In such common scenarios, N2D, self-attention complexity, can actually be computationally cheaper than ND2, recurrent complexity. So self-attention wasn't just better theoretically for path length, it was often faster in practice for typical NLP sequence lengths.
And they were already thinking ahead about very long sequences for tasks like maybe processing images or long audio, where N could be huge. They suggest that self-attention could be restricted to considering only a neighborhood of size R. This would change the complexity to O, linear in now, but it would increase the path length to O and R. This sounds like a trade-off.
Exactly. It's a very practical trade-off they anticipated. For inputs where N is extremely large, tens or hundreds of thousands like pixels in an image or samples in audio, the N2 complexity becomes computationally infeasible. Restricting attention so each position only attends to our neighbors, a local window, makes the complexity linear in N, which is manageable. However, you lose the magic O1 global path length. Now, information has to propagate through ONR such restricted attention layers to get from one end of the sequence to the other. Becomes more like a convolutional approach in terms of path length, but potentially still more flexible. It was a clear acknowledgement of the scalability challenge and a proposed direction for future work.
Okay, that covers self-attention. Now let's look at the comparisons in Table 1 for recurrent layers. Complexity, sequential operations, ON, maximum path length, ON. This really just perfectly highlights the fundamental bottleneck they were trying to eliminate, doesn't it?
It absolutely does. The D2 factor in complexity comes from the dense matrix multiplications needed to update the hidden state at each time step. For example, HT equals F, WH21 plus UXT, involves DXD weight matrices W and U. The crucial N factor appears everywhere else because these D2 operations must be performed sequentially, N times, for a sequence of length N. The ON sequential operations means you simply cannot parallelize the computation across the sequence length dimension. And the ON path length means information from the start of the sequence has to physically pass through n computational steps to influence the n. This is precisely why learning long-range dependencies was so notoriously difficult for RNNs.
Crystal clear.
And finally, convolutional layers in Table 1. Complexity, or no clean than DT2, or uses the kernel size. Sequential operations, O1, maximum path lengths. O-kernel for contiguous kernels, or O-locane for dilated convolutions.
Right. So CNNs do achieve O1 sequential operations, like self-attention, because the convolutional filters can be applied in parallel across the sequence positions. That's a plus. The complexity involves K kernel size, in sequence length, and D2, from the filter operations mapping D input channels to D output channels. But the key limitation is the path length. A single convolutional layer with a typical small kernel size K, like 3 or 5, doesn't connect distant pops of the sequence. To connect positions I and J that are far apart, information has to pass through multiple stacked layers. For standard contiguous kernels, this requires stacking O layers, leading to a linear path length, though with a better constant factor than RNNs. Dilated convolutions can reduce this path length to O log, which is much better, but still not the O1 achieved by self-attention.
The paper also notes that convolutional layers are generally more expensive than recurrent layers by a factor of K. And it mentions separable convolutions, which can reduce complexity significantly to OKD and D2. But even then, they make a striking point. Even with KK in meaning a kernel as wide as the sequence, their complexity is equal to the combination of a self-attention layer and a point-wise feed-forward layer.
That comparison is very insightful. Separable convolutions are a more efficient way to implement convolutions, reducing the D2 term. But the authors argue that even if you pushed convolutions to their limit to achieve global connectivity by setting the kernel size K equal to the entire sequence length, then the resulting computational complexity ends up being roughly equivalent to what the transformer uses anyway. One self-attention layer, which has ON2, or effectively ONKD of KN, plus one position-wise FFN layer, which has ONDDFF complexity, somewhat analogous to the ND2 term in separable comms. This reinforces their architectural choice. They're saying self-attention combined with an FFN achieves the desirable O1 path length with a computational cost that's competitive with, or even better than, the most efficient convolutional alternatives needed to get similar global reach.
That's a strong argument. Beyond these performance metrics, complexity, parallelism, path length, the paper highlights an important side benefit in section 4.3. Self-attention could yield more interpretable models. And true. They back this up by inspecting attention distributions from their models, showing examples in the appendix. Let's look at figure 3 on page 13. It visualizes attention patterns, showing how the word making strongly attends to more difficult. Even though they're quite far apart in the sentence, it is in this spirit, making the registration or voting process more difficult. What does this visualization really demonstrate?
It's direct visual proof of the model's ability to capture and utilize long-range dependencies. That phrase, making more difficult, forms a key semantic and grammatical unit, even though the words are separated. Figure 3 shows the attention weights emanating from the word making. One specific attention head, highlighted by color, assigns very high weights, very strong attention, specifically to the words more and difficult. This means the model explicitly recognized and focused on this distant relationship when processing the word making. It's tangible evidence that the self-attention mechanism is doing exactly what it's supposed to do, finding relevant context regardless of distance.
Figure 4 on page 14 is equally fascinating. It shows two attention heads apparently involved in anaphora resolution. Specifically, it highlights how the word "it's" attends strongly back to the law in the sentence. The law will never be perfect, but its application should be just. That seems like quite sophisticated linguistic understanding.
Anaphora resolution, figuring out what pronouns like it, he, she, its refer back to, is a classic challenging problem in natural language understanding. Figure 4 isolates the attention patterns from the word its. It shows that two specific attention heads, head 5 and head 6 in layer 5, have very sharp, highly focused attention weights pointing directly back to the phrase, the law. This is a clear demonstration that the model isn't just processing words locally, it's learning complex linguistic phenomena like coreference. And importantly, the attention mechanism provides a transparent window into how it's making that connection. The paper notes the attention is very sharp, indicating high confidence in this link.
It's like seeing the model's reasoning traced out. Figure 5 pushes this further, showing many of the attention heads exhibit behavior that seems related to the structure of the sentence. And crucially, the heads clearly learn to perform different tasks. This really drives home that different representation subspaces idea behind multi-head attention, doesn't it?
Absolutely. This is empirical evidence supporting the motivation for multi-head attention. It's not just one monolithic attention mechanism. Through training, the different heads learn to specialize. One head might become good at tracking verbs and their subjects, another might focus on prepositional phrase attachments, another might look for specific semantic categories, another might handle negation scopes, and so on. This specialization allows the model as a whole to build a much more multifaceted and nuanced understanding of the sentence's syntax and semantics, which ultimately contributes to its strong performance. And this interpretability, being able to peek inside and see what different parts of the model are focusing on, is incredibly valuable. It helps with debugging when things go wrong, it builds trust in the model's outputs, and it even advances our scientific understanding of how these complex systems learn language.
So it's not just efficient and powerful, but it also offers this potential window into its own thought process. Fascinating. Okay, let's move on to how they actually brought this powerful architecture to life. Training, section 5, starting on page 7. The paper details the training data and batching. For the English to German task, they used the standard WMT 2014 English-German dataset, which had about 4.5 million sentence pairs. And for encoding the text, they used byte pair encoding, BPE, resulting in a shared source target vocabulary of about 37,000 tokens. Can you remind us what BPE is and why you use a shared vocabulary?
Sure. Byte pair encoding, or BPE, is a common subword tokenization technique. Instead of treating whole words as the basic units, BPE learns to break words down into frequently occurring sequences of characters or bytes. For example, a word like unbelievably might be broken into un plus believe plus ably. This has several advantages. It handles rare or unknown words much more gracefully. It can represent them as combinations of known subwords, and it keeps the overall vocabulary size manageable compared to using every single word. A shared source target vocabulary means they use the exact same set of 37,000 subword tokens for both the input English sentences and the output German sentences. This is efficient and particularly useful for translation, as many subwords like names, numbers, or related concepts appear in both languages.
Okay. And for the English to French task, the dataset was significantly larger, 36 million sentences, and they used a 32,000 word piece vocabulary, which is another subword method similar to BPE. A key part of their training efficiency was the batching strategy. Sentence pairs were batched together by approximate sequence length. Why is grouping by approximate sequence length so important for efficient training on GPUs?
It's a really critical optimization for maximizing GPU utilization. When you train neural networks, you typically feed them data in batches. If you have sentences of very different lengths within the same batch, you have to add special padding tokens to the shorter sentences to make them all the same length as the longest sentence in that batch, because GPUs work best with rectangular data. All the computation done on those padding tokens is essentially wasted work. By grouping sentences that have roughly similar lengths together into batches, you minimize the amount of padding needed for each batch. This means the GPU spends almost all its time doing useful computations on actual data, making the training process much more efficient.
And the batch size itself was massive. Each training batch contained a set of sentence pairs containing approximately 25,000 source tokens and 25,000 target tokens. That's huge.
It is huge. That large batch size is specifically designed to saturate the parallel processing capabilities of the GPUs they were using. More data processed in parallel per step generally leads to faster overall training, assuming you have the hardware to handle it.
Speaking of hardware, let's look at hardware and schedule. They trained on one machine with 8 NVIDIA P100 GPUs. These were serious deep learning GPUs for their time, right? High memory bandwidth, good floating point performance.
Absolutely. The P100 was a powerhouse, specifically designed for the kind of large matrix multiplications that dominate deep learning. Having 8 of them working together provided substantial computational power, and the training times they reported were remarkable. For their base models, each training step took about 0.4 seconds. They ran for 100,000 steps, which adds up to just 12 hours of total training time. The big models took a bit longer per step, 1.0 seconds, and ran for 300,000 steps, totaling 3.5 days. These numbers, especially the 12 hours for a state-of-the-art base model, were revolutionary compared to the weeks or months needed previously. It underscored the efficiency gains from the architecture.
Incredible speed up. Now, for the optimization process itself, section 5.3, they use the atom optimizer, a very popular choice. They specify the hyperparameters, order 2 equals by 98 and OIL 9. These control Atom's behavior, like how it adapts learning rates using momentum and path gradients. But the learning rate schedule they use is really interesting and became highly influential. The paper gives the formula. We varied the learning rate over the course of training according to the formula.
yield rate 8 bottle 0.5, min step num max 0.5, step num warm-up steps 1.5. This is equation 3, less complex. Let's break this down piece by piece. What's controlling the learning rate here?
Okay, this learning rate schedule is a really key ingredient for successfully training large transformer models. Let's dissect it. First, notice the D model dash 0.5 term multiplying everything. That's 1 square-tat gindo. For D model 512, it's 1 square-tat 512. This is a constant scaling factor that makes the overall learning rate dependent on the model's size. It helps keep things appropriately scaled. Now, the core logic is inside the min function. It compares two terms and picks the smaller one at each training stepnum. The behavior depends heavily on warm-up steps, which they set to 4,000.
Okay, so it's choosing between stepnum 0.5 and stepnum warm-up steps 1.5. What do those two terms represent?
Let's look at them individually. 1 stepnum dash 0.5. This is simply 1 squared stepnum. As the training stepnum increases, this term decreases. This represents an inverse square root decay of the learning rate. Decay is common later in training to allow for finer adjustments. 2, stepnum warm-up steps 1.5. Here, warm-up steps 1.5 is just a fixed constant since warm-up steps is fixed at 4,000. So this entire term is just stepnum multiplied by a small constant. This represents a linear increase phase. The learning rate grows linearly with the step number.
So we have a linear increase term and a decay term. How does the min function make them work together to create the schedule?
It creates two distinct phases. Phase 1, first warm-up steps equals 4,000 steps. For stepnum, from 1 to 4,000, the linear increase term, stepnum constant, starts very small and grows. It will be smaller than the decay term, 1 squared stepnum, which starts large and decreases. So the min function picks the linear increase term. This means the learning rate increases linearly from effectively 0 at step 1 up to its peak value at step 4,000.
Why start low and increase? What's the point of this warm-up?
The warm-up is crucial for stability, especially at the very beginning of training when the model weights are randomly initialized and far from optimal. If you started with a large learning rate immediately, the initial gradient updates could be huge and erratic, potentially causing the training to diverge or oscillate wildly. A gradual warm-up allows the model parameters to settle down and move into a more reasonable region of the loss landscape before you hit them with the full learning rate. It prevents early instability. Phase 2. Decay after warm-up steps equals 4,000 steps. Once stepnum exceeds 4,000, the decay term, 1 squared stepnum, continues to decrease and eventually becomes smaller than the linear term, which would keep growing if chosen. So after step 4,000, the min function switches to picking the stepnum 0.5 term. This means the learning rate now decreases for the rest of training, following that inverse square root curve.
And why the decay after the peak?
As training progresses and the model gets closer to a good solution, a minimum in the loss function, you typically want to take smaller steps. A high learning rate might cause the model to overshoot the minimum or bounce around it. Gradually decreasing the learning rate allows for finer, more precise adjustments to the weights, helping the model converge more smoothly and settle into a better final solution. The specific schedule linear warm-up followed by inverse square root decay proved highly effective and has become a standard recipe for training transformers.
That's a fantastic detailed breakdown. It makes perfect sense why you'd want both phases.
Yeah.
Okay, finally for training, let's look at regularization in section 5.4, how they prevented overfitting. They used two main techniques. First, residual dropout. They applied dropout to the output of each sublayer before it is added to the sublayer input and normalized, and also to the sums of the embeddings and the positional encodings at the input. The rate for the base model was p drop equals 0.1. Remind us what dropout is and why it's such an effective regularizer.
Dropout is a surprisingly simple yet powerful technique. During each training step, it randomly drops out, meaning it temporarily sets to 0 a certain fraction p-drop of the neuron outputs in a given layer. Here, they apply it to the output of the sublayer x before the residual connection adds x. They also apply it right at the input, after summing embeddings and positional encodings. The reason this works is that it prevents neurons from becoming too reliant on any specific other neurons. Since any neuron's output might randomly disappear on the next step, the network is forced to learn more robust and redundant representations. It can't put all its eggs in one basket, so to speak. It's often thought of as implicitly training a large ensemble of many different thin networks, subsets of the full network, that share weights. This averaging effect leads to better generalization on unseen data.
Makes the network more robust by randomly removing parts during training. Clever. The second technique is label smoothing, with a value ols equals 0.1. The paper makes an interesting observation. This hurts perplexity as the model learns to be more unsure, but improves accuracy in BLEU score. Can you unpack that?
God.
Why would something that makes the model more unsure and hurts perplexity actually lead to better final scores like BLEU?
It seems counterintuitive at first, right? Perplexity measures how confident a model is in its predictions. Lower perplexity generally means higher confidence. Standard training uses hard labels. The correct word gets a target probability of 1.0, and all incorrect words get 0.0. Label smoothing modifies this. Instead of 1.0 for the correct label, it uses 1.0 ols, so zero point 0.9 in this case, and it distributes the remaining ols 0.1 probability mass uniformly across all the incorrect labels in the vocabulary. This means the model is explicitly discouraged from becoming overly confident, even on the correct answer. It's penalized if its output probability for the correct word gets too close to 1.0.
So it's basically telling the model, don't be too sure.
Exactly. It forces the model to maintain a bit of uncertainty. While this slightly smears the probability distribution and makes the model less sharply peaked on the correct answer, hence higher perplexity, it has a crucial benefit. It prevents the model from overfitting to the training data, especially if there's noise or ambiguity in the labels. By being less confident and assigning a tiny bit of probability to incorrect answers, the model becomes more robust and generalizes better to unseen data, leading to improved accuracy and BLEU scores in the end. It's a way to regularize the model's confidence.
That's a great explanation, a trade-off between confidence during training and robustness during testing. Okay, now let's get to the payoff. Results, Section 6. This is where all these architectural and training choices demonstrate their impact. Starting with machine translation, Section 6.1, on WMT 2014 English to German, the results were stunning. The big transformer model outperforms the best previously reported models, including ensembles, by more than 2.0 BLEU, establishing a new state-of-the-art BLEU score of 28.4. And this was achieved, as we heard, in just 3.5 days on 8 P100 GPUs.
This was the headline result that really turned heads. That 28.4 BLEU score wasn't just a small increment. It was a significant jump over the previous best, including those computationally expensive ensembles. Remember, ensembles usually define the ceiling of performance. For a single model to surpass them, and to do so with dramatically less training time, as shown in Table 2 later, was a monumental achievement. It signaled a real changing of the guard. And even their base model, the one trained in only 12 hours, surpassed all previously published single models and ensembles. That really hammered home the efficiency and power of the transformer architecture.
And the success wasn't limited to English-German. For WMT 2014 English to French, our big model achieves a BLEU score of 41.8, outperforming all of the previously published single models at less than 14 the training costs of the previous state-of-the-art model. They do note a minor parameter tweak for this task. Dropout rate p-drop equals 0.1 for ENFR instead of the 0.3 typically used for the big model elsewhere.
Right. Small hyperparameter adjustments are common when tuning for specific datasets or language pairs. The key takeaway, though, is the consistent pattern. State-of-the-art or near state-of-the-art results across different translation tasks, achieved with significantly reduced training costs compared to the competition. This demonstrated the transformer wasn't a one-trick pony. It was broadly applicable and highly effective.
Now, when they actually used the trained models for generating translations, inference, they employed a couple of techniques. First, model averaging.
Yeah.
For the base models, we used a single model obtained by averaging the last 5 checkpoints. For the big models, we averaged the last 20 checkpoints. Why average multiple checkpoints? What benefit does that provide?
Model averaging is a simple but effective technique, essentially a form of ensembling applied to checkpoints from a single training run. As a model trains, its performance can fluctuate slightly towards the end, and it might land in slightly different local minima at different checkpoints, which are just snapshots of the model's weights saved periodically. By averaging the weights of several recent checkpoints, the last 5 or 20, you tend to smooth out these fluctuations and create a model that's more robust and often generalizes slightly better than any single checkpoint would on its own. It reduces the variance associated with picking just one specific point in the training trajectory.
Okay, averaging smooths things out. They also used beam search with a beam size of 4 and length penalty equals 0.6. What exactly is beam search in sequence generation, and why the length penalty?
Beam search is a common decoding algorithm used to find a high probability output sequence, like a translation. A simple approach called greedy decoding just picks the single most probable word at each step. But this can lead you down a path that seems good locally but ends up being globally suboptimal. Beam search is less greedy. At each step of generating the sequence, it keeps track of the beam size, here 4, most probable partial sequences generated so far. Then, for the next step, it considers all possible next words for each of those 4 hypotheses, calculates their probabilities, and again keeps only the top 4 overall best sequences. It explores a limited beam of possibilities instead of just one. This usually finds much better overall sequences than greedy search. The length penalty is a heuristic used to counteract a common bias in sequence models. Models often prefer shorter sequences because multiplying probabilities together naturally favors fewer terms. The length penalty adjusts the scores to slightly favor longer, more complete hypotheses, preventing overly short or truncated outputs.
Got it. Beam search explores more options. Length penalty avoids overly short outputs. Now, Table 2 in the paper is where they really lay out the results quantitatively. It summarizes our results and compares our translation quality and training costs to other model architectures. They meticulously estimated the training costs using floating point operations, FLOPs, calculated from training time, number of GPUs, and GPU capacity. FLOPs provide a standardized measure of computational work.
Exactly. They used estimates like 9.5 TFLOPS per P100 GPU, footnote 5. This allows for a more apples-to-apples comparison of computational cost than just reporting training time, which depends heavily on specific hardware. And the comparisons in Table 2 are dramatic. Let's pick one. Transformer, big for English to German, achieved that 28.4 BLEU score using an estimated 2.3E one-time FLOPs. Now compare that to a major competitor at the time, the GNMT plus RL Ensemble. It only reached 26.30 BLEU, over 2 points worse. It required a massive 1.8 E2U FLOPs. That's almost 10 times more computational cost for significantly lower quality. Table 2 is filled with examples like this, clearly demonstrating the Transformer's huge leap in both efficiency and effectiveness. It was really a mic drop moment for sequence modeling.
That table truly tells a powerful story. Okay, let's turn to section 6.2, model variations. This is where they dissected the architecture's impact by systematically tweaking components of their base model and measuring performance changes. Let's look at Table 3, which shows results on the English to German development set. In rows A, they varied the number of attention heads, H, and the dimensions per head, DK, keeping the total D model constant. The observation: while single-head attention is 0.9 BLEU, worse than the best setting, quality also drops off with too many heads. What's the key takeaway here about multi-head attention?
This is a really important finding. It shows that multi-head attention isn't just about parallel computation. The number of heads and their individual dimensions significantly impact performance. Using just a single head was clearly suboptimal, suggesting that capturing diverse relationships through different heads is beneficial. However, simply increasing the number of heads indefinitely wasn't the answer either. Using too many heads, like 16 in their test, also hurt performance. This suggests there's an optimal balance. Maybe with too many heads, each head has too few dimensions, DK becomes too small, to learn effectively, or perhaps the optimization becomes harder. It implies that finding the right number and size of heads is crucial, not just maximizing the count.
Interesting. In rows B, they specifically reduced the attention key size DK while keeping other things constant. The result, reducing the attention key size DK hurts model quality. The paper then speculates. This suggests that determining compatibility is not easy, and that a more sophisticated compatibility function than dot product may be beneficial. That's a fascinating self-critique, or future direction hint.
It really is. It implies that the DK dimensional key and query vectors need sufficient capacity, sufficient richness to accurately capture the complex notion of compatibility or relevance between different sequence positions using just a simple dot product. If DK is too small, the vectors are too compressed, and the dot product might not be expressive enough to distinguish subtle differences in relevance. While the scale dot product was incredibly successful and efficient, this result opens the door to thinking about whether more complex functions for comparing keys and queries could potentially yield even better results, though likely at a higher computational cost.
Makes sense. Rows C and D look at overall model size by varying D model in the feed-forward interdimension DFF and the impact of dropout, P-drop. The observations are pretty consistent with general deep learning wisdom. Bigger models are better, and dropout is very helpful in avoiding overfitting. Increasing D model and DF improves BLEU, and turning off dropout, P-drop, significantly harms it.
Yes, this confirms standard practices. Larger models generally have more capacity to learn complex patterns from large data sets, leading to better performance, up to a point, of course. And dropout is clearly shown to be essential. Row D shows the base model with p-drop 0.1 gets 25.8 BLEU, but with p-drop 0.0, no dropout, it drops to 24.6 BLEU. That's a huge difference, highlighting dropout's critical role in preventing overfitting in these high-capacity models and ensuring they generalize well.
And finally, row E revisits positional encodings. They replace our sinusoidal positional encoding with learned positional embeddings and observe nearly identical results to the base model. This is interesting, given their strong theoretical argument for choosing the sinusoidal version earlier.
It is interesting. Empirically, on the tasks and sequence lengths they tested, the learned positional embeddings performed just as well as the fixed sinusoidal ones. However, as we discussed, the reason for initially choosing the sinusoidal version, its theoretical ability to extrapolate to sequence lengths never seen during training still holds. So while the performance was similar in these experiments, the sinusoidal choice offered a potential robustness advantage for handling arbitrarily long sequences in the future, which might not have been fully tested by the datasets used here. It was a design choice with longer-term generalization in mind.
Okay, that wraps up the translation experiments. But they didn't stop there. Section 6.3 shows them applying the transformer to a different, structurally complex task, English constituency parsing. Can you briefly explain what constituency parsing involves?
Sure. Constituency parsing aims to break down a sentence into its grammatical constituents, phrases like noun phrases, NP, verb phrases, VP, prepositional phrases, PP, etc., and show how they are hierarchically nested together to form the complete sentence structure. The output is typically represented as a tree diagram showing these relationships. It's about understanding the underlying syntax of the sentence.
This task seems quite different from translation. The paper notes challenge is like, the output is subject to strong structural constraints. It has to be a valid tree, and it's often significantly longer than the input. The tree representation uses many more tokens than the original sentence. And crucially, they mention the previous RNN sequence-to-sequence models have not been able to attain state-of-the-art results in small data regimes for this task.
Right. These points highlight why parsing is a good test of a model's architectural capabilities beyond simple sequence-to-sequence mapping. It requires understanding complex grammar rules and generating highly structured, often lengthy output. The fact that prior RNN-based sequence models struggled, especially when training data was limited, makes the transformer's performance here a significant benchmark.
So their experimental setup involved a 4-layer transformer with D model equals 1024. Note, slightly different config from the base translation model. They trained it in 2 settings. 1, WSJ only, using just the Wall Street Journal section of the Penn Tree Bank, which is only about 40,000 training sentences. This represents the challenging small data regime. 2, semi-supervised, using a much larger data set of about 17 million sentences. And importantly, they mentioned doing only a small number of experiments to select the dropout, learning rates, and beam size. All other parameters remained unchanged from the English to German-based translation model, so minimal task-specific tuning.
That minimal tuning point is important. It suggests the core transformer architecture itself is quite adaptable and doesn't require extensive modifications to work well on a significantly different task structure like parsing.
Table 4 shows the results. The paper states, despite the lack of task-specific tuning, our model performed surprisingly well, yielding better results than all previously reported models, with the exception of the recurrent neural network grammar, which was a highly specialized parsing model. Looking at the F1 scores, the transformer achieved 91.3 on the WSJ-only set, beating several prior benchmarks.
Yes, and the crucial comparison they emphasize is this. In contrast to RNN sequence-to-sequence models, the transformer outperforms the Berkeley parser, a strong traditional parser, even when training only on the WSJ training set of 40K sentences.
Why is that specific comparison so significant?
It's significant because it directly addresses the weakness of previous RNN sequence-to-sequence approaches on this task, particularly in the low data setting. It demonstrates that the transformer architecture is remarkably data efficient for learning complex syntactic structures. Its self-attention mechanism seems better suited to capturing the kinds of hierarchical and long-range dependencies needed for parsing, even without massive amounts of training data. This further cemented the idea that the transformer was a versatile and powerful new building block for NLP.
It really showcases the generalization power. Okay, let's bring this deep dive to a close by looking at the conclusion, Section 7.
They start by summarizing their achievement. We presented the transformer, the first sequence transduction model based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architectures with multi-headed self-attention, a concise restatement of their core contribution.
And they reiterate the key benefits demonstrated. It trains significantly faster than architectures based on recurrent or convolutional layers, and achieved a new state-of-the-art on both major WMT translation tasks, even beating costly ensembles.
Looking forward, the authors stated they were excited about the future of attention-based models and plan to apply them to other tasks. That certainly turned out to be quite an understatement. Transformers are now ubiquitous. They also explicitly mentioned plans to extend the transformer to problems involving input and output modalities other than text, such as images, audio, and video. This prediction also clearly came true, with models like vision transformers, VITs, becoming dominant in computer vision shortly after.
They also acknowledged the scalability challenge we discussed.
Right.
To investigate local, restricted attention mechanisms to efficiently handle large inputs and outputs such as images, audio, and video. This shows they were aware of the O(n)2 limitation for extremely long sequences. And another future goal was making generation less sequential, hinting at research towards more parallelizable decoding methods beyond this standard autoregressive approach.
Yes, and very importantly for the research community, they concluded by stating, "The code we use to train and evaluate our models is available at https://github.com/TensorFlow-Tensor2Tensor." This commitment to open sourcing their code was absolutely critical. It allowed researchers worldwide to immediately start using, adapting, and building upon the transformer architecture, massively accelerating progress in the field.
Absolutely. Open science in action. And a final quick mention for the acknowledgments, thanking Nal Kelchbrenner and Steven Gauss for fruitful comments, corrections, and inspiration. A nice reminder that science is collaborative.
Indeed. Groundbreaking work rarely happens in complete isolation.
So there we have it. We've journeyed deep into the intricate details of attention is all you need. From its, frankly, radical decision to throw out recurrence entirely, to the elegant mathematics behind scaled dot product and multi-head attention, and the clever way positional encodings bring back sequence order. You should now have a much clearer understanding of how this single paper, which might have seemed like just a technical abstract before, truly redefined what was possible in artificial intelligence.
That's right. The transformer isn't just some historical research paper anymore. It's the invisible engine driving so much of the advanced AI we interact with constantly. From chatbots to translation tools, its principles are at work. Understanding these foundations, we hope, moves you beyond just being a user to being someone who's genuinely informed about the cutting edge of how these powerful technologies actually function.
So as we wrap up, here's a provocative thought for you to consider. If simply rethinking a core architectural assumption like recurrence and deciding to dispense with it entirely could lead to such a monumental leap forward, what other fundamental assumptions in our current AI models might just be waiting to be challenged? What seemingly fixed parts of today's best models could be the next recurrence, the next component that gets thrown out, leading to the next unpredictable paradigm shift in AI?
It's a fascinating question. We really encourage you, if you're interested, to seek out the original paper, look at the diagrams, maybe even skim the code if you're adventurous. The beauty of this work isn't just in the impressive results, but in the elegant simplicity and the profound, lasting impact of its core ideas.
Welcome back to The Deep Dive, the show where we take a stack of sources, articles, and research and distill them into the most important nuggets of knowledge, all custom-tailored for you, our curious listener.
Hey, everyone.
Today, we're not just diving deep. We're plunging into the very bedrock of modern AI.
That's right.
Imagine a world where machines struggle to truly understand the nuances of human language, where every sentence felt like a maze, and then suddenly, a single, audacious idea changed everything.
Indeed. We're talking about a moment, a paper that quite literally sparked a paradigm shift. It's the story of how a team dared to defy conventional wisdom, to strip away what everyone thought was essential, and in doing so, achieved state-of-the-art results that still echo through every AI application you use today.
Exactly. Our deep dive today is into that groundbreaking paper, Attention is All You Need. For years, the world of language processing was dominated by complex architectures. Recurrent neural networks, or RNNs, like LSTMs, and later even convolutional neural networks, or CNNs.
Right, those were the big players.
These were the champions of understanding sequences, especially in critical areas like machine translation. And if you look closely at the best of them, you'd often find something called an attention mechanism added on, almost like a secret sauce.
That's right. Attention was, for a long time, an add-on, a supplementary component, a little extra sprinkle of magic to boost performance.
But then came the truly revolutionary claim of the transformer model, as proposed in this paper. It completely dispensed with both recurrence and convolutions.
Yeah, just threw them out.
It decided to rely solely on attention mechanisms. Imagine trying to build a highly complex machine, But instead of adding more parts, you make it incredibly powerful and effective by removing what everyone thought were essential pieces.
It's a genuine aha moment in AI, a moment of brilliant simplification. It sounds counterintuitive, right? Removing parts to make it better.
Totally. So why does this matter to you, our listener? Why should you care about this foundational deep dive?
Well, the immediate impact was nothing short of striking. It delivered superior quality in machine translation, achieving state-of-the-art results that just left previous models in the dust.
Okay, better results, but what else?
Beyond sheer quality, this architecture also unlocked something truly valuable. Significantly more parallelizable training.
Ah, okay. And what does that mean?
Much, much faster model development. Less waiting around.
Right. Speed is always good.
And its impact wasn't confined just to translation. The paper also demonstrated the transformer's surprising generalizability to other complex tasks, such as constituency parsing, which is all about understanding the grammatical structure of sentences.
So faster, better, and more versatile AI models.
Exactly. And that translates directly into more accurate translations you use every day, more nuanced language understanding in your chatbots, and a whole new frontier of applications we're only just beginning to explore.
So diving into this paper isn't just theory, it's kind of a shortcut to understanding a fundamental building block of modern AI.
It really explains why so many of the advanced systems we now rely on function the way they do. It's foundational.
Before we unpack the genius within, let's take a moment to acknowledge the brilliant minds behind this monumental work. This was a truly collaborative effort, with 8 authors from Google Brain, Google Research, and the University of Toronto.
Yeah, it's quite a list.
The paper itself explicitly states equal contribution, which is, a testament to their incredible teamwork. But it's worth highlighting some of the specific foundational contributions that brought this vision to life.
Absolutely.
Jacob Hochreiter, for instance, had this radical initial proposal to replace RNNs entirely with self-attention, and he really spearheaded the effort to evaluate that audacious idea.
That took some guts, I imagine, just saying, let's ditch RNNs.
Right. And then there's Noam Shazir, who brought forth the brilliant concepts of scaled dot product attention and multi-head attention components we'll definitely get into in detail, and even the clever parameter-free position representation.
His involvement was crucial, really, in nearly every fine-grained detail of the architecture. He was deep in the weeds.
And Ashish Vaswani and Ilya Polosukhin were absolutely instrumental in designing and implementing the very first transformer models, deeply involved in every aspect, from the initial conceptual design to the practical implementation.
Building the thing from scratch, basically.
Yeah. And Nikki Parmar, who meticulously designed, implemented, tuned, and evaluated countless model variants in their original code base, really refining the architecture.
That iterative process is so key. Trying things out, seeing what sticks.
Lee and Jones contributed significantly to novel model variants, setting up the initial codebase and ensuring efficient inference and visualizations.
Making it work in practice and helping others see how it works.
And finally, Ukaz Kaiser and Aidan N. Gomez spent countless hours designing and implementing the Tensor2 tensor library.
Ah, Tensor, yeah, that was huge.
This library ultimately replaced their earlier codebase and dramatically improved results, massively accelerating their research and making the transformer accessible to the broader research community.
It really democratized it in a way, opened the doors. It's truly a testament to the power of collaborative scientific discovery.
Okay, let's unpack this innovation by first understanding the world it disrupted. To truly appreciate the transformer, we need to set the stage by looking at the landscape before its arrival.
Right. Context is everything.
For a long time, recurrent neural networks, or RNNs, and specifically their more sophisticated cousins like long short-term memory networks, LSTMs, and gated recurrent units, GRUs, were the undisputed champions for sequence modeling tasks, especially language translation.
They were the go-to, absolutely.
What made them so popular, so dominant for so long?
Well, their popularity stemmed from their inherent design, which, seemed to perfectly mirror the sequential nature of language.
How so?
RNNs process sequences one symbol at a time. Think of it like reading a book word by word, truly absorbing each word before moving to the next.
Okay, step by step.
Exactly. At each step, say, for the teeth word, the model generates a hidden state. Let's call it HT. This HT is a function of the previous hidden state, HT1, and the current input, XDA.
So it always knows what came just before.
Precisely. This unique architecture allows them to build a representation that incorporates context from earlier in the sequence, modeling dependencies across different positions. It's an elegant way to capture how words relate to each other as they unfold in a sentence.
That makes intuitive sense. If you're building meaning from a sentence, you constantly refer back to what came before. But it sounds like there was a hidden cost to this elegance. What was the catch?
The catch, ironically, was precisely that inherent sequential nature. While excellent for modeling dependencies, it became their Achilles heel, especially as sequence lengths grew.
How?
This step-by-step computation, where HE must be computed after HT1, fundamentally precludes parallelization within a single training example.
Ah, okay. So you mean if I have one very long sentence like a complex legal document or a detailed medical report, I can't process different parts of it simultaneously on a powerful modern GPU?
Exactly. It's always one step after another, like dominoes falling.
Can you give an analogy?
Sure. Imagine trying to build a really, really tall Lego tower. You can only place one brick at a time, and the placement of the current brick always depends on the stability and position of the brick directly below it.
Right.
You simply cannot have multiple people building different parts of the same tower simultaneously. You could have multiple people building different towers, but that single really tall tower is always a single person sequential job.
And what's the consequence of that for training these large neural networks that demand massive data sets and complex sentences?
This becomes a major bottleneck for longer sequence lengths. When even the length of the sequence grows, both the time it takes to process and the memory required become significant constraints. It just gets slower and needs more memory.
Were people trying to fix this?
Oh yeah. The paper points out that previous efforts tried to mitigate this using clever tricks like characterization or conditional computation. While these methods improved efficiency and sometimes even model performance,
Right.
they fundamentally did not remove that sequential constraint. The core problem, the inability to truly parallelize the processing of a single long sentence, remained. It was a ceiling on what RNNs could achieve efficiently.
So the ambition to build truly scalable and efficient language models was hitting a fundamental wall. Researchers knew they need a breakthrough beyond just tweaking the old methods. And that's when a fascinating concept, attention, which had been lurking in the background, started to gain traction. What did these early attention mechanisms bring to the table?
Attention mechanisms were a significant conceptual step forward. They introduced a way for models to model dependencies without explicit regard to their distance in the input or output sequences.
Okay, so distance didn't matter as much.
Right. Instead of just relying on the immediate past, attention offered a mechanism for the model to look back at any point in the sequence and decide which parts were most relevant for the current prediction.
So it's like instantly highlighting the most important words in a sentence, no matter where they are, rather than having to remember a long string of previous words.
Precisely. Imagine you're reading a very long and complex contract. Instead of having to meticulously remember every clause in order, attention allows you to instantly highlight and focus on the most relevant clauses or phrases when you're trying to understand a specific term, regardless of how far apart they are.
That makes sense, like finding the subject of a verb way earlier in the sentence.
Exactly. For instance, if you're trying to translate a verb, attention could help the model focus directly on its subject, even if that subject appeared much earlier, bridging what would be a long path in an RNN.
But these are still used with RNNs, mostly.
Crucially, yes. The paper notes that most existing attention mechanisms, with very few exceptions, were still used in conjunction with a recurrent network. They were powerful enhancements, but not replacements. They augmented the existing sequential processing. They weren't the whole story.
And this is where the transformer makes its audacious, truly revolutionary move. The paper states, "We propose the transformer, a model architecture eschewing recurrence and instead relying entirely on an attention mechanism."
That's the money quote right there, eschewing recurrence.
What does eschewing recurrence truly mean for the model's fundamental philosophy and design? How radical is that?
It truly was a complete philosophical shift. It meant breaking free from that step-by-step sequential processing that defined RNNs. The fundamental goal was to fully embrace parallel computation from the ground up.
So design for parallelism from the start.
Exactly. Design a model where every part of the input sequence could be processed simultaneously without waiting for the previous part to finish.
Were others trying similar things?
Oh, well, prior work, such as the extended neural GPU, ByteNet, and ConvS2S, had also aimed at reducing sequential computation, often by using convolutional neural networks, CNNs, as their building blocks.
But convolutions still have a kind of local window, right? Like looking at a word and only its immediate neighbors. How does that compare to what the transformer does, especially for long-range dependencies?
You're absolutely right. With CNNs, the number of operations required to relate signals from two arbitrary input or output positions still grows with the distance between them.
So it's still harder to connect far apart words.
Yes. For a standard convolutional network like ConvS2S, it's a linear growth. For ByteNet, which use dilated convolutions, it's logarithmic. This means that even with CNNs, it's harder to learn direct dependencies between very distant positions because the information has to propagate through multiple layers, increasing the path length.
And the transformer.
The transformer, however, with its reliance on self-attention, radically reduces this to a constant number of operations, an O1 relationship.
Wow.
Yeah. This means any two positions in a sequence, no matter how far apart, are connected directly in a single step, making it inherently superior for capturing long-range context.
That's a massive, massive difference. So it's not just about getting rid of recurrence, but also about addressing the limitations of convolutions for those crucial long-range dependencies.
Precisely.
And the mechanism it uses for this direct, instant connection is self-attention.
Precisely. Self-attention, sometimes also called intra-attention, is the engine of the transformer. This is an attention mechanism specifically designed to relate different positions of a single sequence to compute a richer contextualized representation of that same sequence.
Can you give an example?
Sure. Think about processing the word "it" in a sentence like, "The cat sat on the mat, it was fluffy." Self-attention allows the model to instantly connect it back to cat, capturing that critical relationship directly.
Ah, okay. And this had been used before.
Yes, this mechanism had seen prior successes in tasks like reading comprehension, abstractive summarization, and learning general sentence representations, but not as the sole component like this.
And the paper makes a very strong, almost defiant claim about its innovation, stating the transformer is the first transduction model relying entirely on self-attention to compute representations of its input and output without using sequence-aligned RNNs or convolution.
It is a very bold claim.
That's a significant statement that truly frames the scale of their innovation and their confidence in this new path.
It unequivocally positions their work not just as an improvement, but as a genuine paradigm shift in architectural design for sequence transduction, asserting that attention alone is sufficient and even superior.
Okay, let's move into the core architecture of the transformer itself. The paper says it follows the typical encoder-decoder structure. Could you walk us through that high-level blueprint first, that overarching design philosophy, before we dive into the nitty-gritty of its individual parts?
Certainly. At a high level, the encoder-decoder structure is a standard, tried-and-true framework for sequence-to-sequence problems, like machine translation. It's essentially a two-stage process.
Okay, stage one.
First, you have the encoder. Its fundamental role is to take an input sequence of symbols, for instance, an English sentence like by 1, by 2, xn.
Got it, the source sentence.
Right. It then maps this entire sequence into a sequence of continuous abstract representations. Let's call it Z, Z1, Z2, SEZ in it.
What is Z?
Think of Z as an enriched, context-aware understanding of the entire input sentence. It captures the meaning and relationships of the input words in a dense numerical form, ready for translation.
Okay, so the encoder reads the input and creates this rich understanding. What's stage two?
Second, you have the decoder. Given this Z representation, this rich encoded understanding from the encoder, the decoder's job is to generate the output sequence of symbols. For example, a German translation, Y1, Y2, IM.
And how does it generate that?
It generates this output one element at a time. This brings in the autoregressive property of the decoder.
Autoregressive.
Yeah, it means at each step, when it predicts the next symbol, say yi, it actively consumes the previously generated symbols, Y1 through Y1, as additional input, alongside the encoder's output Z.
So the decoder is essentially translating word by word, continually building on what it's already translated, and always referring back to that comprehensive understanding of the original source sentence that the encoder provides.
Exactly. And if you visualize Figure 1 in the paper, it clearly lays out this overall architecture with the encoder half on the left and the decoder half on the right.
And the transformer uses attention for both.
Yes. The genius of the transformer is how it leverages stacked self-attention and pointwise, fully connected layers for both of these roles, forming a powerful parallel processing pipeline.
Okay, let's get into the specifics of these stack layers that make up the transformer. What makes up a single encoder layer? The paper mentions any 6 identical layers are stacked on top of each other.
Right. Each of these N6 identical encoder layers is composed of 2 primary sublayers, each doing a distinct but complementary job.
What's the first one?
The first sublayer is where the magic of attention truly begins in the encoder. It's a multi-head self-attention mechanism. We'll dive deep into multi-head attention shortly, but for now, understand that this is where the encoder allows each word in the input sentence to pay attention to and thus draw context from every other word in that same sentence.
So every word looks at every other word.
In essence, yes. This way, the representation of each word becomes richer, informed by its entire linguistic neighborhood, regardless of distance.
Okay, that's sublayer 1. What's the second?
The second sublayer is a simple yet powerful, position-wise, fully connected feed-forward network. This is essentially a small, standard neural network that processes each position's representation completely independently but identically across the entire sequence.
Like applying the same process to each word's representation.
Exactly. It's like applying the same analytical lens to every single word's context-rich representation after it's gone through self-attention.
So 2 main components within each encoder layer. But the paper also mentions some crucial additions like residual connections and layer normalization wrapped around each sublayer. What are those and why are they so important for training a deep network like this?
These are absolutely vital for successfully training any very deep neural network. Let's take them one by one.
Okay, first, residual connections.
First, residual connections. The paper defines the output of each sublayer as layer norm x plus sublayer x. Let's break that down.
All right.
X here is the input to the sublayer. Sublayer X is the output of that specific attention or feed-forward operation. The X plus sublayer X part means that the original input X is added directly to the output of the sublayer.
Like a shortcut.
Exactly. This technique, often called a skip connection, creates a direct pathway for information to flow through the network. This is crucial during backpropagation, helping with gradient flow by allowing gradients to bypass layers, preventing them from vanishing or becoming too small, which is a common and debilitating problem in very deep networks. It essentially ensures information doesn't get lost or diluted.
Makes sense. And the second addition, layer normalization.
Second, layer normalization. After adding the residual connection, the result is normalized. Layer normalization is distinct from batch normalization, which is more common in computer vision.
Why use layer norm here?
In natural language processing, where sequences can have variable lengths, layer normalization is generally preferred because it normalizes across the features of each individual example rather than across a batch. This helps stabilize the activations, ensuring they remain in a healthy range, which in turn speeds up and stabilizes training.
Okay, and how do these residual connections actually work? Don't the dimensions need to match?
Good point. And that's why, to make these residual connections work seamlessly, all sublayers in the model, as well as the initial embedding layers, produce outputs of a consistent dimension. This is what they define as D model 5-to-1.
D model, that's the key dimension.
Yes. This D model is the embedding dimension or the representation dimension, meaning every vector representation throughout the network, whether it's an initial word embedding or the output of a deep sublayer, will consistently have 512 dimensions. This consistency is crucial for the residual connections because it ensures that the input X and the sublayer X output have compatible shapes for direct addition.
That clarifies the encoder layer. Now let's turn to the decoder. It sounds a bit more intricate, adding a critical third sublayer. What's the structure of a single decoder layer?
Yes, the decoder is also composed of N6 identical layers, stacked just like in the encoder. Each decoder layer starts with the same 2 sublayers found in the encoder: a multi-head self-attention mechanism and a position as FFN.
Okay, same start, but what's different?
However, there's a crucial third sublayer inserted right in the middle. This performs multi-head attention over the output of the encoder stack.
Ah, so it looks back at the encoder's work.
Exactly. This is what the paper refers to as encoder-decoder attention. Its purpose is explicit and absolutely vital for translation. This allows every position in the decoder to attend over all positions in the input sequence.
So that's how the translation uses the original sentence.
Precisely. This is how the decoder looks back at the original source sentence, leveraging that rich, context-aware representation created by the encoder to inform its translation. It's the bridge between understanding the input and generating the output.
And does it also have the residuals and layer norm?
Similar to the encoder, yes. Residual connections and layer normalization are meticulously applied around each of these three sublayers, ensuring stable and effective training.
And there's a critical modification to the self-attention of the decoder, right? Something about masking. Why is that so important for how the decoder works?
Absolutely. This masking is essential for maintaining the autoregressive property during training. The self-attention sublayer in the decoder stack is modified to prevent positions from attending to subsequent positions.
Why prevent looking ahead?
Think about how you translate a sentence word by word. You predict the next word based only on the words you've already generated or already know. You can't magically peek into the future words of your own translation. The model needs to mimic this.
Okay, so it forces it to generate step by step, like a human would.
Exactly. The mechanism to achieve this is called masking, the paper explains. This masking, combined with the fact that the output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at positions less than I.
How does the masking actually work, technically?
In practice, masking is implemented very cleverly by setting the values in the input of the softmax function to -infinity for any connections that would correspond to illegal or future positions.
Negative infinity.
Yeah. When softmax is applied too, those values effectively become zero probability, preventing the model from attending to them. This preserves the autoregressive nature, making sure the model generates its output in a proper, sequential, prediction-based manner, using only available information.
So attention is the absolute core, the beating heart of this model. Before we dive into its specific implementation, what exactly is an attention function, generally speaking? Can you paint a picture for us?
At its most fundamental level, an attention function can be described as mapping a query and a set of key value pairs to an output.
Query key value. Okay.
All of these, the query keys, values, and the resulting output are vectors, essentially numerical representations of information. The output of the attention function is a weighted sum of the values.
A weighted sum. How are the weights decided?
That's the crucial part. The weight assigned to each value is computed by a compatibility function between the query and its corresponding key. It basically measures how relevant each key and thus its value is to the query.
That still sounds a bit abstract. Can you give us an analogy to make that more concrete, something we can really visualize?
Certainly. Imagine you're at a library and you have a very specific research question in mind. That question is your query.
Okay, got my question.
The library has thousands of books on its shelves. Each book has a title and a summary on its spine. That's its key, telling you what the book is about.
Right, the label.
And the actual content inside the book is its value.
The information itself.
Exactly. When you have your question, query, you quickly scan the titles and summaries keys of all the books. You're constantly comparing your question to each book's key to see how relevant that book is to your query. This comparison is the compatibility function.
How well does the book title match my question?
Right. Based on how compatible each book's key is with your query, you implicitly assign a relevant score or weight to each book. Then you pull out the most relevant books, the ones with high weights, and combine their information, the values, to form your comprehensive answer. That combined information is the output of the attention function.
So I don't read every book. Just combine info from the relevant ones based on their keys matching my query.
Precisely. The key idea is that you're not just reading every single book. You're selectively focusing and combining information from the most relevant ones.
That analogy truly clicks. Now, the paper introduces a specific implementation called scaled dot product attention. What's in that name, and how does this specific attention mechanism work step by step?
Scaled dot product attention is their particular highly efficient implementation of this general attention function. Let's walk through its computation step by step, perhaps imagining figure 2 left in the paper.
Okay, lay it out.
The inputs for this operation are your queries, Q, keys, K, and values, V. For queries and keys, they all have a dimension we call dk. Values have a dimension dv.
And these are usually matrices, right? Not single vectors.
Correct. In practice, for efficiency, you're not processing just one query at a time. The attention function is computed on a set of queries simultaneously, which are packed together into a matrix queue. Similarly, the keys and values are packed into matrices K and V.
Got it. Step 1.
Here's the step-by-step computation for the matrix of outputs. 1. Compute dot products. You calculate the dot products of each query with all keys. A dot product between two vectors, say q and k, is qk equals k. It's a fundamental measure of similarity or alignment between vectors.
How is this done efficiently for all queries and keys?
If Q is your query matrix and K is your key matrix, this step is achieved by the matrix multiplication QKT, where KT is the transpose of K. This single matrix multiplication efficiently computes all dot products between every query vector in Q and every key vector in K simultaneously.
Okay, dot products calculated. Step 2.
2. Scaling. Each dot product result is then divided by squart TDK. This is the scaled part of the name, and it's a crucial detail I'll elaborate on in a moment.
Got it. Scaling, then.
3. Softmax. A softmax function is applied to the scaled dot products. The softmax converts these raw similarity scores into a probability distribution, ensuring that the weights assigned to the values sum up to 1 for each query. This step precisely determines how much attention each query pays to each key's corresponding value.
So now we have the attention weights. Final step.
4. Weighted sum. Finally, these softmax-generated weights are multiplied by their corresponding values, the V matrix, and then summed up to produce the final output for each query. This output is a context-rich representation for each query, incorporating information from the most relevant values.
Could you provide the mathematical formalization of that with precise definitions of the terms and notation? That seems important.
Absolutely. The formula for scaled dot product attention is right there in equation 1. Attention Q, K, V, U softmax, QKT, S square RT, DK, V.
Okay, let's break that down rigorously. What is Q?
Q. This represents the matrix of queries. If you have LQ queries, e.g. the number of words in your sentence, if this is self-attention, and each query vector has DK dimensions, then Q is a matrix, specifically RLQXDK.
Okay.
K. This is the matrix of keys. If you have LK keys, e.g. also the number of words in your sentence for self-attention or the number of words in the source sentence for encoder-decoder attention, and each key vector also has DK dimensions, then K is a matrix, RLKXDK.
And
V. This is the matrix of values. If you have LV values and each value vector has DV dimensions, then V is a matrix, RLVXDV. Note that LK and LV are typically the same, the number of items you're attending over, but DK and DV can be different, though often in practice they are set equal.
right. And DK and DV are just the dimensions of those vectors.
Precisely. .dk, this is the dimension of the query and key vectors. .dv, this is the dimension of the value vectors.
What about the QKT part?
QKT. This signifies the matrix multiplication of Q and the transpose of K. As we said, this operation efficiently computes all pairwise dot products. Each element, ij, in the resulting matrix represents the dot product, similarity score, of the ith query vector and the jth key vector. It's how all similarities are computed in one highly parallelized step.
And the scaling factor.
Yeah.
Sequor RT-DK. This is the scaling factor which divides each element of the QKT matrix. We need to talk more about why that's there.
Okay. And the softmax. This function is applied row-wise to the matrix after scaling. It converts the raw similarity scores into a probability distribution for each query, ensuring that the attention weights for each query sum to 1 across all keys. This is what generates the actual attention focus, or weights.
And the final multiplication by V.
V. This is another matrix multiplication. The result of the softmax, the attention weights matrix, is multiplied by the V matrix. The final output is a matrix where each row is the weighted sum of the value vectors, representing the attended to output for each query.
Okay, that's much clearer. So that first QRT-DK scaling factor, that's a subtle but clearly important detail. Why did they add that? What problem does it solve in the grand scheme of training these models?
This is indeed critical, a little stroke of genius, really. The paper explains the problem. For large values of DK, the dot products QK, the components of QKT, can grow very large in magnitude.
Why do they grow large?
To understand why, consider footnote 4 in the paper. If the components of Q and K are independent random variables with a mean of 0 and a variance of 1, then their dot product, QK equals sec TK, will have a mean of 0, but a variance that grows linearly with DK.
Ah, so bigger dimension DK means bigger variance in the dot products.
Exactly. As DK increases, the variance, and consequently the typical magnitude of these dot products also increases significantly.
And why is a large magnitude a problem for the softmax function, which is supposed to give us nice probability summing to 1?
This directly impacts the softmax function's behavior. When the inputs to a softmax function are very large in magnitude, either very large positive or very large negative, the softmax function gets pushed into regions where its gradients become extremely small.
Vanishing gradients again.
Yes, it's a classic vanishing gradient problem, specifically for the softmax. If the gradients are too small, the model's weights won't update effectively during training, making it very difficult for the model to learn subtle relationships. Essentially, the softmax output becomes almost binary, nearly 0 or 1 for large positive numbers, making the attention very peaky or hard.
Or almost uniform for large negative numbers.
Right. In these extreme saturated regions, small changes in input produce almost no change in output, leading to tiny, ineffective gradients. The model just stops learning effectively.
So that tiny scaling factor is actually the secret sauce that stops the attention mechanism from getting blinded by the light, preventing it from becoming too extreme and unable to learn subtle connections, essentially making training stable and smart.
Precisely. Scaling by first TOR-RTDK effectively counteracts this increase in magnitude. It pulls the values back into a more stable range for the softmax function, where gradients are well behaved and training can proceed effectively. Without it, you'd likely see the model struggling to learn meaningful attention distributions, making it unstable or just converging poorly.
Did they compare it to other attention types?
Yeah, the paper briefly notes that while additive attention, which uses a feed-forward network for compatibility, and unscaled dot product attention are theoretically similar in complexity, dot product attention is faster and more space-efficient in practice due to optimized matrix multiplication libraries. The scaling is what makes it robust for larger dimensions, which are often needed.
So if scaled dot product attention is so great, why do we need multi-head attention? What does adding edge heads achieve? It seems to add complexity and more parameters.
This is where the transformer's ability to capture truly rich and diverse relationships within language really shines. The core idea of multi-head attention, as depicted in Figure 2, right, is that instead of performing a single attention function on our D-model dimensional queries, keys, and values,
You do something else.
we actually linearly project these inputs each times into different learned lower dimensional subspaces.
Okay, multiple projections. So it's not just one big attention mechanism, but several smaller, specialized ones running in parallel. Can you walk us through that derivation process step by step?
Of course, it's a clever way to diversify the model's focus. Let's break it down. 1. Projection. The original Q, K, and V matrices representing the queries, keys, and values for a given layer are not used directly. Instead, for each of the H attention heads, they are first transformed. For head, where it goes from 1 to H, Q, K, and V are projected using different learned weight matrices, WQY, WKY, and WV. So you effectively create Q, QWQY, Key, KWQY, and Vi, VWVI. These projected matrices are of lower dimensions, DK for key and chi, and DV for V. Each head gets its own view of the inputs.
Okay, so H different sets of projected Q, K, V, then what?
It's 2. Parallel attention. For each of these H heads, a separate scaled dot product attention function is performed in parallel on its corresponding projected inputs, key, chi, V. So head E, attention key chi. Each of these parallel calculations yields a DV dimensional output for that specific head.
So you get H different output vectors for each original position.
Exactly, different DV dimensional outputs. 3. Concatenation. The H resulting DV dimensional output values, i.e. head 1, head 2, head, are then concatenated side by side into a single large vector. If each heady is DV dimensions, the concatenated vector will be HDV dimensions.
A big combined vector. What's the final step?
4. Final linear projection. This concatenated result is then linearly projected once more using a final learned weight matrix, WO, to get the final output of the multi-head attention layer. This final projection typically brings the dimension of the output back to D model, maintaining consistency throughout the network.
Can you write out the math for that too?
Sure. Mathematically, this is formalized as multi-head Q, KV, concat, head 1, head WO, where heady, attention, Q, WQY, KWKY, VWVA.
And those W matrices,
Huh?
the projection weights.
Right. Let's define the notation for those learned parameter matrices. WQY. This is the learned weight matrix used to transform the original Q input for the IVE head. Its dimensions are D model XDK. It allows each head to focus on different aspects of the query. WQY. Similarly, this is the learned weight matrix for transforming the original K input for the I head, dimensions D model XDB, WVI, and this is the learned weight matrix for transforming the original V input for the I head, dimensions D model XDV, WO. This is the final learned output weight matrix. Its dimensions are HDV x D model. It combines the diverse insights from all the individual heads into a single cohesive D model dimensional representation.
That seems like a lot of extra computation running all those attention mechanisms in parallel. So why is this beneficial? What does it achieve that a single larger attention head doesn't?
This is a crucial design choice, and it's incredibly powerful. The paper says, multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions.
Different subspaces, meaning...
Right. Think of it like this. A single attention head is trying to find one optimal way to combine information. It has to average out various types of relationships and dependencies which can blur the focus. Multi-head attention, however, is like having a dream team of specialized linguistic detectives.
Ah, the detective analogy again.
Yeah. Each detective has their own specialized filter or lens, looking at the same information but focusing on different things.
So each head might be looking for something slightly different within the same sentence, like one for grammar, another for meaning.
Exactly. One head might specialize in identifying syntactic relationships, like subject-verb agreement or which noun a verb is acting upon. Another might focus intently on semantic relationships, such as anaphora resolution, figuring out what it refers to. A third might specifically look for dependencies related to negation or sentiment.
And a single head couldn't do all that well.
If you had only one head, it would have to average out all these different types of relationships, which could inhibit its ability to capture any single one precisely. By having multiple heads, each can specialize in learning different kinds of dependencies or focusing on different parts of the input. Then their individual findings are concatenated and combined through that final linear projection WRO to form a richer, more comprehensive understanding. The paper highlights this by saying, with a single attention head, averaging inhibits this.
And what were the practical configurations they used in the paper for these multi-heads? How many heads?
In this work, they employed 8 parallel attention layers, or heads. For each of these, they used DK, DV, D model H equals 512, 8 equals 64. This means that while there are 8 heads, each processes data at a much smaller dimension, 64 instead of 512.
Okay, so smaller dimensions per head. Is it actually more computationally expensive overall then?
And here's the clever design choice regarding computational efficiency. Due to the reduced dimension of each head, the total computational cost is similar to that of single head attention with full dimensionality.
Really? How does that work?
Well, while you have H parallel attention calculations, each is on much smaller vectors. DK and DV are D model. The dominant cost is often in the matrix multiplications, and roughly speaking, HU model 2 is comparable to D model 2, especially when considering the projections too. So it's an ingenious way to get diversified attention without exploding computational costs.
That is clever. So multi-head attention is clearly powerful and efficiently designed. Where exactly does it show up in the transformer architecture? You mentioned it's used in 3 distinct ways.
Indeed. The transformer strategically uses multi-head attention in 3 distinct yet interconnected ways integrated into its encoder and decoder layers.
Okay, location number 1.
1. Encoder-decoder attention layers. This is the critical third sublayer unique to the decoder. Here, the queries originate from the previous decoder layer's output, i.e. the partially generated target sentence.
Right, the translation so far.
While the keys and values come from the output of the encoder stack, the comprehensive representation of the source sentence.
The bridge we talked about.
Exactly. This is absolutely vital because it's how the decoder effectively accesses information from the source sentence to inform its translation. It allows every position in the decoder to attend over all positions in the input sequence. This is the most direct parallel to traditional attention mechanisms found in classic encoder-decoder sequence-to-sequence models.
Okay, that makes sense.
Yeah.
Location number 2.
2. Encoder self-attention layers. These are the first sublayers within each encoder layer. In a self-attention layer, all of the keys, values, and queries come from the same place specifically, the output of the previous layer within the encoder itself.
So the encoder attends to itself.
Yes. This allows each position in the encoder's input sequence to understand its relationship to all other positions in that same input sequence. For example, when processing the word "it's" in a sentence like, "The cat chased the mouse and its tail twitched," the self-attention mechanism allows "it's" to directly attend to cat, clarifying the pronoun's reference and enriching its contextual representation.
And the third location, also self-attention.
3. Decoder self-attention layers. These are the first sublayers within each decoder layer. Similar to the encoder's self-attention, the queries, keys, and values all come from the previous decoder layer's output.
But there's a difference here, right?
Yes. There's that crucial masking modification we discussed. It's masked. This means positions are strictly prevented from attending to subsequent positions in the output sequence.
Remind us how that works again.
The masking mechanism, as we covered, involves setting the scores for illegal connections, future positions, to negative infinity before the softmax. This hard constraint enforces the autoregressive property, ensuring that when the model is predicting the next word, it only uses information from the words it has already generated or already knows from the input. It meticulously mimics the sequential act of human translation or generation.
Okay, so attention is everywhere, doing different jobs. Beyond attention, what other components are essential to each layer of the transformer? It sounds like there's more to it than just attention.
Absolutely. Each of the layers in both the encoder and decoder contains an additional crucial component called a position-wise feed-forward network, or FFN.
Position-wise, meaning?
This network is applied to each position separately and identically, so every word's representation gets processed by this same small network, independently of other words, but after it's been enriched by the attention mechanism in that layer.
What's its structure? Is it just a simple linear transformation?
Its structure is quite straightforward, but it provides vital nonlinearity and capacity. It consists of two linear transformations with a ReLU, rectified linear unit, activation function inserted in between them.
Can you give the equation for that?
Sure. Mathematically, for an input vector x representing a single position's d-model dimensional output from the previous sublayer, like attention, the FFN operation is equation 2 in the paper. FFN x equals 0, xw1 plus b1w2 plus b2.
Okay, let's break that down to what's x.
X, this is the input vector to the FFN for a single position. Its dimension is d-model, so 512.
W1 and B1.
W1. This is the learned weight matrix for the first linear transformation. It projects the d-model dimensional input x into a higher dimensional space, specifically DFF.
This is the learned bias vector for the first linear transformation.
And the max 0.
Max 0. This is the ReLU activation function. It sets any negative values to 0 and passes positive values through. This introduces crucial nonlinearity that allows the network to learn complex patterns beyond simple linear combinations.
Got it. And W2, B2.
W2. This is the learned weight matrix for the second linear transformation. It projects the activations from the hidden layer, which has dimension DFF, back down to D-model.
This is the learned bias vector for the second linear transformation.
So it's a very simple two-layer neural network applied to each position independently.
Exactly. A key detail is that while the linear transformations, that is, the parameters W1, B1, W2, B2, are the same across different positions within a single layer.
Meaning the same FFN is used for word 1, word 2, etc. within layer 1.
Correct. But they use different sets of parameters from layer to layer. So the FFN in encoder layer 1 has a different set of learned W and B parameters than the FFN in encoder layer 2.
Okay. The paper also uses a convolution analogy here.
Yes, it provides an insightful analogy. Another way of describing this is as two convolutions with kernel size 1.
How is it like a one-by-one convolution?
A one-by-one convolution, often seen in image processing, mixes channels or features at a single pixel location without looking at neighboring pixels. In the context of sequences, it effectively means you're applying the same small, fully connected network, mixing the D-model features, to each position independently, giving each position a chance to further refine its representation after attending to others.
And the dimensions involved here.
Regarding dimensionality, the input and output dimensions of the FFN are consistent with the rest of the network. D-model equals 512, which is essential for the residual connections. The inner layer, DFF, has a dimensionality of 2048.
So it expands, then contracts.
Exactly. The network first expands a representation from 512 to 2048 dimensions, applies ReLU, and then projects it back down to 512 dimensions. This expansion allows the model to learn more complex interactions between the features at that position.
How do actual words like cat or house get turned into these numbers the model can understand in the first place? And once the model has processed them, how does it output words back to us?
That happens through standard embeddings and softmax. Two key parts here.
Part 1. Embeddings.
First, for words to be processed by the model, input tokens, like the, cat, sat, and output tokens, the words the model generates, are converted into dense numerical vectors. These are called learned embeddings.
Learned, so they aren't fixed.
Right. Each unique word or subword in the vocabulary gets a unique vector of D-model dimensions, 512 in this case. These embeddings are not fixed beforehand, but are learned and refined during the training process, allowing words with similar meanings or functions to have similar vector representations.
Okay, that's the input side. What about the output? How do we get words back?
Second, for the output side, after the decoder produces its final D-model dimensional vector for a given position, this vector needs to be converted into a probability distribution over the entire vocabulary to predict the next token.
How's that done?
This is done using a standard learned linear transformation followed by a softmax function. The linear transformation maps the D-model dimensional output vector to a vector whose size is the vocabulary size, for example, 37,000 for English-German. The softmax then transforms these raw scores, called logits, into probabilities, indicating the likelihood of each word being the next token in the sequence. The word with the highest probability is usually chosen during generation.
And there's interesting detail about how some of these learned parts are shared to save parameters.
Yes, the paper mentions an interesting optimization. They share the same weight matrix between the two embedding layers, the one that converts input tokens to embeddings and the one that converts output tokens to embeddings, and the pre-softmax linear transformation layer.
Why do that?
This is a technique seen in other models as well, sometimes called weight tying. It reduces the total number of parameters in the model, which can help with generalization and prevent overfitting based on the intuition that the mapping from word to vector, embedding, and vector back to word score, pre-softmax, should be related.
Any other tricks with embeddings?
Additionally, in the embedding layers, the learned weights are multiplied by squared D model. This is mentioned as a common practice.
Why multiply by squared D model?
It helps keep the variance of the embedding vectors consistent, especially after they are summed with the positional encodings, which we need to talk about next. It prevents the positional encoding from dominating the embedding, or vice versa.
Yes. This is a critical question for a model that eschews recurrence and convolution. How on earth does the transformer know about word order? If it processes everything in parallel, simultaneously, how does it know which word comes first, second, or last in a sentence? That seems like a fundamental piece of information for language.
This is indeed the crucial piece that compensates for the complete lack of sequential processing. The paper states it clearly. Since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in the sequence.
Right. Otherwise, dog bites man looks the same as man bites dog.
Exactly. If you just threw all the words into a bag and processed them with self-attention, the order would be lost.
So how do they inject this position information?
To achieve this, they add positional encodings to the input embeddings at the bottom of both the encoder and decoder stacks.
Add them. Literally vector addition.
Yes. These positional encodings have the same dimension, D model, so 512, as the word embeddings, allowing them to be directly summed. This way, the input to the first layer of the encoder and decoder is the sum of the word embedding and its corresponding positional encoding, effectively imbuing each word vector with information about its position in the sequence.
So it's literally adding a position vector to the word vector. What kind of positional encoding did they choose? Did they learn these positions or were they fixed?
The paper chose a very specific and clever type of fixed positional encoding based on sine and cosine functions of different frequencies. They didn't learn these, they computed them deterministically based on the position.
Sine and cosine. That sounds interesting. What's the formula?
Here's the mathematical formalization they used. For a given position, pus in the sequence, for example, 0 for the first word, 1 for the second, and a given dimension I within the D-model dimensional encoding vector. For a given position pus in the sequence, for example, 0 for the first word, 1 for the second, and a given dimension I within the D-model dimensional encoding vector, PE plus 2I, and a given dimension I within the D-model dimensional encoding vector, PE plus 2I plus 1, Winkel's Cospos 1000 2ID model.
Whoa, okay, let's unpack that. Pulse is the word position, right?
Pulse, yes, this represents the absolute position of the token in the sequence, 0, 1, 2.
And I, what's I?
I, this represents the dimension index within the positional encoding vector, ranging from 0 up to D model 2, 1.
So 2I and 2I plus 1 cover all the dimensions from 0 to D model 1.
Exactly. 2I and 2I plus 1. These are used to differentiate between the sine and cosine functions. For even dimensions 2I, the sine function is used. For odd dimensions, 2i plus 1, the cosine function is used. This means half the dimensions use sine and half use cosine, creating a unique oscillating pattern for each position.
And that term in the denominator, 1000 2ID model.
1000 2ID model. This term controls the wavelength or frequency of the sinusoid. As I increases, moving through the dimensions of the positional encoding, the term 2ID model goes from 0 towards 1, so 1000 2ID model increases. This means the wavelength this term gets progressively longer.
So different dimensions encode position at different frequencies.
Precisely. The paper mentions that the wavelengths form a geometric progression from 2 back up to 10,000, 2 parse 2 half, for I equals D model 2, 1. This ensures that different dimensions of the positional encoding correspond to different frequencies, allowing the model to capture information about both fine-grained local positions and broader, long-range relative positions.
Why this specific, somewhat complex sinusoidal function instead of just simple incremental numbers like 0, 1, 2, or a learned embedding for each position, which seems more straightforward?
This choice was made for a very specific, powerful reason related to relative positioning. The authors hypothesized that this particular sinusoidal function would allow the model to easily learn to attend by relative positions, since for any fixed offset k, p-pos plus k can be represented as a linear function of p-pos.
Wait, what does that mean? P-pos plus k is a linear function of p-pos.
It comes from trigonometric identities like sin, a plus b, and cos, a plus b. It means that the positional encoding for a word at position pos plus k can be calculated just by applying a simple linear transformation, a matrix multiplication, to the positional encoding of the word at position pos.
Why is that useful?
This is a profound property. It means the model doesn't have to learn absolute positions from scratch. It can learn a general concept of k positions away simply by learning a single linear transformation, which should make it easier to generalize to relative positions it hasn't explicitly seen during training. It's a built-in inductive bias for relative positioning.
That's subtle but really smart. Did they compare it to learned positional embeddings?
They did experiment with learned positional embeddings, as suggested by other work. They essentially treated each position index like a word and learned a D-model dimensional vector for it during training. And they found that the two versions produced nearly identical results in terms of empirical performance on translation, as shown in Table 3, Row E.
So if they performed similarly, why stick with the more complex sine cosine version?
They ultimately chose the fixed sinusoidal version primarily because it may allow the model to extrapolate to sequence lengths longer than the ones encountered during training.
Ah, generalization again.
Exactly. Learned embeddings might struggle with sequences significantly longer than those seen during training because they haven't learned representations for those unseen higher position indices. Fixed sinusoidal encodings, being a continuous mathematical function, can theoretically generate positional information for any position pose, providing a significant practical advantage for generalizability to new, longer inputs without retraining.
Okay, so we've dissected the transformer's innovative components. The multi-head self-attention, the encoder-decoder attention, the position-wise feed-forward networks, the embeddings, and these crucial positional encodings. But the big question that remains is, why is this whole package better than the older, established approaches like RNNs and CNNs?
Right, what are the fundamental advantages?
The paper offers 3 key criteria, or design goals, for comparing self-attention layers to recurrent and convolutional layers. What were these benchmarks?
Exactly. These criteria quantify the fundamental advantages of self-attention that led to the transformer's breakthrough performance. Let's break down the comparison using Table 1 from the paper as our guide.
Okay, criteria number 1.
The first design goal is total computational complexity per layer. This measures how much processing power is theoretically needed for a single layer of each type in terms of operations.
How does self-attention stack up?
For self-attention, the complexity is ON2, ND1D. Here, N is the sequence length, the number of tokens in the sentence, and D is the representation dimension, D model, which is 512. The N2 part comes from the QKT operation in attention, where effectively every query needs to interact with every key to compute attention scores. That interaction across all pairs is what gives the N2.
Okay, and recurrent layers, RNNs.
For recurrent layers like LSTMs or GRUs, the complexity is ONDD2. Here, D2 comes from the multiple matrix multiplications involved in processing the hidden state D-dimensional through the recurrent connections at each of the N steps.
And convolutional layers, CNNs.
For convolutional layers, the complexity is typically Cocaine E1D2, where out K is the kernel size of the convolution, how many neighbors it looks at.
So comparing N2D for attention versus ND2 for recurrent. Yeah, which is better.
Analysis. The paper points out that self-attention layers are actually faster than recurrent layers when the sequence length n is smaller than the dimension d. So if nd, then n2d is less than nd2.
And is n usually smaller than d?
Yes. They state this is most often the case with sentence representations used by state-of-the-art models in machine translation, which often use subword units like word pieces or byte pair encoding. These break words down, sometimes increasing n a bit, but d, like 512 or 224, is often significantly larger than the typical sequence length n after subwording. So for many practical language tasks, self-attention can be computationally cheaper per layer than RNNs.
What about really long sequences? Doesn't N2 become a problem then?
It does. That N2 term means the cost grows quadratically with sequence length, which can be prohibitive for very long sequences, like whole documents. They acknowledge this and mention that for such cases, self-attention could be restricted to only consider a neighborhood of size R around each token, reducing complexity to R on ID. This was flagged as future work, and indeed, many subsequent models have explored sparse or restricted attention patterns.
How does it compare to CNNs?
They also compare to separable convolutions, which can be more efficient, on 1ED plus on D2. But note that even with maximum kernel size KR on, the complexity is similar to the combination of a self-attention layer plus the FFN layer used in the transformer. So complexity-wise, it's competitive, especially for typical sentence lengths.
Okay, so complexity is often better, but not always. What's the next criterion? This seems like the big one.
Yes. The real game changer, the fundamental advantage, is the second design goal: amount of parallelization measured by the minimum number of sequential operations required. This is about how much of the computation can be done simultaneously, which is key for modern hardware like GPUs.
How does self-attention fare here?
For self-attention, this is O1, a constant number of operations. This is the single biggest win for training efficiency. It means that all positions in the sequence can be computed simultaneously within a layer. There's no inherent sequential dependency holding back the processing. Unlike RNNs, everything can happen at once.
And RNNs.
For recurrent layers, this is ON. This reflects their inherently sequential nature. You must compute the state for step T after computing the state for step T1. You have to wait n steps. This is why they are slow to train on long sequences.
What about CNNs? They seem parallel too.
For convolutional layers, this is also O1. Like self-attention, convolutions can also be parallelized across positions within a layer. So both self-attention and convolutions are inherently parallelizable, which is a major advantage over RNNs.
Okay, so both self-attention and convolutions are good for parallelization, unlike RNNs. But then what about the path length between distant words? You mentioned earlier this was a weakness for CNNs compared to attention.
That brings us to the third and equally critical design goal: maximum path length between long-range dependencies. This is about how easily and directly the network can learn relationships between words that are far apart in a sentence.
Define path length again.
The paper defines path length as the length of the paths forward and backward signals have to traverse in the network. Shorter paths are universally considered easier for the model to learn long-range dependencies, as signals are less likely to get diluted or distorted over long chains of computation.
Right, so how does self-attention do on path length?
For self-attention, the maximum path length is O1, constant. This is truly the hallmark advantage. It means that any two positions in the sequence, no matter how distant, are directly connected through the attention mechanism in a single operation. Information doesn't need to propagate through multiple intermediate steps or layers to reach distant positions. It's an instant connection.
And RNNs, we know this is bad for them.
For recurrent layers, the maximum path length is ON, linear. Information has to propagate sequentially from one end of the sequence to the other. For a dependency between the first and last word, the signal literally travels through N1 steps. This makes learning very long-range dependencies challenging due to vanishing or exploding gradients over that long path.
And CNNs. They're parallel, but what about path length?
For convolutional layers, this is more complex and depends on the setup. For standard contiguous kernels of size k, it still requires O-on convolutional layers stacked on top of each other to connect the first and last positions across a long sequence. Even for more advanced dilated convolutions, which are designed to expand the receptive field more rapidly, it still requires O-log-N layers. So while parallelizable, they still require multiple layers to effectively connect very distant points, increasing the path length compared to the direct O1 of self-attention.
So To use our travel analogy again, if I'm trying to connect two distant cities,
Right.
a recurrent network is like a relay race where each runner passes the message to the next one by one. Takes time.
Right.
A convolutional network is like a series of short plane hops, still requiring multiple intermediate stops, even if a few planes are flying at once across different routes. Faster, but still multiple steps to get far.
Good analogy.
But self-attention is like a direct flight from anywhere to anywhere else in the sequence. Instant connection. Is that the right way to visualize it?
That's a perfect analogy. The O1 maximum path length is truly the defining advantage of self-attention in the transformer for learning long-range dependencies. It fundamentally makes it easier for the model to capture long-range contextual information, which is paramount in understanding complex human language. It's a direct, unhindered line of communication between any two words, no matter how far apart.
Is there a more intuitive, perhaps even artistic, benefit beyond these cold, hard technical metrics, something that helps us understand how the model is thinking?
Yes, a significant and often celebrated side benefit, as noted by the authors, is that self-attention could yield more interpretable models.
Interpretable. How?
What this means is that because the attention mechanism explicitly calculates weights showing what the model is focusing on when processing a particular word, you can actually inspect these attention distributions. You can visualize them to see which words are attending to which other words in a sentence.
So you can actually get a glimpse into the model's thought process, or at least its focus, in a way that's much harder with other architectures like RNNs, where everything is mixed into a hidden state.
Exactly. And the paper previews figures in the appendix, figures 3, 4, 5 in the final paper, which demonstrate this beautifully. They state that individual attention heads clearly learn to perform different tasks. Many appear to exhibit behavior related to the syntactic and semantic structure of the sentences.
Like what kind of tasks?
Well, we'll look at the figures later, but they show examples where one attention head seems to specialize in connecting verbs to their objects, even across long distances. Another head might focus on resolving pronouns, like showing the word "it's" attending strongly back to the noun it refers to, like the law in one example.
Wow. So you can see different heads doing different linguistic jobs.
Yes, it offers an incredible glimpse into the model's inner workings, revealing how it parses meaning and structure. This shows that different heads specialize, offering insights that are much harder to glean from traditional RNNs or CNNs. It's like peeking into the minds of those specialized linguistic detectives we talked about earlier.
That's absolutely fascinating. It transforms these abstract mathematical operations into something we can almost intuitively grasp. Now, let's talk about how they brought this groundbreaking model to life through training and, of course, the results. What kind of data did they use to teach this transformer to translate and understand language?
For the core machine translation tasks, they primarily used two well-established datasets from the WMT, the workshop on machine translation competitions, specifically from 2014.
Which ones?
First, the WMT 2014 English to German dataset. This consists of approximately 4.5 million sentence pairs. For this, sentences were encoded using byte pair encoding, BPE.
BPE, what's that?
It's a method that breaks words into common subword units, so transformer might become trans plus former. This helps handle rare words and creates a shared source target vocabulary of about 37,000 tokens in this case.
Got it. And the second data set?
Second, for English to French, they used the significantly larger WMT 2014 English to French dataset, comprising about 36 million sentence pairs. For this, tokens were split into a 32,000-word piece vocabulary, which is another popular subword tokenization method.
And how did they feed this data during training? Just randomly?
No, a practical detail crucial for efficient training was their batching strategy. Sentence pairs were batched together by approximate sequence length.
Why batch by length?
Each training batch contained a set of sentence pairs with roughly 25,000 source tokens and 25,000 target tokens. This approach maximizes efficiency because sequences of similar lengths can be processed together with minimal padding, adding dummy tokens to make sequences in a batch the same length. Less padding means less wasted computation.
And once they had the data, how much compute power did it take to actually train these transformers to achieve these results? I imagine it was substantial.
The training was performed on one machine equipped with 8 NVIDIA P100 GPUs. While powerful for the time, the speed they achieved was remarkable compared to previous state-of-the-art models.
How fast are we talking?
Regarding the training schedule, their base models, using the core hyperparameters discussed throughout the paper, like D model 512, 6 layers, took about 0.4 seconds per training step. They trained these base models for a total of 100,000 steps, which amounted to approximately 12 hours.
12 hours, that's it. for a state-of-the-art translation model.
Yeah, incredibly fast for the time. The big models, with larger configurations as shown at the bottom of Table 3, meaning more parameters like D model Tumen 24, had a step time of 1.0 seconds. These big models were trained for 300,000 steps, which took about 3.5 days.
Okay, 3.5 days is longer, but still.
The crucial point here, which we'll see reinforced in the results, is that this training time, even for the big models, was a small fraction of the training costs of the best existing models from the literature at that time. This powerfully demonstrated the parallelization advantage of the transformer architecture. Faster training was a huge selling point.
How did they actually optimize the model during training? Any special tricks for the learning rate, which can often be tricky in deep learning?
They used the Atom Optimizer, which was and still is a very popular and effective adaptive learning rate optimization algorithm. They used the standard recommended parameters from the Atom paper. NEOR2 equals 0.9, NUS2 equals 0.98, and NOLs 10 to 9. Nothing too unusual there.
But what about the learning rate itself? Was it constant?
No, they did employ a specific, clever learning rate schedule, which is often crucial for training deep networks successfully. It's designed to provide stability early on and then fine-tune as training progresses. It's defined by equation 3 in the paper. NEO rate D model, NEO 0.5, NES stepnum, national warm-up steps 1.5.
Okay, another formula. Let's break this one down step by step too. What's D model?
All right.
5.
D model 0.5. This is a constant scaling factor based on the model's dimension. Since D model's 512, D model 0.5 is 1 SWOT-RT 512, which is approximately 122.6 or about 0.044. This generally scales the learning rate down to a reasonable magnitude.
And the min part, that looks like the core of this.
This is the core of the schedule. It means that the learning rate will always be the minimum of the two terms inside the parentheses. This is what creates the distinct warm-up and decay phases.
What are the two terms? What's warm-up steps?
The two terms are stepnum -0.5, which is 1 stepnum, and stepnum warm-up steps, 1.5. They set warm-up steps equals 4,000. This parameter defines the initial phase of training.
Okay, so how does the learning rate actually behave over time with this min function?
Let's look at the two phases. One, warm-up phase for stepnum warm-up steps equals 4,000. In this phase, the term stepnum warm-up steps, 1.5, will be the smaller of the two terms since stepnum 0.5 starts high and decreases. As stepnum increases linearly from 1 up to warm-up steps, 4,000, the learning rate will increase linearly from a very small value up to its peak at step 4,000.
So it starts slow and ramps up.
Exactly. 2. Decay phase for stepnum warm-up steps equals 4,000. After the warm-up steps, the term stepnum 0.5, which is 1 in stepnum, becomes smaller than the linear term from the warm-up phase, which would keep increasing. Consequently, the learning rate will then switch to following stepnum, or 0.5, meaning it will decrease proportionally to the inverse square root of the step number. The longer the training progresses, the slower the learning rate becomes.
So why this specific two-stage schedule? Why the warm-up? Why not just start high and decay?
This schedule serves a crucial dual purpose that stabilizes and optimizes training. Warm-up. The linear increase in the learning rate during the initial warm-up steps helps the model stabilize early in training. If you start with a very high learning rate right away, the initial gradients can be huge and erratic, causing the model to diverge or oscillate wildly. Starting low and gradually increasing allows the model to find its footing and adapt its parameters more gently before taking larger steps. Decay. The inverse square root decay after the warm-up helps the model fine-tune as training progresses. Once the model is in a good region of the parameter space, smaller learning rates allow for smaller, more precise adjustments to the weights, helping it converge closer to a good minimum without overshooting. It prevents large oscillations in the loss later in training. This kind of warm-up then decay schedule is widely considered very effective for training deep and complex neural networks like the transformer.
What measures do they take to prevent overfitting, which is a common and critical challenge with large, powerful models and vast data sets?
Regularization, right?
Yeah.
Yes. They employed two primary types of regularization during training to enhance the model's ability to generalize to unseen data.
What was the first type?
1. Residual dropout. Dropout is a popular technique where, during training, a certain percentage of neurons, or their outputs, are randomly dropped out or set to 0 for a given training example. This prevents specific neurons from co-adapting too much and forces the network to learn more robust, less interdependent features.
Where did they apply dropout in the transformer?
In the transformer, dropout was applied in two key places: to the output of each sublayer, the attention mechanisms and the feed-forward networks, before it was added to the sublayer input for the residual connection, and then normalized by layer norm. This injects noise right into the flow between sublayers. Also, to the sums of the embeddings and the positional encodings at the very bottom of both the encoder and decoder stacks. This ensures the initial representation is also robust.
What dropout rate did they use?
For the base model, they used a dropout rate, p-drop, of 0.1, meaning 10% of the relevant activations were randomly set to 0 at each training step for each example.
Okay, dropout. What was the second regularization technique?
2. Label smoothing. This is a clever technique applied to the target probabilities during training, specifically for the cross-entropy loss function.
How does it work?
Instead of using a hard one-hot encoding for the true label, for example, assigning a probability of 1 to the correct word and 0 to all others, label smoothing assigns a slightly smaller probability, 1 epsilons, to the correct label, and distributes the remaining probability mass epsilons uniformly across all incorrect labels. They use an epsilons equals 0.1.
So the model isn't told the correct word is 100% certain.
Exactly. It's encouraged to be slightly less certain. The paper notes its counterintuitive effect. This hurts perplexity as the model learns to be more unsure, but improves accuracy in BLEU's score.
Wait, it hurts perplexity but helps accuracy?
Yeah. Perplexity is a measure of how well a probability distribution predicts a sample. Lower is better. Since label smoothing forces the model to put some probability mass on incorrect words, it naturally makes the model seem less confident, and thus increases perplexity slightly. However, it acts as a powerful regularizer. By preventing the model from becoming overly confident in its predictions, like predicting probability 1.0 for one word, it often leads to better generalization to unseen data and higher actual translation quality, measured by metrics like BLEU score or accuracy. It essentially encourages the model to keep its options slightly open, making it less prone to making overly strong, potentially brittle predictions based only on the training data patterns.
All right, the moment of truth. After all this innovative design, the attention to positional encoding, and the careful training with warm-up and regularization, how did the transformer actually perform on machine translation? What were the headline results that made everyone sit up and take notice?
This is truly where the paper cemented its legacy. Table 2 summarizes the machine translation results, and they were, for their time, quite astonishing. Let's look at the main tasks.
Okay, English to German first. That's a standard benchmark.
On the highly competitive WMT 2014 English to German translation task, the transformer, big model, achieved a BLEU score of 28.4.
How good is 28.4 BLEU?
At the time, it was exceptional. This score outperformed all previously reported models, including large ensembles of models, by over 2.0 BLEU points.
2 whole BLEU points. That's huge in translation, right?
It's a substantial and rare leap, signaling a major breakthrough. This result established a new state-of-the-art by a significant margin.
What about their smaller base model?
Even their base model achieved 27.3 BLEU, which also surpassed all previously published single models and even some ensembles, and importantly, did so at a fraction of the training cost of any of the competitive models listed in the table.
Okay, impressive on German. What about English to French? That was the larger data set.
On the even larger WMT 2014 English to French translation task, the big model achieved an impressive BLEU score of 41.8. The abstract and Table 2 confirm 41.8, though the body text weirdly says 41.0. We'll stick to the table result as per the source.
And how did that compare?
This result outperformed all previously published single models at a significantly reduced training cost. It was another state-of-the-art result for single models.
And when you say fraction of the training cost, what are we talking about specifically? The paper makes a point of highlighting the FLOPs, or floating point operations. Can you give an example?
Yes, the FLOPs column in Table 2 is critical because it quantifies the computational effort required for training. Let's look at English to French again.
Okay.
The previous state-of-the-art ensemble model at the time, ConVS2S ensemble, required approximately 1.2 by 1,021 FLOPs to train. That's a massive number. The transformer, big model, on the other hand, achieved its superior results with only 2.3 by 119 FLOPs.
How much less is that?
That's a reduction in computational effort by a factor of over 50. It really underscores the profound efficiency and parallelizability of the transformer architecture. You got better results with vastly less compute.
Wow. And for English-German?
For English to German, the biggest ensemble previously reported had 1.8 by 10 and 20 FLOPs, while transformer, big, used 2.3 by 1019 FLOPs, still a reduction by a factor of nearly 8. This wasn't just a quality leap, it was an efficiency revolution.
How did they perform inference once the models were trained? Was it a simple one-shot prediction, just taking the most likely word at each step?
No, for inference, they used common, effective techniques to maximize translation quality. Models like these benefit from more sophisticated decoding strategies than just greedy, one-word-at-a-time prediction.
Like what?
They use checkpoint averaging. For the base models, they average the parameters of the last 5 checkpoints saved during training, saved at 10-minute intervals. For the big models, they average the last 20 checkpoints.
Why average checkpoints?
This helps stabilize performance and often leads to slightly better results than using a single checkpoint, as it smooths out any minor fluctuations or noise from the very end of training.
Okay. What else?
They also used beam search for decoding the output sequences.
Beam search. What's that?
Instead of just picking the single most probable word at each step, which is called greedy search, beam search explores multiple possible translations in parallel. It keeps track of the top care and most likely sequences, the beam, at each step.
How big was their beam?
They used a beam size of 4, so keeping track of 4 candidate translations at each step, and applied a length penalty for 0.6. This penalty helps prevent the model from favoring overly short translations, which beam search can sometimes do. These hyperparameters, beam4, SGR 0.6, were chosen based on careful experimentation on a development set.
And how long did they let the translation run?
The maximum output length during inference was set to the input length plus 50 tokens, but crucially, the generation would terminate early if the model predicted a special end-of-sentence token, ensuring it generated natural length sentences.
The paper also includes experiments where they tweak the model's parameters to understand what parts of the design were most important for its performance. These are often called ablation studies, right? Where they remove or change one thing at a time.
Exactly. What did they learn from those experiments in Table 3? What were the key takeaways from those variations?
These model variations, or ablation studies, provide crucial insights into the transformer's design choices, really showing why certain decisions were made and how sensitive the performance is to them. Let's go through the key findings from Table 3, which reports BLEU scores on the English to German translation development set, NUSTIS 2013, comparing variations to their base model. First up, row A looks at the attention heads. What did they find there?
Attention heads. They systematically varied the number of attention heads and the key value dimensions, dk, dav, while keeping the total computational cost roughly constant. So if h increased, dk decreased. They found that. Using a single attention head, h1, resulted in a significant 0.9 BLEU point drop compared to their base model setting.
So multi-head is definitely better than single head.
Absolutely. This clearly demonstrates the immense benefit of multi-head attention. A single head simply isn't enough to capture the diverse relationships effectively. It validates the dream team of specialized linguistic detectives concept we discussed.
Do more heads always mean better? What if they use, say, 16 or 32 heads?
Interestingly, quality also drops off with too many heads. For example, with H16, performance was similar to H8, but with H32, the performance was slightly worse than H8. This suggests there's an optimal number, perhaps around 8 or 16 for this configuration. Too much specialization might lead to fragmentation or difficulty integrating the information effectively in the final projection.
Okay, what about row B, reducing the key size decay?
Key size decay. They explored the impact of reducing the attention key size, dk, while keeping the number of heads and the total dimension, dmodel 512, fixed. When dk was reduced from 64, the base value, down to 16, the model quality significantly dropped by 0.7 BLEU points, from 25.8 to 25.1.
What does that tell us?
This suggests that accurately determining the compatibility between queries and keys is not trivial, and dk needs to be sufficiently large, at least 64 in this case, to represent those complex relationships effectively. It indicates that the expressiveness of the key and query vectors is indeed crucial for the attention mechanism to calculate meaningful similarity scores. You can't skimp too much on the dimensions here.
Makes sense. Rows C and D seem to be about the overall model size and dropout. Standard stuff.
C and D, model size and dropout. These experiments explored the overall size of the model, specifically the main dimension D model and the inner layer dimension of the FFN DFF, and the effect of the dropout rate P drop. As is a common and often predictable finding in deep learning, they found that bigger models are better. Increasing D model from 512 to 1024 and DF from 2048 to 4096, creating their big model configuration, significantly improved performance. Larger models simply have more capacity to learn complex patterns from the data. Dropout was confirmed to be very helpful in avoiding overfitting. Removing dropout entirely, P drop equals 0.0, hurt performance noticeably, and increasing it too much, e.g. P drop equal 0.2 in some runs not shown in the main table but likely explored, could also hurt performance. This reinforces that their choice of BO1 was a good balance for the base model, preventing the model from memorizing the training data too much while still allowing to learn effectively.
Finally, row E, the positional encoding. We talked about this, learned versus sinusoidal.
E, positional encoding. They replaced their fixed sinusoidal positional encoding with learned positional embeddings, an alternative approach where the model learns a vector for each position index during training. The result was remarkably close. Nearly identical results, 25.7 BLEU for learned versus 25.8 for sinusoidal on this dev set.
So empirically, it didn't matter much which one they used.
Empirically, for the sequence lengths in this benchmark, yes, the performance was very similar. This confirms that while injecting some form of positional information is absolutely crucial, omitting it entirely would likely destroy performance, the exact method, fixed sinusoidal versus learned embeddings, had minimal impact on the final BLEU score here.
But they stuck with sinusoidal.
Yes, as we discussed, they reiterated that they ultimately chose the sinusoidal version primarily for its potential theoretical advantage. The ability to extrapolate to sequence lengths longer than those encountered during training, a practical benefit for real-world robustness and generalization.
So the transformer performed incredibly well on translation, breaking records and doing it efficiently. But what about other challenges? Could this architecture generalize to other tasks beyond just language translation, which seems to be its primary focus in the paper?
That's a critical question for any novel architecture's lasting impact, and the paper addressed it head-on by applying the transformer to English constituency parsing.
Constituency parsing, what's that again, and why is it challenging?
It's the task of analyzing a sentence to determine its grammatical structure, usually represented as a tree. For example, identifying noun phrases, verb phrases, prepositional phrases, and how they nest together. It presents distinct challenges compared to translation. The output isn't just a sequence of words, but a linearized representation of a parse tree, like SNP, VP, which has strong structural constraints. The output sequence representing the tree can be significantly longer than the input sentence, especially for complex sentences. Furthermore, traditional RNN sequence-to-sequence models had historically struggled to attain state-of-the-art results in small data regimes for parsing, often requiring specialized parsers or large amounts of external data.
So how did they test the transformer on parsing? What data did they use?
They conducted two main experiments on the Wall Street Journal, WSJ portion of the Penn Tree Bank, which is a standard benchmark dataset for parsing. One, WSJ only setting. They trained a 4-layer transformer, a smaller version than the translation models with D-model at least 1024, on a relatively small 40,000 training sentences of the WSJ section. This tests its ability to learn from limited high-quality data. 2. Semi-supervised setting. They also trained it using a much larger corpus of approximately 17 million sentences, combining high-confidence parsed sentences from external sources and output from the Berkeley parser applied to other corpora. This tests its ability to leverage large amounts of potentially noisier data.
Did they use a different vocabulary?
Yes. They use a vocabulary of 16,000 tokens for the WSJ-only setting and 32,000 tokens for the semi-supervised setting, tailoring the vocabulary to the parsing task and data size.
And what were the results in Table 4? Did it really live up to its promise of generalizability? Could this attention-only model handle structured prediction like parsing?
The results were very promising and indeed demonstrated strong generalizability. The standard metric for parsing is F1 score, which balances precision and recall. For the WSJ-only setting, training on only the relatively small amount of high-quality data from the Wall Street Journal, their 4-layer transformer achieved 91.3 F1 score.
How good is 91.3 F1?
This is significant because it outperformed the Berkeley parser, a well-established, highly optimized parser from prior work, even when the transformer was trained only on the relatively limited WSJ training set. This was a key finding, as RNN sequence-to-sequence models often struggled in this small data regime for parsing, indicating the transformer's ability to learn complex structures effectively even with less data. For the semi-supervised setting, leveraging the much larger corpus, the transformer achieved an even higher F1 score of 92.7.
So it works surprisingly well, even without specific parsing modifications.
Exactly. The conclusion from the authors was clear. Despite the lack of task-specific tuning, our model performs surprisingly well. This strong performance, especially on a task with different structural demands and in data regimes where RNNs sometimes struggled, really solidified the transformer's versatility and robustness as a general-purpose sequence modeling architecture. It showed this wasn't just a translation trick, it was a fundamental breakthrough in how machines process sequences applicable more broadly.
We've covered the architecture, the math, the training, the results. Let's bring this to life a bit more. The paper includes some fascinating visualizations of what the attention heads are actually looking at. What insights can we glean from those?
Yes, Section 7 and the appendix contain visualizations that offer some really cool qualitative insights into how self-attentional works and what the different heads might be learning. Let's look at a few examples they highlight.
Okay. Figure 3 focuses on long-distance dependencies, right?
Figure 3, long-distance dependencies. They show an example sentence. Making recommendations to the interim government on the processes and procedures is proving particularly challenging and time-consuming now that the government has been in place for over a year. They visualize the self-attention from the word making in one specific head, and that head clearly attends strongly to words like proving, challenging, and time-consuming.
So it connects the start of that long phrase making to its conclusion is proving.
Exactly. It shows one attention head learning to perform a task related to identifying these long-distance dependencies, completing a phrase across many intervening words. This directly addresses the problem of long path lengths that plagued RNN's attention, provides that direct connection.
What about figure 4? Anaphora resolution. What's that?
Figure 4, anaphora resolution. Anaphora resolution is about figuring out what pronouns or other referring expressions refer back to. They show the sentence. The law will never be perfect, but its application should be just, this is what we are missing, this is what we should be concentrating on. They visualize the attention from the word its, and several attention heads show its attending very strongly back to the law.
So the model figures out that its refers to the law.
Precisely. It demonstrates a semantic understanding of pronoun reference. They also point out the sharp nature of these attentions. The lines are very bright, meaning the model is very confident about what it's focusing on. It's not just vaguely looking everywhere, it's pinpointing the relevant antecedent.
And figure 5 shows multiple heads at once.
Figure 5, syntactic semantic structure. This figure provides a broader view showing attention patterns for multiple heads from the word it in the sentence, the animal didn't cross the street because it was too tired. One head strongly attends to the animal, correctly resolving the pronoun. Another head seems to attend broadly across the whole sentence, perhaps capturing a more global context.
So different heads really do special.
Yes, the overall conclusion from these visualizations is that many attention heads exhibit behavior that seems related to the structure of the sentence, both syntactically and semantically. This offers an incredible glimpse into how the model parses meaning, going beyond just processing tokens sequentially. It supports the idea that different heads specialize in different linguistic tasks, contributing distinct pieces of information that are then integrated.
So to conclude this deep dive, what's the final verdict on attention is all you need? What did this paper fundamentally achieve, wrapping it all up?
The paper's ultimate conclusion is impactful and straightforward. They presented the transformer, which they asserted was the first sequence transduction model based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architectures with multi-headed self-attention. This wasn't just an incremental improvement, it was a foundational shift in how we approach sequence modeling.
And the key wins, the big takeaways that really drove this paradigm shift. Can you summarize those again?
The key wins are threefold, and they've profoundly reshaped the field. 1, faster training. For translation tasks, the transformer could be trained significantly faster, often an order of magnitude faster than architectures based on recurrent or convolutional layers, thanks to its high parallelizability O1 sequential operations. This meant faster iteration, faster research, and quicker deployment of advanced models. 2, state-of-the-art quality. It achieved new state-of-the-art results on both the WMT 2014 English to German and English to French translation tasks. In the former, their best model even outperformed all previously reported ensembles, a truly stunning achievement for a single model. 3, strong generalization. The successful application to English constituency parsing demonstrated its robust ability to generalize to other complex tasks, even with limited task-specific tuning. This showed it wasn't a niche solution just for translation, but a powerful general-purpose architecture for understanding sequential data.
And what did the authors envision for the future based on this incredible work? Did they have a roadmap for what attention could unlock next? Where do they see this going?
Their excitement was palpable in the conclusion, and they truly laid out a vision that has largely come to pass in the years since. They expressed plans to apply attention-based models to other tasks beyond translation and parsing.
Like what?
Critically, they wanted to extend the transformer to problems involving input and output modalities beyond just text, such as images, audio, and video. This multimodal ambition is a huge area of research today. They also intended to investigate local or restricted attention mechanisms, like the RND complexity we mentioned, to efficiently handle even larger inputs and outputs, like entire documents or high-resolution images, pushing the boundaries of what the model could process.
Anything else?
And finally, making generation itself less sequential, exploring non-autoregressive or partially non-autoregressive decoding was another key research goal mentioned. These weren't just technical details, they essentially laid out a roadmap for much of the future AI research that followed.
And they shared the code, right?
Yes. Importantly, they mentioned that the code used to train and evaluate their models was available as part of the Tensor library on GitHub, fostering open science and enabling the rapid community adoption and iteration that truly propelled the transformer revolution.
This deep dive has truly shown us that sometimes the most profound breakthroughs come not from adding more layers or more complexity, but from simplifying a complex system. In this case, by relying solely on attention and completely removing the old stalwarts of recurrence and convolutions, they unlocked a truly revolutionary new architecture.
It's not always about more, it's about finding the right fundamental building block. And attention, it turned out, was incredibly powerful.
Absolutely. The transformer born directly from this paper underpins so many of the advanced AI applications you interact with daily.
Yeah, from the improved translation services on your phone or web browser to better chatbots and question answering systems.
And most significantly, it forms the foundational architecture for the large language models like GPT, Gemini, LaMDA, Llama, and others that are now dominating the AI landscape and capturing the public imagination.
This isn't just theoretical history. It's a practical innovation that has fundamentally reshaped the field and increasingly our daily lives.
And that leads to our final provocative thought for you, our listener, to mull over. If attention truly is all you need for language, and we've seen its incredible power in processing text, what might happen when we apply this same attention-only philosophy or variations of it to even more complex multimodal challenges?
What does it mean for the next generation of AI that can understand and generate not just text, but images, sounds, music, code, robot actions, maybe even scientific discoveries, all potentially within a unified, attention-based framework?
If attention is the key to flexible, parallelizable, long-range understanding, what does that unlock for creating truly general-purpose artificial intelligence?
Understanding these core principles from papers like Attention is All You Need really empowers you to better grasp the next wave of AI developments and appreciate the elegant simplicity that can emerge from profound innovation. It's truly a testament to the power of a single brilliant idea.
Thank you for joining us on this deep dive into Attention is All You Need. We hope this conversation has illuminated a pivotal moment in AI history for you. Until next time.
Thanks, everyone.
Welcome, curious minds, to the deep dive. Today, we're plunging into a research paper that, well, didn't just tweak an existing technology.
No, it fundamentally reshaped an entire field. We're really talking about the bedrock for modern AI giants, things like ChatGPT, Google Translate.
Exactly. If you've ever marveled at a sophisticated language model
Right.
or, translated text instantly, or just noticed these incredible leaps in AI capabilities recently.
Then the paper we're diving into today is truly the genesis of that revolution.
So our mission in this deep dive is to peel back every single layer of this groundbreaking work. Attention is All You Need, published back in 2017 by Vaswani and a whole team.
That's right, Vaswani et al.
You've almost certainly heard the name, maybe seen Transformer tossed around, but how much do you truly know about what makes it tick?
Yeah, the radical innovations it introduced, the mathematical elegance underpinning it all, that's what we're getting into.
And our guide for this, well, extensive exploration is the original paper itself. We're going section by section, maybe even line by line sometimes.
Absolutely. We want to make sure you gain a comprehensive and, truly informed understanding of the what and, crucially, the why behind every single design choice these authors made.
Okay, let's begin right at the start then, page 1. The abstract and the introduction. This is where they really lay out their bold declaration.
Right, setting the stage by describing the AI landscape just before 2017.
So the abstract kicks off by setting that scene, highlighting the dominant sequence transduction models of the time.
Exactly. Before the transformer burst onto the scene, the field was primarily led by complex recurrent neural networks, RNNs, or convolutional neural networks, CNNs.
Right, and these models typically operated within an encoder-decoder structure.
That was the standard paradigm.
And when we talk about sequence transduction, we're basically talking about a task where you take one sequence, like an English sentence,
And transform it into another sequence, like, say, a German sentence. Machine translation is the classic example, yeah.
but it also applies to things like speech recognition, right? Where an audio sequence becomes text.
Precisely. Or text summarization, sequence to sequence. And in those pre-transformer days, attention mechanisms did exist. That's important.
Okay, but they weren't the main event.
Not at all. Here's a key difference. They were almost always an add-on. The paper notes, they were used to, quote, connect the encoder and decoder.
Meaning they helped information flow between these existing RNN or CNN parts.
Exactly. They weren't the core computational engine. They were more like a helpful bridge, facilitating communication between the encoder and decoder stages.
Okay, and this is where it gets really interesting, because the paper then just drops this bombshell, quote, we propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely.
That's the mic drop moment right there. A truly radical proposal.
What does it actually mean to be solely on attention and to just dispense with recurrence and convolutions? Those are the main tools.
The significance is profound. To dispense with recurrence means abandoning that traditional sequential processing of RNNs. Think about how an RNN reads a sentence.
Word 1, then word 2 based on word 1, word 3 based on word 2, like a chain.
Precisely. Each step TET depends directly on the output of the previous step T1. This chain-like dependency, while maybe intuitive for sequences, inherently makes them very, very difficult to parallelize.
And modern deep learning thrives on parallel computation, right?
Yeah.
Especially with GPUs.
Absolutely. So this sequential bottleneck was a massive hurdle. It limited speed, it limited scale.
Okay, so getting rid of recurrence tackles that parallelism problem. What about shedding convolutions? CNNs were used for sequences too, weren't they?
They were in models like ConvS2S or ByteNet, and CNNs compute representations by applying filters across different positions simultaneously, so they do offer more parallelism than RNNs.
But they have their own limitation.
Yes, the path length issue. To capture dependencies between distant parts of a sequence, say, a word at the beginning and a word at the end, you typically need to stack many convolutional layers.
And each layer adds a step.
Adds a step to the path length information has to travel. This accumulation of steps makes it harder to learn those really long-range connections effectively. Information gets diluted, gradients can struggle.
So the transformer's core idea, based solely on attention, means attention isn't just helping out anymore, it is the mechanism.
It's the only mechanism relating different parts of the sequence. No more HT1 feeding into HT, no more sliding convolutional filters building up context layer by layer. It's a completely different way of thinking about sequence processing.
And this radical architectural shift enabled some truly groundbreaking claims right there in the abstract. Let's unpack those. First, quality.
Right, quote, our model achieves 28.4 BLEU on the WMT 2014 English to German translation task, improving over the existing best results, including ensembles, by over 2 BLU.
Okay, BLEU. We need to break that down. What does 28.4 BLEU actually mean? And why is a 2 BLU point jump such a big deal in machine translation?
Okay, so BLEU stands for Bilingual Evaluation Understudy. It's basically a standard metric that measures how good machine-translated text is by comparing it, n-gram by n-gram, to one or more high-quality human reference translations.
So higher is better.
Higher is better, yes. And a score of 28.4 for English to German back in 2014. That was remarkable high. It indicated a really fluent, accurate translation. In machine translation research, honestly, even a 0.5 BLEU point increase is considered pretty significant.
So 2 points is huge.
It's a massive leap. It translates into a noticeably better, more human-like translation quality. And the fact that it outperformed ensembles.
Yeah, what does that mean? Ensembles are like combinations of models.
Exactly. Combining multiple strong models usually gets you the very best scores. So for a single model architecture to beat even the best ensemble results, that was really telling. It set a completely new benchmark.
Then there's the claim about parallelization. More parallelizable. Why is that so critical? We touched on GPUs, but let's elaborate.
It's absolutely fundamental to deep learning at scale. Modern AI training relies so heavily on graphics processing units, GPUs, which are just fantastic at parallel computation, doing tons of calculations simultaneously.
But RNNs couldn't really use that power effectively.
Not fully, no. Because of that inherent sequential processing needing step T1 to do step T, The transformer, by operating solely on attention, can compute relationships between all parts of a sequence at the same time.
Wow. Okay.
So no waiting. This means you can feed much larger chunks of data through the network at once, dramatically speeding up the training process. It's like switching from a single-lane country road to a multi-lane superhighway for data.
Which leads directly to their next claim about training time, requiring significantly less time to train. They give that specific example.
Yeah, the English to French task.
I've done.
Our model establishes a new single-model state-of-the-art BLEU score of 41.8 after training for 3.5 days on 8 GPUs, a small fraction of the training cost of the best models from the literature.
3.5 days on 8 GPUs. How does that compare to what came before? And what did that mean practically for AI research?
Well, if you look ahead to Table 2 in the paper, we'll get there, the contrast is just stark. State-of-the-art models back then, like Google's big neural machine translation system, GNMT,
Yeah, I remember that one.
it could take weeks, sometimes even months, to train on similar hardware for comparable tasks. Reducing that to 3.5 days, that wasn't just a little bit better, it was a complete game changer.
Right. Changes how you can even do research.
Exactly. It meant researchers could iterate on ideas much faster, run way more experiments, develop more powerful models in a fraction of the time, and, crucially, the cost. This directly accelerated the pace of AI research and development for the entire field. It unlocked progress.
And the final claim in the abstract mentions generalization. The transformer generalizes well to other tasks by applying it successfully to English constituency, parsing both with large and limited training data. Why is generalization so important?
Generalization is really the holy grail for AI models. It signals robustness, versatility, a model that can perform well on different kinds of tasks without needing a ton of specific redesign or tuning for each one is far more valuable.
It suggests the architecture itself learns something fundamental.
That's the idea. It's learned transferable patterns that apply more broadly. And English constituency parsing, well, that's quite different from machine translation.
How so?
It's about understanding the grammatical structure of a sentence, identifying noun phrases, verb phrases, how they fit together, not just converting it to another language. The transformer's success here showed its adaptability beyond just translation, hinting at its potential for a huge range of natural language processing challenges.
Before we move on from the abstract, it's worth acknowledging the authors. The paper mentions equal contribution from 8 researchers: Jacob Uskarite, Ashish Vaswani, Ilya Polosukin, Noam Shazir, Nikki Parmar, Leon Jones, Yukas Kaiser, and Aiden N. Gomez.
That's right. It really highlights the collaborative genius behind a breakthrough like this. It wasn't just one person having a eureka moment.
No, it was clearly a synergistic effort bringing together diverse expertise to make this happen.
A fantastic testament to collaborative innovation in science. Okay, so now diving into the full introduction section, the authors dig deeper into the limitations of that status quo, the problems the transformer was designed to solve.
They start by reiterating the dominance of RNNs, right? LSTMs, GRUs.
Yes, long short-term memory networks,
Yeah.
LSTMs, and gated recurrent units,
Yeah.
GRUs. These had been the undisputed kings of sequence modeling for years. They were the state of the art, and people were continuously making incremental improvements to them.
But they all shared that fundamental flaw. Sequential computation. The paper says recurrent models typically factor computation along the symbol positions of the input and output sequences. Let's unpack that phrase again.
Right. It means that to compute the hidden state, the model's internal representation, let's call it HT, at a given time step t.
Like for the third word in a sentence.
The model absolutely needs the hidden state from the previous step, HT1, and the input for the current position, t. So HT is a function of HT1 and the input at t.
Using your example, the child ate the big red apple. To process apple.
Its understanding, happle, is a direct function of its understanding of red, and the input word apple. Its happle is a chain, red and not apple. It's literally a chain reaction where each link depends entirely on the one immediately before it.
And that chain reaction is the bottleneck.
Precisely. This inherently sequential nature precludes parallelization within training examples. Because you need hat T1 before you can calculate HT, you simply cannot calculate all the HT values for a single sentence simultaneously.
You have to wait, step by step.
You have to wait. This becomes, as the paper says, critical at longer sequence lengths because the chain gets longer, the dependencies grow, the wait time accumulates. It leads to very, very long training times.
And it also mentions memory constraints.
Yes. Memory constraints limit batching across examples. If your individual sequences are very long, the intermediate states, HT for all T, take up a lot of memory. This means you can't fit many long sequences into your GPU memory at once to process different sequences in parallel within a batch. So it hinders efficiency in two ways: within a sequence and across sequences in a batch.
The paper does acknowledge there were attempts to mitigate this, things like factorization tricks and conditional computation.
Right, references 21 and 32. And these did achieve significant improvements in computational efficiency. They were clever ideas.
Yeah.
But, as the authors emphasize, the fundamental constraint of sequential computation, however, remains. These were optimizations around the sequential nature. They didn't eliminate it. They made the chain reaction faster, perhaps, but it was still a chain reaction.
They didn't break the chain.
Exactly. That foundational limitation is what the transformer was designed to shatter. The introduction then pivots, highlighting the growing importance of attention mechanisms.
We mentioned these were add-ons before.
Right, but they had become an integral part of compelling sequence modeling and transduction models, and their power was in allowing modeling of dependencies without regard to their distance in the input or output sequences.
Okay, so attention could create these shortcuts, allowing a word to directly connect with any other word, no matter how far apart.
That's a great way to think about it. It directly addressed the distance problem that RNN struggled with. In an RNN, information from the start of a really long sentence could get diluted or just lost by the time the model reached the end because it had passed through so many sequential steps.
Like a game of telephone.
A bit, yeah. Attention provided a direct connection. So, for example, a pronoun at the end of a paragraph could directly attend to the noun it refers to way back at the beginning, grabbing that relevant information instantly without it having to filter through all the intermediate words.
That sounds powerful. But again, the crucial caveat.
The crucial caveat the paper states clearly. In all but a few cases, however, such attention mechanisms are used in conjunction with the recurrent network. They were still assistants to the main RNN engine.
Which brings us back to the transformer's defining principle. Let's hear it again.
Quote, the transformer, a model architecture, eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output.
Eschewing recurrence, just getting rid of it, and relying entirely on attention.
This means the transformer doesn't just connect distant parts, it connects all parts of a sequence simultaneously, directly, and in parallel. These global dependencies mean any output position can directly relate to any input position or any position within its own sequence. That's the self-attention part.
Which is fundamentally different from the local step-by-step context building of RNNs.
Completely different. And this direct global connection is what provides that significantly more parallelization and allows it to reach a new state-of-the-art in translation quality after being trained for as little as 12 hours on 8 P100 GPUs. It was a true paradigm shift, hitting both speed and performance.
All right, let's transition into part 2, background. So even before the transformer, other models were trying to push for more parallelism in sequence modeling, right?
Yes, absolutely. The goal of reducing sequential computation wasn't unique to the transformer team. The paper mentions earlier models like the extended neural GPU, ByteNet, and ConvS2S.
And their approach was mainly using CNNs?
Primarily, yes. They used convolutional neural networks as their basic building block. CNNs, as we mentioned, inherently compute hidden representations in parallel for input and output positions by applying filters across the sequence simultaneously.
So CNNs offered parallelism, but they still had that challenge we talked about, the path length to distant dependencies.
They definitely did. The paper states, in these models, the number of operations required to relate signals from two arbitrary input or output positions grows in the distance between positions.
How much does it grow?
Linearly for ConvS2S and logarithmically for ByteNet. This path length is basically the minimum number of computational steps or layers a signal has to go through to connect two distant points.
And if that path length increases with distance,
it inherently makes it more difficult to learn dependencies between distant positions, as reference 12 points out. Think about backpropagation. Trying to send an error signal back through many, many layers or steps makes gradients prone to vanishing or exploding. It just gets harder to learn those connections.
and the transformer's advantage here is just night and day.
Absolutely monumental. In the transformer, this is reduced to a constant number of operations.
O1 versus ON or O log ln.
Exactly. It means no matter how long the sequence is, hundreds or even thousands of words, any two positions can directly communicate in a single computational step via the attention mechanism. This fundamentally solves that long-range dependency bottleneck that plagued previous architectures.
Making it much easier to capture context across an entire document, potentially.
Potentially, yes.
Yeah.
Now, the paper does acknowledge a subtle trade-off, albeit at the cost of reduced effective resolution due to averaging attention-weighted positions.
Meaning a single attention calculation might sometimes average things together too broadly, maybe losing some fine-grained detail.
That's the potential concern, yeah. If one attention mechanism tries to capture everything, it might smooth things out too much, but the authors immediately signal their solution, and it's a core part of the architecture. An effect we counteract with multi-head attention, as described in section 3.2.
Ah, so that's one of the key reasons for multi-head attention. We'll definitely circle back to that.
Absolutely, it's a crucial piece.
Okay, let's properly define the core concept itself.
Yeah.
Self-attention. Section 2.2. The paper defines it as, quote, an attention mechanism relating different positions of a single sequence in order to compute a representation of the sequence.
Let's break that down. Relating different positions of a single sequence. That's the key. Unlike the encoder-decoder attention we mentioned earlier, which connects the input sequence, encoder, to the output sequence, decoder.
Like English to German.
Self-attention looks within just one sequence. For instance, take the sentence, the cat chased the mouse because it was fast. Self-attention allows the word it to directly look back and attend to both cat and mouse to figure out which one it refers to.
Ah, okay. Or maybe fast attends strongly to cat and chased to understand the context.
Exactly. It's about building a richer representation for each word within its specific context by letting it look at and relate to all the other words in the same sentence.
It's like an internal dialogue within the sentence, where each word clarifies its meaning based on its neighbors near and far.
That's a great analogy. This internal contextualization helps the model grasp nuances of meaning, syntax, and relationships within the input itself. And self-attention wasn't entirely new, it had already shown promise.
Right, the paper mentions prior successes.
Yeah, in tasks like reading comprehension, abstractive summarization, textual entailment, and learning task-independent sentence representations. References 4, 27, 28, 22.
Why were those tasks particularly suited for self-attention?
Because they heavily rely on understanding internal relationships within a text. Reading comprehension often involves resolving pronouns or understanding complex dependencies. Summarization needs to capture the core meaning derived from relationships across the whole document. Textual entailment checks if one sentence logically follows from another, requiring deep comparison. So the ability to relate any part of the text to any other part is crucial.
The paper also briefly mentions end-to-end memory networks. How do they fit in?
They are mentioned as being based on a recurrent attention mechanism instead of sequence-aligned recurrence. So they also used attention, often to access some form of external memory.
But still involve recurrence.
Often, yes, in how they processed queries or updated the memory over time. The key distinction the paper draws for the transformer is the complete absence of sequence-aligned RNNs. While memory networks might use attention, they often weren't purely attention-based in the way the transformer processes the sequence itself.
Got it. So the transformer really unyoke attention from any kind of step-by-step recurrent processing for the main sequence representation.
Precisely, making it fully parallelizable in that core computation.
And that leads them to strongly reaffirm their unique contribution. Quote, to the best of our knowledge, however, the transformer is the first transduction model relying entirely on self-attention to compute representations of its input and output without using sequence-aligned RNNs or convolution.
That sentence really sums up their core claim to novelty. No sequence-aligned RNNs, no sequence-level convolution, just attention. It sets the stage perfectly for the rest of the paper, where they promise to actually describe the transformer architecture, motivate self-attention further, and really hammer home its advantages.
Okay, let's dive into that architecture then. Part 3, model architecture. This is where we get the blueprint, starting with the overall encoder-decoder structure in section 3.1.
Right. And as we mentioned, most competitive sequence transduction models, even before the transformer, generally followed this encoder-decoder pattern.
Let's recap the rules quickly. The encoder.
The encoder's job is to take an input sequence of symbol representations. Think of these as word embeddings, basically vectors representing words like my1, xn, and map them into a sequence of continuous contextualized representations. Let's call it Z, Z1, Z, and N.
So Z is the encoder's rich, abstract understanding of the entire input sentence.
Exactly. It's digested the input and produced this meaningful representation.
And then the decoder takes this Z.
Given Z, The decoder then generates the output sequence, say Y1IM, but crucially, it does this one element at a time.
Step-by-step generation.
Yes, and this step-by-step generation is key because the model is autoregressive, reference 10. This means that at each step j, when the decoder is generating the output psi j, it consumes the previously generated symbols as additional input.
Can you give that translation example again?
Sure. Machine translation, English to French. Input, the cat sat. Output, le chat s'est assis. When the decoder is about to generate the third word, c'est, it not only looks at the encoder's output z, but it also takes its own previous outputs, le and chat, as input to inform its prediction for set.
So it builds the output incrementally, using its own past predictions to guide the future ones.
Precisely. Now, the transformer adopts this overall encoder-decoder architecture, but it implements the internals of the encoder and decoder very differently. It uses, quote, stacked self-attention and point-wise fully connected layers for both the encoder and decoder, which we can see visually in the left and right halves of Figure 1.
Okay, let's picture Figure 1. Left side encoder, right side decoder. They look similar in structure, stacks of layers, but with some key differences we'll get into. Let's break down these encoder and decoder stacks, section 3.2.
Right. The encoder is described as being composed of a stack of n equals 6 identical layers.
Identical layers means they have the same internal components, right? But different weights.
Exactly. Same structure, but distinct learned parameters for each of the 6 layers. Now, each of these 6 identical layers itself contains 2 main sublayers.
Okay, what are they?
First, a multi-head self-attention mechanism. This is the core engine we've been talking about. Second, a simple, position-wise, fully connected feed-forward network. We'll unpack both of those in detail.
But crucially, around these 2 sublayers, they add a couple of other important things. Quote, we employ a residual connection 11 around each of the 2 sublayers, followed by layer normalization 1. Let's tackle residual connections first, often called skip connections.
That's right, skip connections. A residual connection means that the input X to a sublayer is directly added to the output of that sublayer before it goes through the next step, like normalization.
So, mathematically, if the sublayer computes a function sublayer X, the output is X plus sublayer X.
Essentially, yes, followed by normalization. So the full operation for a sublayer's output is layer norm X plus sublayer X. These residual connections are incredibly important in deep networks.
Why is that?
They act like information highways, allowing the gradient signal during training to flow back through the network more easily, bypassing layers if needed. This helps prevent the vanishing gradient problem, where the signal gets too weak in very deep networks. It also helps ensure that information from earlier layers isn't lost as it passes through many transformations. It makes training much deeper networks feasible.
Okay, so residual connections help with training deep networks. And then right after the addition comes layer normalization 1. What does that do?
Layer normalization, or layer norm, works by normalizing the activations within a single layer for each data sample independently. It calculates the mean and variance across all the features, the D-model dimension, for a given sequence position and normalizes based on that.
How is that different from batch normalization?
Batch normalization normalizes across the batch dimension, using the mean and variance of the activations for a specific feature across all samples in the batch. Layer norm is often preferred in NLP and sequence models because sequence lengths can vary within a batch, which can make batch norm statistics less stable. Layer norm helps stabilize the hidden state dynamics, speeds up training convergence, and makes the model less sensitive to the scale of the parameters or initialization.
So the formula layer norm X plus sublayer X means take the input X, pass it through the sublayer to get sublayer X, add the original input X back, the residual connection, and then normalize the result using layer norm.
Precisely that order.
And to make that X plus sublayer X addition work, the dimensions have to match, right?
Absolutely. The paper notes, to facilitate these residual connections, all sublayers in the model, as well as the embedding layers, produce outputs of dimension D model equals 512. This consistent dimensionality of 512 throughout the network is a key design choice, enabling those vital residual connections.
Okay, that covers the encoder stack. Now the decoder stack. Also N equals 6 identical layers.
Also N equals 6 identical layers, yes, but with a critical addition.
The third sublayer.
Exactly. In addition to the 2 sublayers in each encoder layer self-attention and feed-forward, The decoder inserts a third sublayer, which performs multi-head attention over the output of the encoder stack.
This is the connection between the decoder and the encoder's understanding of the input.
Precisely. This is the encoder-decoder attention, sometimes called cross-attention. Its purpose is absolutely crucial. It's how the decoder accesses and incorporates that rich, contextualized representation Z that the encoder works so hard to produce from the source sentence.
So as the decoder is generating the output sequence, step by step, it uses this layer to constantly look back at the encoded input, asking, okay, based on the whole input sentence, what should I generate next?
That's exactly the intuition. It allows every position in the decoder to attend over all positions in the input sequence. And just like in the encoder, they employ residual connections and layer normalization around each of these three sublayers in the decoder for stability and good gradient flow.
Now, there's one more modification, specifically to the self-attention sublayer within the decoder. It's masked, right?
Yes, this is critical. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions.
Why is this necessary?
It's fundamental for preserving that autoregressive property during training. When we train the model, we typically feed the entire target sequence to the decoder at once using teacher forcing. But when the decoder is calculating the representation for, say, the third word in the target sequence, it must not be allowed to peek ahead and see the fourth, fifth, or any subsequent words in the target sequence. If it could, the prediction task would be trivial.
It needs to predict the next word based only on the previous words, just like it will have to do during actual generation inference.
Exactly. So this masking enforces that causality. The paper explains how. This masking, combined with the fact that the output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at positions less than I.
And how is the masking implemented technically?
It's done inside the scaled dot product attention mechanism, specifically before the softmax step. They mask out setting to all values in the input of the softmax which correspond to illegal connections.
So if position 3 is attending, the scores for attending to positions 4, 5, 6, etc. are set to negative infinity.
Precisely. And when you take the softmax of a vector containing negative infinity, those positions get a probability weight of essentially 0. So future positions contribute nothing to the attention output for the current position. It's a very elegant way to enforce the autoregressive constraint during parallelized training.
Very clever. Okay, that sets up the overall structure. Now let's get to the absolute heart of it. Section 3.3, attention, the core mechanism, visually laid out in Figure 2. How do they define an attention function generally?
In its most general sense, they describe it as mapping a query and a set of key-value pairs to an output, where the query, keys, values, and output are all vectors.
Query, keys, values. Let's use that librarian analogy again.
Yeah, it works pretty well. Imagine you query, go to a library with a specific question. You look at the catalog entries or book titles, keys, to see which ones seem relevant to your question. Based on the relevance scores, you then retrieve information, values, from the most relevant books. The attention output is like a synthesized answer based on a weighted combination of the information you retrieved.
So the output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key.
Exactly. That compatibility function is the crucial part that determines how much attention a query should pay to each key value pair. In the transformer, the primary compatibility function they use is the dot product.
Which brings us neatly to section 3.3.1, scale dot product attention. This is shown on the left side of Figure 2. How does this specific mechanism work step by step? Let's really dig into the math here.
Okay, it starts with 3 inputs, which are typically matrices for efficient computation across a batch of sequences in multiple positions. Q for queries, K for keys, and V for values. Let's say Q has dimensions, num queries dk, K has num keys dk, and V has num keys dv. Note that the query and key dimensions dk must match, but the value dimension dv can be different. The process unfolds in 4 main steps. 1. Compute dot products. We compute the dot products of the query with all keys. Mathematically, this is achieved via matrix multiplication, QKT. If Q is num queries xdk and KTK transposed as dkx num keys, the result is a matrix of size num queries x num keys. Each element, ij, in this resulting matrix represents the raw compatibility score, the dot product, between the ith query vector and the ja key vector.
So this matrix essentially holds all the raw relevance scores between every query and every key.
Exactly. That's the raw attention score matrix. 2, scaling. This is critical. They divide each dot product by square RT dk. So the operation becomes QKT S square RT dk.
Okay, why this specific scaling factor, the square root of the key dimension? This seems important.
It's incredibly important, and the paper gives the reasoning. They found that for large values of dk, the dot products grow large in magnitude. Why? If you assume the components of the query Q and key K vectors are independent random variables with mean 0 and variance 1, then their dot product QK equals sum key will have a mean of 0 but a variance of dk. That's in footnote 4.
So as dk gets larger, the variance, the spread of the dot products increases. The values get bigger on average.
Right, and if these dot product values become very large, they can push the softmax function into regions where it has extremely small gradients.
What does that mean? Why are small gradients bad?
The softmax function takes a vector of scores and turns it into a probability distribution. If one score is much larger than the others, softmax will assign it a probability very close to 1 and all others very close to 0. When the outputs are saturated like this, stuck near 0 or 1, the gradient of the softmax function becomes tiny. Small gradients mean that during backpropagation, the updates to the model's weights become minuscule and the model essentially stops learning effectively. This is the vanishing gradient problem again.
So the large dot products could effectively paralyze the learning process.
Precisely. Dividing by score TDK counteracts this. Since the variance of the dot product scales with dk, dividing by score TDK scales the variance back down towards 1, keeping the inputs to the softmax in a healthier range where gradients are more meaningful. It stabilizes the training. 3. Softmax. After scaling, they apply a softmax function to obtain the weights on the values. The operation is now softmax, QKT, score TCTK. The softmax function takes that matrix of scaled scores and converts each row into a probability distribution. So for each query I, the j-type element in the resulting row is the attention weight alpha, representing how much attention query I should pay to key value j. The sum of weights for each query across all keys will equal 1.
So these are the actual attention weights, ranging from 0 to 1 and 0.4, weighted sum. Finally, we compute the weighted sum of the values. The full formula is softmax, QKT, score RT-DKV. The matrix of attention weights, output of softmax, size num queries, x num keys, is multiplied by the V value matrix, size num keys, xdv. This effectively computes for each query a weighted average of all the value vectors, where the weights are determined by the attention scores. The final output is a matrix of size num queries, xdv, where each row is the contextualized representation for the corresponding query. So equation 1, attention QK, V equals softmax QKT, scar TDKV. That neatly captures the entire process. Calculate raw scores, scale them, turn scores into probabilities, weights, and use those weights to combine the values.
Exactly. It's a concise and powerful formulation.
The paper also briefly compares this scale dot product attention to other types, like additive attention.
Yes, they mention additive attention, used in some earlier influential models, which computes the compatibility score using a feed-forward network with a single hidden layer. They also mention dot product multiplicative attention, which is essentially identical to theirs but lacks the crucial score TDK scaling factor.
And the advantage of their scaled version.
Beyond the stability benefit of scaling, they state it's much faster and more space efficient in practice, since it can be implemented using highly optimized matrix multiplication code. Additive attention involving that extra feed-forward network is generally slower and more complex to implement efficiently. Leveraging highly optimized linear algebra libraries for matrix multiplication gives scaled dot product attention a significant practical speed advantage, especially on hardware like GPUs.
Okay, that's scaled dot product attention. But the transformer uses multi-head attention. Section 3.3.2, shown on the right of Figure 2. The paper says, instead of performing a single attention function with d-model dimensional keys, values, and queries, we found it beneficial to linearly project the queries, keys, and values times with different learned linear projections. Why? Why do this?
This is one of the most ingenious parts of the transformer. The core motivation, as the paper states, is that multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. With a single attention head, averaging inhibits this.
Different representation subspaces, what does that mean?
Think of it like this. A single attention mechanism trying to capture all types of relationships, syntactic, semantic, positional, long range, short range, might end up just averaging them all together into a single representation. This averaging could blur or lose distinct important signals?
So it might struggle to focus on multiple things at once.
Exactly. Multi-head attention solves this by creating multiple heads, where each head learns its own projection of the query's keys and values into a lower dimensional space. Each head can then specialize and focus on learning different types of relationships or extracting different features from the input.
Like having multiple specialists looking at the same data, one focusing on grammar, another on meaning, another on long-distance connections.
That's a perfect analogy. One head might learn to track subject-verb agreement. Another might focus on resolving pronoun references, like it, animal. Another might capture stylistic nuances, and so on. By having multiple heads, H of them, typically 8 in the base model, the model can capture a richer, multifaceted understanding of the sequence.
Okay, so how does it work technically? Let's go step by step through the multi-head process.
Right, it involves these main steps. 1, linear projections. For each of the H heads, let's index them by I from 1 to H. The original input query Q, key K, and value V matrices, which are D-model dimensional, are linearly projected into lower dimensional spaces using different learned weight matrices for each head. 1, linear projections, key, WQI. 1, linear projections, key, WQI. 1, linear projections, VI, V, WVI. 1, linear projections. Here, WQI, and WVI are the unique parameter matrices for head I. For example, WQI projects Q from D model down to DK dimensions. WQI has shape D model X DK. Similarly, WQI projects K to DK and WVI projects V to DV. These projections allow each head to look at the input data from a different perspective or subspace. 2, parallel attention calculation. On each of these projected versions of queries, keys, and values, we then perform the attention function in parallel, yielding DV dimensional output values. So for each head I, they calculate heady, attention, chi, key, guy. So for each head I, they calculate. This attention function is exactly the scaled dot product attention we just discussed, but applied independently and in parallel for each head using its specific projected kuyu, ki, v. Each heady produces its own DV dimensional output vector, representing the contextualized information captured by that specific head. 3, concatenation. These outputs from all heads are concatenated. 3, concatenation. The output vectors head 1, head 2, head are simply concatenated together side by side into one larger vector or matrix. If each heady has dimension dv, the concatenated output will have dimension h dv4. Final linear projection, and once again projected, resulting in the final values. 4, final linear projection. This large concatenated matrix is then multiplied by one final learned weight matrix, WO. The full multi-head attention calculation is multi-head Q, Ka, B, quad GO. The full multi-head attention calculation is this final projection matrix WO has dimensions, HD plus DV D model. Its role is to take the combined information from all the heads and project it back down to the model's standard hidden dimension D model. This ensures the output of the multi-head attention layer has the right dimensionality to be fed into the next layer or added to the residual connection.
So it projects down, does attention in parallel across multiple specialized views, concatenates those views, and then projects back up to the main dimension. That's clever.
It's very elegant.
The paper specifies they use 8 parallel attention heads, and for each head, they use dimensions dkdv, d model h equals 64. Since d model is 5, 12, 12, dividing by 8 heads gives 64 dimensions per head for keys and values.
That's the standard setup for the base transformer model, yes.
Now, does having 8 heads, even with these reduced dimensions per head, significantly increase the computational costs compared to just one big attention head?
Surprisingly, no. And this is another brilliant part of the design. The paper notes, due to the reduced dimension of each head, the total computational cost is similar to that of single head attention with full dimensionality.
How does that work out?
Let's look at the rough computational complexity. The dominant cost in attention is the matrix multiplications, which scale roughly quadratically with the dimensions involved. A single attention head operating at the full D model dimension would have a cost proportional to something like N2D model for QKT plus NE model 2 if QK EV projections are included, or maybe just N2DK plus NDKDV focusing just on the core attention. Let's simplify and compare the projection costs in the attention calculation. A single head projection might be 3 ND model 2 and attention N2D model, with H heads each operating on dimensions DK ulis dan D model H NW ulis D model H. The projection cost per head is roughly proportional to ND model DK. Total projection cost for H heads, HA ND model, D model H, ND model 2, similar for K and B, so maybe maybe 3 in D model 2 total. The attention calculation cost per head is roughly proportional to N2DK. Total attention cost for H heads. HN2 D model H equals N2 D model. The attention calculation cost per head is roughly proportional to N2DK. Total attention cost for H heads. Then there's the final projection WO, which involves NHEVB, D model, NHB model, D model, ND Ben D model 2. So if you add those up, the total cost for multi-head attention is roughly in the same ballpark, or even potentially slightly less complex in some parts as a single head operating at the full D model dimension, especially if DK and DV are significantly smaller than D model. They essentially trade off the dimension size against the number of heads to keep the overall computation manageable while gaining the representational power of multiple subspaces.
That's incredibly efficient.
Yeah.
Getting the benefit of multiple views without a major computational hit.
Exactly. It's a key reason why the transformer architecture is so effective and relatively efficient.
Okay, so where is this powerful multi-head attention actually used within the transformer model? Section 3.3.3 lists 3 distinct ways.
Yes. The transformer strategically deploys multi-head attention in 3 crucial contexts. 1. In the encoder-decoder attention layers. These layers are found only in the decoder stack. 1. In the encoder-decoder attention layers. Here, the queries Q come from the output of the previous decoder layer. 1. In the encoder-decoder attention layers. But the keys, K, and values, V, come from the output of the final encoder layer, that representation Z we talked about. 1. In the encoder-decoder attention layers, the purpose allows every position in the decoder to attend over all positions in the input sequence. This is the mechanism by which the decoder accesses the meaning and context of the source sentence that the encoder captured. It's looking back at the input to inform the output generation. It mimics the typical decoder attention mechanisms seen in earlier sequence-to-sequence models. 2. In the encoder self-attention layers. These layers reside within each of the annually 6 encoder layers. Here, all 3 inputs, queries, Q, keys, K, and values V come from the same place, specifically the output of the previous layer in the encoder. Here, all 3 inputs, queries, Q, keys, K, and values V come from the same place, the purpose. Each position in the encoder can attend to all positions in the previous layer of the encoder. This allows the encoder to build up increasingly sophisticated representations of each input token by considering its relationship with all other tokens in the input sequence. It refines the understanding of the input context layer by layer. 3. In the decoder masked self-attention layers. These layers are found within each of the N-6 decoder layers. Similar to the encoder self-attention, the queries Q, keys, K, and values V all come from the same place, the output of the previous layer in the decoder. Similar to the encoder self-attention, the queries Q, keys, K, and values V all come from the same place, the purpose. Similarly, self-attention layers in the decoder allow each position in the decoder to attend to all positions in the decoder up to and including that position. This helps the decoder understand the context of the output sequence it has generated so far. But crucially, as we discussed, there's a constraint. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. And the implementation is the masking. We implement this inside of scale.product attention by masking out setting to all values in the input of the softmax, which correspond to illegal connections, i.e. connections to future positions J, E, I.
That clarifies the 3 distinct roles perfectly.
Yeah.
Okay, beyond attention, what's the other sublayer found in each encoder and decoder layer? That takes us to section 3.4. Position-wise feed-forward networks.
Yes, the FFNs. In addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected feed-forward network. And the key phrase here is, which is applied to each position separately and identically.
Separately and identically. What does that mean in practice?
It means that the same feed-forward network with the exact same learned weights W1, B1, W2, B2 is applied to the representation of each word or token position in the sequence. However, the computation for each position is done completely independently of the others. It's not looking across positions like attention does, it's just processing each position's vector on its own.
So it's like each word vector gets passed through its own identical mini-neural network after the attention step.
Exactly. This network provides additional nonlinear transformation capabilities within each layer.
And what's the structure of this FFN?
It's pretty simple. It consists of 2 linear transformations with a real U activation in between. The formula given is equation 2. FFNX, max W1, XW1 plus B1, W2 plus B2. Let's break that down. 1 XW1 plus B1. The input vector X, the output from the preceding attention sublayer after layer norm for a specific position, is multiplied by a weight matrix W1 and a bias B1 is added. This is the first linear transformation, which typically expands the dimensionality to max CO0. The result is then passed through a rectified linear unit, ReLU activation function. ReLU introduces nonlinearity by setting any negative values to 0 and leaving positive values unchanged. This is crucial for the network to learn complex patterns, 3-point W2 plus B2. The output of the ReLU is then multiplied by a second weight matrix W2 and another bias B2 is added. The second linear transformation typically projects the dimensionality back down.
So input linear expansion, ReLU linear contraction output.
That's the flow for each position independently. The paper notes while the linear transformations are the same across different positions, they use different parameters from layer to layer.
Right, so the FFN in layer 1 has different weights, W1, B1, W2, B2, than the FFN in layer 2, but within layer 1, all positions use the same weights.
Precisely. They also offer an alternative perspective. Another way of describing this is as two convolutions with kernel size 1.
How does that work?
A convolution with a kernel or filter of size 1 essentially means the filter looks at only one position at a time. Applying such a filter across the sequence dimension independently at each position is mathematically equivalent to applying the same linear transformation defined by the filter weights to each position's vector. So, two 1-by-1 convolutions with a ReLU in between is equivalent to this position-wise FFN structure. It emphasizes the parallel and local nature of this operation.
And what about the dimensions here?
The dimensionality of input and output is D model equals 512, maintaining consistency. And the inner layer, meaning the output dimension after the first linear transformation and ReLU, xW1 plus B1, has dimensionality DFF 2048.
Wow, so it expands quite a bit, from 512 up to 2048, then back down to 512.
Yes, this expansion in the intermediate layer, DFF is typically 4 times D model, gives the network more capacity to learn complex features and transformations before projecting back to the standard dimension needed for the next layer and the residual connection.
Yeah, that covers the core layer structure. Next up, section 3.5, embeddings and softmax, basically the input and output layers.
Right, this is about how we get tokens into the model and probabilities out.
Right.
Similarly to other sequence transduction models, we use learned embeddings to convert the input tokens and output tokens to vectors of dimension D model.
Learned embeddings, these are crucial, right?
Yeah.
Mapping discrete words or subwords into continuous vectors.
Absolutely essential. These embeddings are learned during training and capture semantic and syntactic information about the tokens. They allow the model to process language numerically and understand relationships between words based on their vector representations in this D-model dimensional space.
And then on the output side, how does the decoder translate its final internal vector representation back into a prediction for the next word?
We also use the usual learned linear transformation and softmax function to convert the decoder output to predicted next token probabilities. So, the final D-model dimensional output vector from the top decoder layer is passed through one more linear transformation, learned weight matrix, that projects it up to the size of the vocabulary.
So if the vocabulary has 37,000 tokens, this linear layer outputs a vector of 37,000 numbers.
Exactly. And then that vector of raw scores, called logits, is passed through a softmax function. The softmax converts these scores into a probability distribution across the entire vocabulary, where each probability indicates the model's confidence that that specific token should be the next one in the sequence.
And typically, you'd pick the token with the highest probability as the output word.
That's the most common approach, greedy decoding. Or you use something like beam search, which we'll discuss later.
The paper mentions an interesting detail here. In our model, we share the same weight matrix between the two embedding layers, input embedding and output embedding, and the pre-softmax linear transformation, citing reference 30. Why share these weights?
This is a common and often beneficial technique. It means the same matrix is used for 3 purposes. 1, to convert input tokens into D-model vectors. 2, to convert target tokens, during training teacher forcing, into D-model vectors for the decoder input. 3, to convert the final decoder output vector, size D-model, into vocabulary size logits before the softmax.
What's the advantage of using the same matrix for all 3?
There are a couple of potential benefits. First, it significantly reduces the number of parameters in the model, as you only need 1 large matrix instead of 3. Fewer parameters can act as a form of regularization, helping to prevent overfitting. Second, it intuitively ties the input and output representations together. It suggests that the way a word is represented as input should be related to how the model predicts that word as output, enforcing consistency.
Makes sense. And there's one more scaling detail. In the embedding layers, we multiply those weights by score, D-model. Why this scale?
This is often done, especially when you have positional encodings that are added to the embeddings. The magnitude of learned embeddings can vary during training. Scaling them by SCORT-T model helps to normalize their magnitude relative to the positional encodings, whose magnitude is somewhat fixed by the syncos functions. It helps ensure that neither the embedding nor the positional encoding dominates the other when they are summed, leading to more stable training, particularly in the early stages.
Okay, that makes sense. Balancing the contribution of meaning and position. Which brings us perfectly to the last piece of the architecture puzzle, section 3.6, positional encoding. This is super important because, as the paper states, since our model contains no recurrence and no convolution, we must inject some information about the relative or absolute position of the tokens.
This is the crux of handling order in a purely attention-based model. As we discussed, attention itself is permutation invariant. It treats the input as a bag of vectors. If you shuffled the words in a sentence, the self-attention output for each word before positional info would be identical because it only cares about pairwise relationships, not sequence order.
But order is critical in language. Dog bites man versus man bites dog.
Exactly. So without recurrence or convolution, which inherently process sequence order, the transformer needs an explicit mechanism to tell the model where each token is located in the sequence.
In their solution.
To this end, we add positional encodings to the input embeddings at the bottoms of the encoder and decoder stacks.
Add meaning just element-wise vector addition.
Yes, direct element-wise summation. For this to work, the positional encodings have the same dimension D model as the embeddings so that the two can be summed. The resulting vector combines the token's semantic meaning from the embedding with its position information from the positional encoding.
The paper mentions there are many choices of positional encodings, learned and fixed. What did they choose?
They chose a fixed, non-learned method using sine and cosine functions of different frequencies.
Okay, let's get into these formulas.
Yeah.
They look a bit intimidating at first glance, but they're actually quite elegant.
They are. The positional encoding vector PE for a given position, postes in the sequence, is defined differently for even and odd dimensions I, where it goes from 0 up to D model 2, 1. PE post I, sin post to sum post 2ID model for even dimensions. PE post 2I plus 1 equals cos post B post 2ID model for odd dimensions. Let's break down the terms inside the syncos. This is simply the position of the token in the sequence. 0 for the first token, 1 for the second, and so on. $110,000. This is just a large constant chosen by the authors. It affects the range of wavelengths used, .I. This is the dimension index. Each pair of dimensions, 2I, 2I plus 1, uses the same frequency, but with both a sine and a cosine wave. 2ID model. This exponent term is the key to getting different frequencies. As the dimension index increases from 0 up towards D model 2, this term 2ID model increases from 0 towards 1.
So 1000 2ID model gets larger as I increases.
Exactly, which means the denominator post 1000 2ID model gets smaller. This argument inside the sin and cos determines the frequency or wavelength. A smaller argument means a lower frequency or a longer wavelength.
Ah, so lower dimensions, small i's, correspond to high frequencies, short wavelengths, and higher dimensions, large I, correspond to low frequencies, long wavelengths.
Precisely. The paper says each dimension of the positional encoding corresponds to a sinusoid. And importantly, the wavelengths form a geometric progression from 2π2 to 10,000 2π.
Why is a geometric progression of wavelengths useful?
It means the model has access to positional signals at many different scales simultaneously. The high-frequency waves, small I, can encode very fine-grained relative position information between adjacent words. The low-frequency waves, large I, can encode coarser positional information over much longer distances in the sequence. This allows the attention mechanism to potentially learn to attend to relative positions effectively, regardless of the distance.
And the authors had a specific hypothesis about why this sinusoidal approach might be good.
Yes. We chose this function because we hypothesized it would allow the model to easily learn to attend by relative positions, since for any fixed offset k, PE post plus k can be represented as a linear function of PE post.
A linear function, how does that work?
It comes from the trigonometric angle addition formulas. Sin A plus B plus cos A sin B and cos A plus B cos B sin sin B. If you let A cos wavelengthy and B k wavelengthy, you can see that PE post plus K at dimension I can be expressed as a linear combination of PE post 2I and PE post 2I plus 1, where the coefficients of the combination depend only on the offset K and the wavelength, i.e. they are fixed for a given offset K.
Wow. So the model doesn't need to learn a completely different pattern for position 5 relative to position 3 versus position 105 105 relative to position 103, the relationship is encoded linearly.
That's the hypothesis. This property might make it much easier for the network's linear transformations, like those in the attention projections, to leverage relative positional information.
Did they test other methods, like learned positional embeddings?
They did. We also experimented with using learned positional embeddings 9 instead, and found that the two versions produced nearly identical results. See Table 3 row.
So, if learned embeddings work just as well, why stick with the more complex sinusoidal functions?
But there's a crucial potential advantage to the sinusoidal version, extrapolation. We chose the sinusoidal version because it may allow the model to extrapolate to sequence lengths longer than the ones encountered during training.
How so?
Learned embeddings are discrete. If you train a model on sequences up to length 512, it learns specific embedding vectors for positions 0 through 511. If you then give it a sequence of length 600 at test time, it has no learned embedding for position 512 or beyond. What do you do? The sinusoidal functions, however, are defined mathematically for any position post. You can generate a valid positional encoding for position 1000 even if the model only ever saw sequences up to length 500 during training. This gives the sinusoidal approach a theoretical edge in generalizing to unseen sequence lengths.
That's a really important practical consideration. Okay, that wraps up the core architecture. Now, part 4. Why self-attention? This section really justifies their core architectural choice by comparing it to the alternatives.
Exactly. The goal here is to compare self-attention layers head-to-head against the recurrent and convolutional layers that were dominant for sequence-to-sequence tasks at the time. They frame the comparison around 3 key desirable properties, or desiderata, for a sequence processing layer. 1. Total computational complexity per layer. Basically, how much number crunching is required, usually expressed in big O notation relative to sequence length n and representation dimension d. Lower is generally better. 2. Amount of parallelization, measured by the minimum number of sequential operations required. Can computations be done simultaneously? O1, constant time, independent of sequence length, is the ideal for parallel hardware like GPUs. ON, linear time, means sequential processing. 3. Path length between long-range dependencies. How many computational steps does information need to traverse to get from one arbitrary position in the sequence to another arbitrary position? Shorter paths make it easier to learn long-range dependencies, as signal and gradients don't have to travel as far. O1 is again the ideal.
And Table 1 in the paper provides a fantastic summary of this comparison. Let's walk through it, starting with their proposed solution. Self-attention.
Okay, for a self-attention layer. Complexity per layer. O N2 day. As we discussed, the N2 comes from the fact that every position attends to every other position. N queries x n keys equals N2 dot products. The D factor comes from the dimensionality of the representations involved in these calculations. Sequential operations. O1. This is the killer feature. All the pairwise attention scores, the softmax, and the weighted sums of values can be computed in parallel across all n positions simultaneously. No waiting for the previous step. Maximum path length, O1. Also revolutionary. Any two positions in the sequence are connected directly via a single attention operation. The path length is constant, regardless of how far apart the positions are in the sequence n. This directly tackles the long-range dependency problem.
So even though the complexity has that N2 term, which can be costly for very long sequences, the O1 parallelism and O1 path length are the game changers for training efficiency and learning long-range patterns.
Precisely. The paper points out an interesting regime. Self-attention layers are faster than recurrent layers when the sequence length n is smaller than the representation dimensionality d. And they note this is most often the case with sentence representations used by state-of-the-art models in machine translations, where d, like 512, is often larger than typical sentence lengths n.
They also mention a way to handle very long sequences.
Yes, they acknowledge the N2 cost could be prohibitive for extremely long sequences, like maybe whole documents or high-res images. They suggest a future direction. Self-attention could be restricted to considering only a neighborhood of size R in the input sequence centered around the respective output position.
Like only attending to nearby words.
Exactly. This restricted self-attention would reduce the complexity to OIR, making it linear in M instead of quadratic. However, the trade-off would be an increase in the maximum path length to OIR, as information would have to hop between these local windows to cross long distances. It wasn't implemented in the original paper, but showed they were thinking about scalability.
Okay, now let's compare that to the incumbent. Recurrent layers, like LSTM's GRUs.
For recurrent layers, complexity per layer, OND2. The D2 factor comes from the matrix multiplications involved in the recurrent update. e.g. HTH1 plus WXH x where HH is DXD. The n factor comes from having to perform this calculation sequentially for each of the n steps in the sequence. Sequential operations, ON. This is their fundamental limitation. Each state HT depends on the previous state HE1, forcing sequential execution step by step. This severely limits parallelization within a sequence. Maximum path length, ON. Information from the beginning of the sequence has to pass sequentially through all n intermediate steps to reach the end. This long path makes it difficult for gradients to flow effectively and for the model to capture dependencies between distant parts of the sequence.
So, compared to self-attention, RNNs are bottlenecked by sequential operations at long path lengths, even if their per-step complexity involves D2 instead of N2.
Exactly. The transformer sacrifices per-step complexity, potentially for large n, for massively improved parallelism and direct long-range connections.
What about the third contender? Convolutional layers, used in sequence models like ByteNet or ConvS2S.
For convolutional layers, with kernel size k, complexity per layer. For simple comms, or OKND2, if including depth-wise separable Pong variations. Let's stick with the paper's OKND2 for comparison. The com comes from the kernel width, n because the kernel slides across the sequence, and d2 from filter operations on d-dimensional vectors. Sequential operations, O1. Like self-attention, convolutions can be applied in parallel across all positions simultaneously. So they are parallelizable, maximum path length. This is where they fall short of self-attention. For standard contiguous kernels, the path length is O. Using dilated convolutions, as in ByteNet, can improve this to O log n, but in either case, a single convolutional layer with a kernel size k less than the sequence length n does not connect all pairs of input-output positions directly.
You need to stack multiple convolutional layers to allow information propagate across the whole sequence.
Precisely. And stacking layers increases the effective path length. While O log n is much better than the ON of RNNs, it's still not the O1 direct connection offered by self-attention.
And computationally.
The paper notes, convolutional layers are generally more expensive than recurrent layers by a factor of k. They mention separable convolutions can reduce the complexity, but even then they argue the complexity is comparable to the combination of a self-attention layer and a position-wise feed-forward layer used in the transformer, suggesting their approach remains competitive or superior.
So self-attention wins on path length and parallelization, O1, at the cost of N2 complexity, while RNNs suffer from ON sequential operations in path length, and CNNs have O1 parallelization but non-constant path length.
That's a perfect summary of the trade-offs highlighted in Table 1. The transformer design prioritizes maximum parallelism and direct long-range connections above all else.
Beyond these core performance metrics, the paper mentions a fascinating side benefit in Section 4.3, interpretability. As side benefit, self-attention could yield more interpretable models.
This is a really appealing aspect. Because the self-attention mechanism explicitly calculates these attention weights, alpha, representing how much position I attends to position j, you can actually visualize these weights. You can create heat maps or connection diagrams showing which parts of the sequence the model focused on when processing a particular word.
And the authors did this.
Yes. They inspect attention distributions from our models and present and discuss examples in the appendix. These visualizations provide glimpses into the model's reasoning. Figure 3, page 13, shows attention patterns for the word making in a complex sentence. The law will never be perfect, but its application should be just, this is what we are missing, this is what makes the difference between a civilized society and total chaos. They highlight that many of the attention heads attend to a distant dependency of the verb making, completing the phrase making dot more difficult. Actually, the example sentence in the appendix for Fig 3 is different. Making attends to more difficult. You can literally see lines connecting making across several words to more and difficult. It's visual proof of learning long-range dependencies. Figure 4. Page 14. Focuses on anaphora resolution, figuring out what pronouns refer to. Using the sentence, the law will never be perfect, but its application should be just. Quote, they show attention patterns for the word its. You see two attention heads, apparently involved in anaphora resolution. The visualization clearly shows strong attention from it. It's pointing directly back to the law. The paper notes the attentions are very sharp for this word, indicating high confidence in the link. It makes the model's reasoning transparent. Figure 5, page 15, shows broader patterns. Many of the attention heads exhibit behavior that seems related to the structure of the sentence. They provide examples suggesting some heads focus on nouns and adjectives, others on verbs and prepositions, indicating specialization. The heads clearly learn to perform different tasks, which reinforces that idea of different representation subspaces from multi-head attention.
So these visualizations aren't just pretty pictures. They offer real insights into how the model is working.
Exactly. They show that not only do individual attention heads clearly learn to perform different tasks, many appear to exhibit behavior related to the syntactic and semantic structure of the sentences. This kind of interpretability is huge for debugging models, building trust in their outputs, and advancing our scientific understanding of what these complex AI systems are actually learning. It's a step away from purely black box models.
A very valuable side effect indeed. Okay, let's move on to part 5. Training, bringing the transformer to life. This section gives the practical details of how they actually train these models, starting with data and batching, section 5.1.
Right. For the key machine translation tasks, English-German, they used the standard WMT 2014 English-German dataset, which contained about 4.5 million sentence pairs. They tokenized the text using byte pair encoding, BPE, resulting in a shared source target vocabulary of about 37,000 tokens. BPE is a subword tokenization method. It breaks words into common sequences of characters, helping handle rare words and morphology better than just using whole words.
And for English-French,
a significantly larger WMT 2014 English-French dataset with 36M sentences. For this, they used a different but related subword method called word piece encoding, yielding a 32,000 word piece vocabulary. Both BPE and word piece aim to find a good balance between character level and word level tokenization.
how do they batch this data for efficient training on GPUs?
This was clever. Sentence pairs were batched together by approximate sequence length, Y, to minimize wasted computation due to padding. If you put very short and very long sentences in the same batch, you have to pad the short ones extensively to match the longest one. Grouping by approximate length makes batches more uniform.
And the batch sizes were huge, right?
Absolutely massive in terms of tokens. Each training batch contained a set of sentence pairs containing approximately 25,000 source tokens and 25,000 target tokens. This large token count per batch is designed to fully saturate the parallel processing capabilities of the GPUs, maximizing throughput.
Speaking of GPUs, section 5.2 covers hardware and schedule. What were they running on?
They trained their models on one machine with 8 NVIDIA P100 GPUs. The P100 was a top-tier GPU for deep learning back then, known for its high memory bandwidth and support for things like FP16 half-precision floating-point computation, which can significantly speed up training.
And the training times were remarkably fast compared to previous models.
Yes. For their base models, each training step took about 0.4 seconds. They trained for 100,000 steps, totaling just 12 hours. For their big models, with more layers dimensions, the step time was 1.0 seconds. They trained for 300,000 steps, which took 3.5 days, for their big models with more layers dimensions. As we'll see later in the results, Table 2, this was a fraction of the time required by other state-of-the-art models to achieve comparable or even worse results.
Incredible speed up. Now, section 5.3, the optimizer. They used Atom, but with a very specific learning rate schedule.
That's right. They used the Atom optimizer, a standard and effective choice known for its adaptive learning rates per parameter. They used fairly standard Atom hyperparameters. Eta 1 equals 0.9, Eta 2 equals 0.98, and OXLs 10 to 9.
But the learning rate itself wasn't constant.
No, and this is a crucial detail for successfully training transformers. We varied the learning rate over the course of training according to the formula given in equation 3. All rate equals D model dash 0.5 mins. Step num dash is 2.5. Step num warm-up steps 1.5. Let's break this down carefully. D model 0.5. This is an overall scaling factor. Since D model equals 512, this is 1 4 T ups 12 for 122.6. It scales the learning rate based on the model's dimensionality. Min, the core of the schedule, lies in this minimum function, which dynamically chooses between two terms based on the current training step number.
Step num.
What are the two terms inside the min, and how do they create the schedule's shape?
The two terms create a schedule with two distinct phases. 1, term 1, step num 0.5. This represents an inverse square root decay. As step num increases, this term decreases. 2, term 2, step num warm-up steps 1.5. This represents a linear increase. Warm-up steps is a fixed hyperparameter. They set it to 4,000. So warm-up steps 1.5 is just a constant. This term increases linearly with step num. Now, how the min function uses these. Warm-up phase, First warm-up steps. For the first 4,000 steps, the linear increase term, step num warm-up steps 1.5, will be smaller than the inverse square root decay term, step num 0.5. So the min function chooses the linear term. This means the learning rate increases linearly from 0 up to a peak value reached at step num warm-up steps. Warm-up phase, first warm-up steps, Y warm-up. Starting training with a high learning rate can cause instability, especially with randomly initialized weights. The warm-up phase allows the model to gently start learning and stabilize before the learning rate gets too large. Decay phase, after warm-up steps. Once step num exceeds 4,000, the inverse square of decay term, step num to 0.5, becomes smaller than the now large linear term. So the min function switches to choosing the decay term. This means the learning rate now decreases proportionally to the inverse square root of the step number for the rest of training. Decay phase, after warm-up steps. Y decay. As the model gets closer to convergence, reducing the learning rate allows for finer adjustments, helping it settle into a good minimum without overshooting or oscillating.
That's a really well-designed schedule. Linear ramp up for stability, then inverse square root decay for convergence. Very clever.
It's become pretty much the standard way to train transformers, or variations of it. Getting the learning rate schedule right is critical.
Okay, finally in the training section, 5.4, regularization. How do they prevent these large models from overfitting?
They use two main regularization techniques. One, residual dropout. They applied dropout, a technique that randomly sets a fraction of neuron activations to 0 during training. The paper specifies where they applied it, to the output of each sublayer before it is added to the sublayer input and normalized. So it's applied inside the sublayer X, part of layer X plus sublayer X equation, host speaker, and anywhere else. Expert speaker. Yes. In addition, we apply dropout to the sums of the embeddings and the positional encodings in both the encoder and decoder stacks. This helps regularize the very input to the model. For the base model, they used a dropout rate of p drop equals 0.1. Dropout acts like training a large ensemble of smaller networks, forcing the model to learn more robust, less codependent features. 2. Label smoothing. They employed label smoothing with a value u is equal 0.1. Host speaker. Label smoothing. How does that work again? Expert speaker. Instead of training the model to be absolutely certain about the correct target label, for example, giving it a target probability of 1.0 and all others 0.0, label smoothing slightly modifies the target. It assigns the correct label a probability of 1 nulls, so 0.9 in this case, and distributes the remaining alls, 0.1 probability mass, uniformly across all the incorrect labels. Host speaker. So it encourages the model to be a little less confident. Expert speaker? Exactly. The paper notes, this hurts perplexity as the model learns to be more unsure. Perplexity measures how surprised the model is by the true data. Lower perplexity means higher confidence. Label smoothing makes the model less certain, so perplexity might go up slightly during training. Host speaker. But it helps in the end. Expert speaker. Yes, but improves accuracy and BLEU score. By preventing the model from becoming overconfident and assigning 0 probability to incorrect labels, it makes the model more robust, less prone to overfitting on the training data's quirks, and ultimately leads to better generalization and performance on unseen data, as measured by metrics like BLEU.
Got it. So, dropout and label smoothing working together to keep the model honest and improve generalization. Okay, that covers how they built and trained it. Now for the payoff. Part 6. Results. The proof is in the pudding. Starting with the main task, machine translation, section 6.1.
Right, on the benchmark WMT 2014 English to German translation task. The big transformer model, transformer big in table 2, outperforms the best previously reported models, including ensembles, by more than 2.0 BLEU, establishing a new state-of-the-art BLEU score of 28.4.
And that was the model trained in just 3.5 days on 8 GPUs. Incredible.
And even more impressively, even our base model surpasses all previously published models and ensembles at a fraction of the training cost of any of the competitive models. So even the smaller, faster-to-train version was beating everything else out there.
What about the English to French results? That was the larger data set.
On WMT 2014 English to French, our big model achieves a BLEU score of 41.8 from Table 2, outperforming all of the previously published single models at less than 14 the training cost of the previous state-of-the-art model. Again, significantly better results for much less computation. They do note a small hyperparameter difference for this task. The big English to French model used a dropout rate p drop equals 0.1, whereas the big English to German model used 0.3, according to Table 3 footnote, though the main text says 0.1 here might be a slight inconsistency or task-specific tuning.
Okay, so clear state-of-the-art results. How did they actually generate the translations during inference to get these scores? What was their inference strategy?
They used a couple of standard but important techniques. 1. Model averaging. They didn't just use the single model from the very last training step. For the base models, we used a single model obtained by averaging the last 5 checkpoints. For the big models, we averaged the last 20 checkpoints. Averaging the weights of models saved at slightly different points near the end of training often yields a more robust and slightly better performing model than any single checkpoint. It's a simple form of ensembling. 2. Beam search. When generating the output sequence word by word, instead of just greedily picking the single most probable word at each step, they use beam search with a beam size of 4. Beam search keeps track of the top, come here for, most probable partial translation hypotheses at each step. It explores a wider range of possibilities, increasing the chance of finding a globally better translation compared to just following the single best path. Host speaker, and they used a length penalty. 8.6 expert speaker. Yes! Beam search can sometimes favor shorter sequences because probabilities multiply, and shorter sequences have fewer multiplications. A length penalty adjusts the score based on sequence length to counteract this bias and encourage translations of more appropriate length. They also set a maximum output length, input length plus 50, but allowed early termination.
Let's dive into Table 2 itself now. It summarizes the results and compares quality, BLEU, and training costs using FLOPs.
Right, Table 2 is where the quantitative comparison really shines. They estimate FLOPs, floating point operations, as a hardware-agnostic measure of total computation, multiplying training time, number of GPUs, and the estimated sustained performance of each GPU. Footnote 5 suggests 9.5 TFLOPS for P100.
Can you pick out one or two key comparisons that really highlight the transformer's advantage?
Let's look at English to German again. Transformer big. 28.4 BLEU, using 2.3 by 119 FLOPs. Compare that to the GNMT plus RL ensemble, previous SOTA ensemble. 26.30 BLEU, over 2 BLEU points worse, using a staggering 1.8 by 1019 FLOPs. That's nearly 8 times more computation for a significantly lower score. Or English to French, transformer, big, 41.8 BLEU using 2.3 by 1021 FLOPs. That's over 47 times more computation for roughly comparable or slightly worse quality.
Wow, the numbers are just undeniable. Orders of magnitude improvement in efficiency for state-of-the-art or better quality.
It completely changed the economics and feasibility of training high-quality sequence models.
Now, besides the headline results, they also performed ablation studies in Section 6.2, model variations, summarized in Table 3. What was the goal here?
The goal was to evaluate the importance of different components of the transformer. They systematically varied aspects of their base model architecture and measured the impact on performance. BLEU score on the English to German development set, Newstis 2013. This helps understand which design choices really matter.
Let's look at the findings row by row or group by group. Group A varied the number of attention heads, HH, and the dimensions per head, DK, DB, keeping total computation roughly constant.
The results showed that, while single-head attention is 0.9 BLEU worse than the best-setting H8, quality also drops off with too many heads, HA16. So multi-head attention is definitely beneficial compared to a single head, but there's a sweet spot. Simply adding more and more heads doesn't necessarily help and can even hurt performance slightly. H8 seemed optimal for D model 512.
Group B reduced the attention key size DK while keeping DV constant.
They found that reducing the attention key size DK hurts model quality. This is interesting. It suggests that the dimensionality used for calculating the attention scores, DK, is important for performance. Their interpretation is quite insightful. This suggests that determining compatibility is not easy and that a more sophisticated compatibility function than dot product may be beneficial. Perhaps just using a 64-dimensional dot product isn't fully capturing the nuances needed for compatibility.
Group C and D looked at model size, bigger D model, bigger DFF, and the effect of dropout.
Unsurprisingly, they found bigger models are better, confirming that increasing model capacity, D model DFF, generally improves performance up to a point. And critically, dropout is very helpful in avoiding overfitting. Removing dropout, setting pdrop 0.0, caused a significant drop in BLEU score, highlighting its importance for regularization in these large models.
And finally, Group E compared their sinusoidal positional encoding to learned positional embeddings.
As mentioned before, they observe nearly identical results to the base model. So, for the sequence lengths encountered during training and testing for this task, learned embeddings worked just as well. However, the author's choice of sinusoidal encoding was still justified by its potential theoretical advantage for extrapolating to longer, unseen sequence lengths.
Okay, that gives a great breakdown of the architectural contributions.
Yeah.
But did the transformer generalize beyond translation? Section 6.3 tests it on English constituency parsing. Remind us what that is again.
English constituency parsing is the task of analyzing the grammatical structure of a sentence and representing it as a hierarchical tree of constituents, things like noun phrases, NP, verb phrases, VP, prepositional phrases, P, etc. It identifies who did what to whom structurally.
And the paper mentions this task has specific challenges.
Yes. The output is subject to strong structural constraints. It has to be a well-formed tree. The output representation, the linearized tree, is often significantly longer than the input sentence. And importantly, previous RNN sequence-to-sequence models had not been able to attain state-of-the-art results in small data regimes for this task.
How did they set up the transformer for parsing?
They use a slightly different configuration. A 4-layer transformer with D model equals 1024, so shallower but wider than the base translation model. They trained it in 2 settings, WSJ only, using just the standard Penn tree bank, WSJ section dataset, which has only about 40K training sentences. This tested the small data regime, semi-supervised, using a much larger dataset of approximately 17M sentences derived from other corpora following prior work. Semi-supervised. They used appropriate vocabularies, 16K for WSJ, 32K for semi-supervised, and did only a small number of experiments to select the dropout, learning rates, and beam size, keeping most other hyperparameters the same as the translation model. So minimal task-specific tuning.
And the parsing results in Table 4. How did the transformer do?
Our results in Table 4 show that despite the lack of task-specific tuning, our model performs surprisingly well, yielding better results than all previously reported models with the exception of the Recurrent Neural Network Grammar 8, which was a highly specialized model for parsing.
But the key comparison was to other sequence-to-sequence models.
Exactly. In contrast to RNN sequence-to-sequence models 37, the transformer outperforms the Berkeley parser 29, even when training only on the WSJ training set of 40K sentences.
That is significant. RNN C2sec models struggled on small parsing datasets, but the transformer did well even with limited data.
Yes, it showed that the transformer's architectural advantages, efficient handling of dependencies, perhaps better sample efficiency due to parallelism, allowing larger batches, enabled it to learn complex structural constraints, even from relatively little data, overcoming a known weakness of previous sequence-to-sequence approaches on this task. It really underscored its generalization capability.
Fantastic. Okay, let's wrap things up with Part 7. Conclusion, the path forward. How did the authors summarize their achievement?
They state clearly. We presented the transformer, the first sequence transduction model based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architectures with multi-headed self-attention. They reiterate the core benefits. It can be trained significantly faster than architectures based on recurrent or convolutional layers, and achieved a new state-of-the-art on both WMT 2014 English to German and English to French translation, even beating the best ensembles in the English to German case.
What was their vision for the future, looking ahead from 2017?
They were clearly excited about the future of attention-based models and planned to apply them to other tasks. Well, that certainly came true. Transformers are everywhere now.
What else did they plan?
They plan to extend the transformer to problems involving input and output modalities other than text, things like images, audio, video. Again, we see this realized today with vision transformers, audio transformers, etc. They also plan to investigate local restricted attention mechanisms to efficiently handle large inputs and outputs, such as images, audio, and video, directly addressing the ON2 scalability concern we discussed. And finally, making generation less sequential is another research goal of ours, aiming for even more parallelism, potentially in the decoding process itself.
It's amazing how many of those future plans have become major research areas and successes in the years since.
It really shows their foresight.
And they conclude with a crucial point about open science.
Yes. The code we use to train and evaluate our models is available at https://github.com/tensor-to-a-tensor. Making the code publicly available was absolutely pivotal. It allowed researchers everywhere to immediately start using, adapting, and building upon the transformer, massively accelerating progress in the entire field.
A truly foundational contribution in every sense. Okay, and there you have it. We've journeyed deep into the mechanics and motivations of attention is all you need. From that radical decision to ditch recurrence entirely.
To the elegant math behind scale dot product and multi-head attention, figuring out why that score TTK scaling matters, how multiple heads give different views.
And how those clever sinusoidal positional encodings manage to preserve sequence order without any sequential processing. You hopefully now have a much clearer understanding of how this single paper completely redefined the possibilities in AI.
And remember, the transformer isn't just some abstract research concept anymore. It's the engine humming away behind so much of the advanced AI you interact with every day. Understanding its foundations gives you, we hope, a much deeper appreciation for these incredible technologies.
It moves you beyond just being a user to being someone who's truly informed about how this stuff actually works at the cutting edge. So here's a final thought to leave you with. If simply rethinking a core assumption, like the necessity of recurrence for sequences, could lead to such a monumental leap forward, what other fundamental assumptions in today's AI models might be waiting to be challenged?
That's a great question. What seemingly essential part of our current best models, maybe even attention itself, or the specific way we use feed-forward layers, or something else entirely could be the next recurrence that gets dispensed with, leading to the next paradigm shift in AI.
Something to ponder. We definitely encourage you, if you're interested, to seek out the original Attention is All You Need paper. Look at the diagrams, maybe even peek at the code if you're adventurous.
The beauty of this work really lies not just in the headline results, but in the elegant simplicity and the sheer profound impact of its core ideas.
That's all for this deep dive. Thanks for joining us.
See you next time.